Hi everyone. So today we are going to see the marathon on data converters. So we are going to study all the kind of ADC and DAC. We will see the basics of that. We will see the specifications. Then we will see all kind of types which are there for ADC and DAC, and we will solve assignment as well. Along with that, we will solve one amazing question as well. So these kind of things we are going to see. So what I am expecting, I am expecting 100 likes, and by the end of the session, I am expecting there will be 1000 views. Okay, so do share it with your friends so that I can bring more and more content on YouTube. First, we are going to see the basics of analog. Basically, we are going to see the basics of op-amp because that is required to study data converters. So, if you already know the basics of op-amp, then you can skip that part. That would be somewhat around 20 minutes video. So, you can skip that 20 minutes video and then proceed to the data converters. So, first we are going to see the basics, then we will study the data converters. So, I hope you will enjoy the video. I do not hope, I am certainly sure that you are going to enjoy the video. Once you are done watching the video, if you like the content, please click on the like button and don't forget to share it with your friends. Thank you very much. So let's start the session now. Yeah, hi everyone. So in this video we are going to cover only the basic part of analog which is required for data converters. Only the basic part. We are not going to cover op-amp comprehensively or analog comprehensively. Whatever that is required for data converters, that we are going to do. Okay, so in analog electronics, when we study analog electronics, there we use a IC. IC means integrated circuit. So which is known as op-amp. So this is known as op-amp. So in op-amp there are two input terminal. This is known as inverting input terminal, inverting V negative, and this is known as non-inverting input terminal, non-inverting, right? And the input current of op-amp is always 0. It will always drive 0 ampere current. From positive terminal as well, from negative terminal as well, it will always drive 0 ampere current. So these things you need to know. Now here op-amp is working as a comparator. Basically V positive terminal is there, V negative terminal is there, V positive terminal is there. Now if your V positive is greater than V negative, then your output will be 1. And if your V positive is less than V negative, then your output will be 0. 1 means logic high. This we are considering in case of digital electronics. Logic high. Actually it would have been plus V set. That you don't need to care, so I would not write it here. Basically in analog when we study, output will be plus V set and minus V set. But in digital when we are going to study, we will see logic high, logic low. So what did you understand? When V positive, this is greater than this potential. V positive is greater than V negative, then output will be logic high. If V positive is less than V negative, output will be logic low. Very basic thing. I hope it is clear to you, right? And V naught is mostly given by A into V positive minus V negative. This is how V naught is given. This is your A, gain A. But if nothing is mentioned, for ideal op-amp, gain A is taken as infinity. So these things you do not need to know. From this slide, only thing which you need to know is that if this is greater, V positive is greater, then output will be 1. If it is less, then output will be 0. That's it. This is the only thing which you need to remember from this particular slide. Or you can also remember that V naught is given as A into V positive minus V negative. This is also you can remember. Okay, and ideally gain A is very high, very infinity, towards infinity. Let's solve some questions. What do you think what will be the output? V positive is greater than V negative, output will be 1. What do you think what will be the output? V positive is less than V negative, output will be 0. What do you think what will be the output here? Look, this will drive 0 ampere current, right? This will take 0 ampere current. So 4 volt, I can directly divide the potential. Basically this is 4 volt, so what will be the current here? 4 volt divided by 2R. And what will be the potential here? 4 volt divided by 2R into R, so 2 volt. Or you can directly divide the potential between R and R. So here you are having 2 volt. So at negative terminal you are having 2 volt. At positive terminal you are having 3.4 volt. So what will be the output? 1. Right? What about this? Again I can divide the potential, right? Again I can divide the potential. So here I will be getting 4 volt. So this will be your 4 volt. So here you are having 3.4 volt and at negative you are having 4 volt. So negative potential is more, so output will be 0. That's it. Okay, so this is our op-amp as a comparator. Now let's see op-amp as an inverting amplifier. So in op-amp there is a property which is known as virtual short. Virtual short. So whenever you see any circuitry in ADC and DAC, when we study data converters, so there we will see some circuitry. So whenever you see that there is some resistance connected to the negative terminal, whenever there is some resistance connected to the negative terminal, what you are going to do, V positive terminal will be equals to V negative. V positive will be equals to V negative. So whatever the potential you are having here, the same potential will go here. Okay. Now you need to find the value of V naught. Did you understand this point? V positive was here, the same potential will go there. If it was 0, then 0 would go there. If it is V in will go there. Whatever you are having at V positive, the same will go to V negative. This much thing you can remember. Okay. Now you need to find V naught. So there could be two methods. One method could be you can apply nodal at V in. Nodal at V in. So how would you apply nodal? You will write down the current in this direction, V in by R1. Then what will be the current in this direction? Input of op-amp. Input of op-amp will drive 0 ampere current. Now what will be the current in this direction? V in minus V naught by R. V in minus V naught by R2 is equals to 0. V in minus 0 by R1. V in minus V naught by R2 plus 0 is equals to 0. This side 0 ampere current. So this is the current which I have written. V in minus V naught by R2. So from here if you solve, what you are going to get? V naught is equals to 1 plus R2 by, or I should solve it only, because if you are not having practice, so you would be messing it up. So 1 by R1 plus 1 by R2 is equals to V naught by R2. So what you need to find? V naught I need to find. So V naught would be coming out to be, this is what I can do. R2 will go here. So R2 plus R1 upon R1 R2 into V in. So this R2 and this R2 is getting cancelled. So what you are getting? 1 plus R2 by R1 into V in. Okay. So this is your V naught, which you can remember. 1 plus R2 by R1 into V in. Or what could be the other method? What is the current in this direction? V in by R1. Right? This current is V in by R1. Now the same current will be flowing through this resistance as well. The same current will be flowing through this resistance as well. V in by R1 will be flowing through this resistance only, because this will drive 0 ampere current. So the complete current will be flowing through this resistance R2. Right? So if this current is flowing through R2, if this current V in by R1 is flowing through R2, then what will be the potential drop here? That potential drop will be V in by R1 into R2. So what will be your V naught? V naught will be V in plus this potential drop, which is V in by R1 into R2. Did you understand this point? V in by R1 current is flowing here. The same current is flowing through R2. So what will be the voltage drop in this direction? That would be V in by R1 into R2. So if I need to write down V naught, what that would be? V in plus V in by R1 into R2 would be equals to my V naught. So what I am getting at V naught? 1 plus R2 by R1 into V in. So this would be my V naught. Okay. So this is known as non-inverting amplifier, but you do not need to remember the name. You just need to know the analysis. If you are not comfortable with this, then do this analysis. If you are comfortable with this, then do this analysis. Better solve with the current. That V in by R1 current is there. The same current is flowing through R2. So what is the potential drop? So what will be my V naught? This potential V in plus this potential is equals to V naught. There you go. Op-amp as inverting amp, you do not need to remember the name. Okay. So what did I tell you? Whatever the potential you are having at V positive, the same potential will be copied at V negative. So 0 will be copied here. This is 0, this is also 0. So what is the current here? V in by R1. Input of op-amp will drive 0 ampere current. Input of op-amp will drive 0 ampere current. So the complete current will be flowing through this. Let's just say I call this current as IF. So what is my IF? IF is V in by R1. And what is my V naught? Can you tell me what is my V naught? My V naught is minus IF into R2. Do you agree to this point? IF current is flowing in this direction. So what will be the voltage drop it will give? That is IF into R2. This will be the voltage drop. So what will be the V naught? V naught will be 0 minus IF into R2. V naught will be 0 minus IF into R2. And what is your IF? IF is minus V in by R1. Minus V in by R1. So what will be your V naught by V in? That would be minus R2 by R1. or if I need to write V naught only, so V naught will be minus R2 by R1 into V in. Did you understand this point? V in by R1, so that is flowing through R2, so that current is IF, so V naught is minus IF into R2, because from this potential is 0 minus IF into R2, that is V naught. Okay, now V naught is minus IF is V in by R1, this is your V naught. Okay, let's solve this question. You need to find the value of V naught. How would you do it? Whatever the potential you are having here at positive terminal, the same potential will be copied here. Now if I say the current here is IF, so what will be your IF current? Can you write down the IF current? IF current will be a addition of this current I1 plus this current I2 plus this current I3. Now if this potential is 0, that means all these potentials are 0. What is your I1? I1 is V1 by R. What is your I2? V2 by 2R. And what is your I3? V3 by 4R. Now all these currents are added, will be flowing here, and input of op-amp will drive 0 ampere current, so the complete current will be flowing through IF only. So IF is simply I1 plus I2 plus I3. Is that clear to you? And what else do you know? If this potential is 0, then what will be the voltage drop here? IF into RF. If this potential is 0 and current is flowing in this direction, so potential drop will be IF into RF. So what will be your V naught? V naught will simply be minus IF into RF. V naught will be minus IF into RF. And what is your IF? IF is the addition of all these three current. And what is all these currents are? V1 by R plus V2 by 2R plus V3 by 4R into RF. That's it. This is your output. So you don't need to mug up anything. You just need to know the method. What we are doing? This 0 we are copying here. Then we are writing down the current V1 by R, V2 by 2R, V3 by 4R. All these currents are added and flowing through RF. What is your V naught? V naught is addition of all these currents into RF and then negative sign, because current is flowing in this direction. So V naught is minus IF into RF. So minus IF into RF. And what is your IF? V1 by R, V2 by 2R and V3 by 4R. There you go. This is your V naught. Okay. Let's see the last circuitry, which is op-amp as an integrator. You are using op-amp as an integrator. So this is your V naught. So forget about integrator. You don't know what is integrator, anything. Here you are having 5 volt. What did I tell you? Whatever you are having at the positive, the same you copy here. So what did you understand? Constant 5 by R current is flowing here. Now the same 5 by R current is flowing through this capacitor as well. So this is your capacitor, which is being charged by 5 by R current, and other end of this capacitor is connected to V naught. If I say this is my VC potential, and this node is what? This node is connected to 0. So what will be your V naught? V naught will be minus VCT. Can I write down this if I call it VCT? So what will be your V naught? V naught will be, this is 0, this is VCT. So V naught will be minus VCT. And how do you write down VC now? So capacitor is being fed with the constant current, which is 5 by R. So can I write down the VCT potential? The direction of current is this. So it will charge the capacitor in this direction only. It will give the charge. It will provide the charge to the capacitor in this direction only. So what will be the VCT equation? I hope you know it. 1 by C integration I dot dt. So what is the current? 5 by R into dt. Let us say it is starting from 0 only. Although it feels like that it is starting from minus infinity, so I should have made a step function here. So now I can see that it is starting from t equals to 0. So here I can put the limit from t equals to 0 to t. So what you can do, 5 by RC you can take common, and dt from 0 to t will be t. So 5 by RC into t. This is your VCT. What will be your V naught? If I say what will be your V naught? V naught will be minus 5 by RC into t. So what did you understand? The capacitor is getting charged in this direction. So your V naught is going down in negative. In that manner it is going down. Okay. This is the graph of your V naught. V naught T. Now instead of this 5-fold, if there was minus 5-fold, instead of this 5-fold, if there was minus 5-fold, then what would be the scene? The 5 by R current would have been flowing here. A 5 by R current would have been flowing here because this is 0, this is minus 5. So 5 by R current would have been flowing here. If the 5 by R current would have been flowing here, that means capacitor would be charged in this direction. Capacitor would be charged in this direction. If the current is flowing, then V naught will be going up. So V naught will be going up like this, right? Because if the capacitor is getting charged in this direction, so if I call this as VCT, then my V naught T would have been VCT only, right? So whatever the charge it is getting, it would be increasing only. We will see this example, no need to worry about that. Okay, all clear? Let's solve this question. So this is the question given, T equals to RC is given, this waveform is given, you need to draw the V naught waveform. So how will you draw it? First 5-volt will come. Here what will come? First 5-volt will come. If 5-volt comes, then what will be the current here? 5 by R. This is grounded, this is grounded. 5 by R current is flowing here. So the same 5 by R current will be flowing here as well. So capacitor will be getting charge in this direction. Capacitor will be getting charge in this direction. So what will be your V naught T equation? Or I can say VCT equation. First I will write down VCT equation, then I know that my VCT is simply equals to minus V naught T. So what will be your VCT equation? So that would be the same as the previous one, 5 by RC into T. And what will be your V naught T? So that would be minus 5 by RC into T. So now I need to draw the V naught waveform. So 5 by RC into T minus 5 by RC into T. But till what point it will go? Till what point it will go? V naught at T by 2. After T by 2 input is changing. So till T by 2 only I need to find. So till T by 2, what I will get? This much potential, right? So minus 5 by RC into T is equals to RC is given. So that means you are going to get till minus 2.5. So this potential is minus 2.5. So if this potential is minus 2.5, then what did you understand? The capacitor would have been charged to 2.5 voltage. Say yes or no? Whatever the charge capacitor is getting, output is just negative of that. Whatever the charge capacitor is getting, output is just negative of that. So capacitor is developing 2.5 voltage, and in the negative direction we are having from 0 to minus 2.5. If I draw the capacitor waveform, how it will be going? In this manner, right? This is how the potential is developing. 2.5 voltage have developed. So output would have gone to 0 to minus 2.5 volt till the time T by 2. Right? Now what will happen? Now input will be changed. That will be changed to minus 5. Input is changed to minus 5. And this capacitor has charged to 2.5 volt already. 2.5 volt already, minus 5 volt here. So this will drive 5 by R current here. So the 5 by R current will be flowing in this direction. Now this 5 by R current will be charging the capacitor, but in the opposite direction. In this direction it will be charging. The 5 by R current will be charging the capacitor in the opposite direction, right? So now what will happen? V naught will go up. Initially V naught was going down. This was minus 2.5. Now V naught will go up. This was the scene for V naught. Now this current is charging the capacitor in the opposite direction. So capacitor would have developed 2.5 volt in this direction now. Now it will develop the potential in the opposite direction, in this direction, right? Yeah, so what I was saying, the capacitor will be charging in this direction now. So if I need to write down the V naught T equation, how will I write down? Initially it was, or let's write down VCT equation. And what I am calling VCT, that is this. So my VCT is 2.5 volt. Now the capacitor is charging in opposite direction. Capacitor is charging in this direction. So what I will write? Negative sign. Because capacitor is getting charged in opposite direction. VCT I am writing in this manner. Plus 2 minus. But capacitor is charging in this direction. So what I will write? Minus sign here. 1 by C integration, what is the current? 5 by RC only into dt. Sorry, current is 5 by R, sorry, not 5 by RC into dt. And what is the time? From t by 2 to any particular time t. Although it is from t by 2 to t, but any particular time, I just want to write down the expression. So this is how I will write down. So 2.5 already developed minus 5 by RC into t minus t by 2. So this will be your VCT. And what is your V naught? Just negative of that. So if I draw V naught, what will happen? So till this point everything is clear. Already we have reached till this point. This is your minus 2.5 volt. So if I write down the V naught T equation, so that is just the negative of this VCT, that would be minus 2.5 volt. Now it will develop some voltage 5 by RC into T minus T by 2. So at what will be your V naught potential at a T, at time T? So what you put? Just put T here. So what you are going to get? Minus 2.5 volt plus 5 by RC into T minus T by 2 into T by 2. And what is your T? T is equals to RC only. So what you are going to get? 2.5 volt plus T is equals to RC. RC getting cancelled. 2.5 volt. What you are going to get? 0 volt. So from minus 2.5 volt to you are going to 0 volt. So what actually happened here? Basically your capacitor was getting some voltage in this direction first. So your capacitor got from 0 to 2.5 voltage in this direction. Then when minus 5 was applied, it got 0 to 2.5 volt only, but in the opposite direction. So that plus 2.5 and minus 2.5 killed each other and you got 0 voltage. And V naught is simply the negative of VCT. So basically it was getting 2.5 volt. So I am saying minus 2.5 volt in negative. From 0 to minus 2.5 volt for V naught. Now capacitor is getting 2.5 volt in this direction. That means V naught is going up. So 0 to 2.5, then again 2.5 to 0. So all these basics will be used in your data converters. Okay. So in the data converters, all these basics will be used. One more basic will be used, which is of digital only. So what do you understand by counter? So basic meaning of counter will be used. Counter could be of two type, up counter or down counter. So if I say, if I just draw a block diagram and I am saying this is your up counter, I am saying this is up counter, and then there is a clock. One clock signal will be there, and let's just say there are 3 bit of output. It could be 4 bit as well, 3 bit as well. So I am calling this as Q2, Q1. So these 3 outputs are there. So just as clock is applied, let's just say my initial condition of Q2, Q1, Q0 was 0, 0, 0. So just as clock is applied, it will go up. Up counter means it will count up. Again clock is applied. Here this was the initial condition. Just as clock was applied, you went up. Again clock is applied, you went up. Again clock is applied, you went up. So in that manner you need to go. Till what point it will go up? Till 7. Then again clock is applied, you will go to 0, 0, 0. I hope you know this much of basics because we are already studying digital electronics only. So this is your up counter. What about your down counter? Down counter will have the same circuitry only. So what I can do, I can just copy it. So what about down counter? So here it is written that it is down counter. So what will happen? Although up counter only will be used, down counter will not be used, but still I am telling. So if I say my initial condition is 1, 1, 1. So now it will count down from 7 to 6 it will go. 6 to 5 with every clock edge. With every clock edge. From 6 to 5. In that manner it will go. Until what point it will go? Till 0, 0, 0. Then again it will go to 7. So it will keep on making this cycle. Okay. So this is the basics which is required before studying data converters. Now we can start our data converters. Okay, you are going to love the session. Okay, so don't forget to put the like. Thank you very much. Let's start our data converters. Now we will be starting to study digital to analog converter, DAC we are going to study. Hi everyone, so now we are going to start studying about our new chapter, that is data converters. So two kind of converters we will see, digital to analog converter and analog to digital converter. Okay, so before starting the lecture, there is some basic prerequisite. You need to know basics of op-amp. Like you just need to know how it will behave as a comparator, how it will behave as an inverting amplifier, how it will behave as a non-inverting amplifier, and basic integration and differentiation. So that thing you need to know, basic integrator and differentiator. So basics of op-amp and counter you need to know. What a counter does, it will count up or count down. So very basics of op-amp if you know, and very basics of counter you know, then you can proceed in this particular lecture. Okay, so first let's start studying about digital to analog converter. First we will study DAC. So in short form I will call it DAC, digital to analog converter. Okay, so before starting the chapter, first let's solve a particular problem. Okay, so this is a question in front of you. It is neither related to DAC, it is nothing, just a simple analog problem. Simple problem based on op-amp. So what they are saying, there are two switches, there are two inputs B1 and B0 which are connected to switches. So this is the kind of switch. That means if B is 1, it will be connected to 1 volt. If B is 0, it will be connected to ground. Very simple thing. So if B1 is 1, it will be connected to 1 volt. If B1 is 0, it will be connected to ground. If B0 is 1, it will be connected to 1 volt. If B0 is 0, it will be connected to ground. You need to find the output voltage for all the possible configuration of or combination of B1, B0. Take B1 as MSB. Okay. So if B1, B0 is 0, 0, then what will be the output? If B1, B0 is 0, 1, what will be the output? 1, 0, what will be the output? And 1, 1, what will be the output? Okay. Very easy, very straightforward problem based on op-amp. So here there is negative feedback present. So if this is 0, this will also be 0. No doubt about that. This is a negative feedback. So because of the virtual short, this will be 0. Now if B1 and B0 both are 0, if B1 and B0 both are 0, that means both are connected to ground. If both are connected to ground, then this is also ground, this is also ground, there is 0 ampere current. This is ground, there is 0 ampere current. So here there is already 0 ampere current. So what will be the current going here? 0 ampere only. So what will be the output? 0 volt. Very simple thing. If both are connected to ground, then output will be simply 0 volt only. Right? This 0 volt is going nowhere. This 0 volt will always be there. If both are connected to ground, output will be 0 volt. Output will be 0 volt. Now if B0 is 1, that means this will be connected to 1 volt and this will be connected to ground. B0 is 1. B0 is 1. So this will be connected to 1 volt and this will be connected to ground. So let me make the circuit again here for your simplicity. This was R and lower one was 2R. Okay, simple analog problem we are solving. We did not start our chapter yet. Just a simple analog problem we are solving. So this is connected to 1 volt and this is connected to ground. And what is this resistance? This resistance is equal to 5R. Okay, so this 0 volt will be copied here. 0 minus 0, this will drive 0 ampere current. There is no use of this. Okay, so 1 minus 0 by 2R, so that would be 1 by 2R. Now that 1 by 2R current will be flowing from here. So what will be your V0? V0 will simply be minus 5R by 2R. 1 by 2R into 5R. So what that would be? Minus 2.5 volt. So here what you are going to get? Minus 2.5 volt. Okay. In the next case, if B1 is 1 and this is 0. B1 is 1 and this is 0. So this will become 0 and B1 is 1 volt. B1 is 1 volt. This is grounded. This is 0 volt. So 0, 0, this will drive 0 ampere current. How much current this will drive? 1 by R current it will drive. So this will drive 1 by R current. That 1 by R current will be flowing through this resistance. 1 by R current will be flowing through this resistance. So what will be your V0? This was the case for 0, 1. Now I am writing V0 for 1, 0. So 1 by R into 5R. That would be minus 5 volt. This is the case for 1, 0. What will be the case for 1, 1? Do you need to solve it? Case for 1, 1. Okay, we can solve it as well. This will be 0, this will be 1 by R current, this will be 1 by 2 R current, right? So what will be the current here? 3 by 2 R. This will be 0 volt, there is no doubt about that. 1 by R current it will drive, 1 by 2 R current it will drive. So 1 plus half, what that would be? 3 by 2 R. So what will be your V naught? V naught will be 3 by 2 R into 5 R, and certainly minus sign will be there. So what you are getting? Minus 7.5 volt. This is the condition for 1 So here you are getting minus 7.5 volt. Or you could have simply thought that for 0 it was minus 2.5, for 10 it was minus 5 volt. For 1 what we can do? We can apply superposition theorem. First I consider only this one, and this is grounded. So only this guy is in action and this is grounded. So only 1 volt is in action, this is grounded. Then what will be your output? Minus 5 volt. Right? Only 1 volt is in action and this is ground. So minus 5 volt. Then plus this 1 volt is in action and this is ground. So what will be your output? Minus 2.5 volt. So what will be the total output? Minus 7.5 volt. Or otherwise you can simply write down these equations and you get your answer. What you are understanding here? Here I am getting 0 volt output. Here I am getting minus 2.5 volt. Can I write it down in this manner? Minus 2.5 into 1. Can I write down in this manner? Minus 2.5 into 2. Can I write down in this manner? Minus 2.5 into 3 volt. And can I write down the initial one in this manner? Minus 2.5 into 0 volt. What is this? This is the decimal equivalent of input. Say yes or no. What was the decimal equivalent of this? 0, 1, 2, 3. So this is the decimal equivalent. So what is your output you are getting? There is some constant value, negative sign is there, forget about the negative sign. There is some constant value into that decimal equivalent. And that constant value we call as R. So this is known as resolution. This is the decimal equivalent of input. So did you understand why did we take this example? What I am doing, at the input I am applying a digital word, or you can say bit stream. I applied 0 0, 0 1, 1 0 and 1 1, and at the output I am getting an analog value. These all are analog values, right? 0, minus 2.5, minus 5 volt and minus 7.5 volt, all are analog value. So what we did here, we applied a bit stream, or you can say this is known as digital word. Okay, we call it digital word. A bit stream we applied, and in the output we are getting an analog value. So this is known as DAC. So this example we solved, it was a DAC only, but we solved it using a simple concept of analog electronics, but it was a DAC only. What we are doing, we are applying a digital bit stream, or you can say digital word, and at the output we are getting analog values. So this is known as DAC. So let us represent this in a box. So basically this will be there in a box. This will be my input. I will be applying 0 0 0 1 1 0 1 1, and based on that I will be receiving my output. So this is how generally a DAC is shown. Bit stream input are there. What I will call it, bit stream, or generally it is known as or digital word. Okay, and this is what, this is your analog output. This will have a decimal equivalent. So what is your D? Decimal equivalent of applied input digital word. Okay, and this is your analog output. So your analog output will be proportional to the applied digital stream. Okay, decimal equivalent of applied digital word. So your analog output will be proportional to what? Decimal equivalent of applied digital word. And when you remove this proportionality sign, you get a value R. Okay, so this is R is proportionality constant and which is known as resolution. Now what is this VREF? So any DAC you design, there will be a VREF voltage. What is that VREF voltage? That maximum output you can receive, or I can write maximum value of analog output. Okay, maximum value of analog output. So when a DAC is given to you, what will be the data given to you? That how many bits you can apply? Okay, it is your n bit DAC. What I will call n bit DAC, n bit digital to analog converter. I can apply n number of bits. What is the VREF voltage? That what is the maximum output voltage you can receive, and what is the resolution? What is the resolution of it? Okay, so let's understand this formula more. This is our formula. V naught is equals to R into D. Okay, now let's just say this is my DAC. Now at the input of the DAC, I can apply 2 bit, 3 bit, 4 bit, depending on the number of bits it can take. Let's just say it can take only 2 bits. It can take only 2 bits. So what is the maximum value you can have with 2 bits? Maximum decimal value 1 1. And what is that equivalent to? 3. If there was 3 bits, 1 1 1, what is the maximum value you can have? 7. If there were 4 bits, what is the maximum value you can have? 15. If there are n bits, what is the maximum value you can have? 2 to the power n minus 1. Say yes or no? Do you agree to my point? And tell me one thing. I am taking this DAC only where I am applying n number of bits. N bits I am applying. Okay. So that will have a maximum decimal equivalent of 2 to the power n minus 1. Now what is my V naught? V naught is R into D. V naught is equals to R into D. Now if this is maximum, tell me one thing. If the decimal equivalent is 0, what will be your, if decimal equivalent is 0, what will be your output? 0. If decimal equivalent is 1, what will be your output? R. If decimal equivalent is 2, what will be your output? 2R. Right? If decimal equivalent is having its maximum value, let's just say if this was 3 bit DAC, so what is the maximum value it can have? 7, right? So V naught will be 7R. And what this will be equals to? Tell me. This is the maximum possible output, and that is known as VREF. Say yes or no. So if my all bit streams are 1, if my all input bits are 1, that means my V naught is equals to V naught max. And what do you mean by V naught max? Maximum possible output, maximum possible of analog output, maximum possible value of analog output, and that is known as what? That is known as VREF. And what will be my decimal equivalent? What will be my decimal equivalent? If all bit streams are 1, what will be the decimal equivalent? 2 to the power n minus 1. Say yes or no. Do you get this point? So only one formula I will keep in mind, that my output voltage will be equals to resolution into the decimal equivalent. Now, if my output voltage is maximum, that means certainly I should have applied the maximum value of input. What will be the maximum value of input? 2 to the power n minus 1. This will be the maximum value of input. So from here what you are getting, that my resolution is VREF divided by 2 to the power n minus 1. Will you mug it up? No. I will only remember this thing. That's it. All the question of DAC will be solved by only this formula. All the questions of DAC. Only one formula is there. V naught equals to R into D. You do not need to remember anything. Okay. V naught is equals to R into D. The output will be depending on the decimal equivalent of the input into the resolution. That's it. Right? Now, if my output voltage is maximum, that means certainly at the input maximum possible combination would have been applied. And what is the maximum possible combination? 1 1 1 1 1. And what do you mean by 1 1 1 1 1? What will be the decimal equivalent? That would be 2 to the power n minus 1. So VREF is equals to R into 2 to the power n minus 1. So from there we are getting this formula. People will mug it up and will get confused lot of times. But we are not going to mug it up. We have the aptitude clear that how this formula came. Let's see more interesting thing about it. Before that, let's solve a problem. So with respect to the applied input B1 B0, you need to draw the V0 waveform. with respect to the applied input. It is having a resolution of R. Okay, so what is your V naught? V naught is equals to R into D, that we already know. V naught is equals to R into D. So now inputs can have value 0, 0, 0, 1, 1, 0, 1, 1, 1. Take B1 as a MSB. So what will be the decimal equivalent here? This will be 0, this will be 1, this will be 2, this will be 3. What will be your V naught? I will just draw a line here. This is the decimal equivalent. What will be your V naught? V naught will be R into decimal equivalent 0, R into decimal equivalent, R into decimal equivalent, R into decimal equivalent, and R into decimal equivalent. Now you need to draw your V naught. So how will you draw the V naught? Draw V naught waveform with respect to the applied input B1 V naught. So if I apply 0, 0, what I am getting? 0 only. If I apply 0, 1, look, if I applied 0, 0, I am getting 0. Now in between there is no input. Directly the input is 0, 1. So till that point my output will remain at 0. Now just as I applied input 0, 1, my output went to R. Now when I applied input 1, 0, my output went to 2R. And when I applied input 1, 1, my output went to 3R. So 0 to R, R to 3R. So this is how my output would look like. Okay, let's make it better on the next page. So this is how we will make it. Okay, so 0, 0, I am getting R. Sorry, for 0, 0, I am getting 0 output. Then for 0, 1, I am getting R output. For 1, 0, I am getting 2R output. And for 1, 1, I am getting 3R output. Okay, so 0 output, R output, 2R output, and 3R output. No issue about anything, right? Now how many number of steps are there? Let's just say this is a ladder. This is a ladder, or you can say this is a staircase. So to reach here, how many steps you need to walk? 1, 2, and 3. So number of steps are 3. What is the step size? In the output you can have 0, R, 2R, and 3R. Do you remember the delay problem that we solved in multiplexer? In multiplexer we solved a problem based on delay. There I asked you what is the step size. So what did you do there? You found out your output, that this will be, sir, my output. And what will be the step size? This is R ahead from it. This is R ahead from it. And this is R ahead from it. So what is the step size? R. Or you can say that, sir, to go from this staircase to this staircase, to go from this stair to this stair, I need to go by the length of R, or you can say height of R. So I need to reach the height of R, then another height of R, then another height of R, and then another height of R. So it is having a constant step size. Okay, it is having a constant step size which is equals to R. And what is your R? R is resolution only. So if they are asking resolution or they are asking step size, both are same thing. Resolution and step size are same thing. So this you will remember. So this is just the other name of resolution. Okay. Now for input B1 B naught equals to 0 1. When input is 0 1, what will be your output? When input is 0 1, your output will be R into decimal equivalent. What is the decimal equivalent? That is 1 only. So your V naught will be R only, right? When input is 0 1. So what did you understand by that? When only LSB bit is high, analog output of DAC is equals to resolution. Okay, so these kind of language will be used in the problems, that they will say that only LSB bit is high and this is your analog output. So what is given there? Resolution is given. That only LSB bit is high. That means if only LSB bit is high, what will be the decimal equivalent? That would be 1. If there were, let's just say if there was 5 bits, B4, B3, B2, B1 and B0. My DAC was of 5 bits. Okay, this was my DAC which was of 5 bits. And only LSB bit was high. Only LSB bit was high. So if only LSB bit was high, then what will be the decimal equivalent? That would be 1. So what will be your output? R into decimal equivalent of that. So that would be equals to R only. So they can mention that in the input only LSB bit is active the output is 5-fold. So from that, what you will understand, the resolution of DAC is 5-fold. Okay, well and good, right? Okay, tell me difference between two successive analog output. What is that? That is also resolution. R to 2R, 2R to 3R, that is also resolution. So this is also resolution. So this can also be written that difference between two successive analog output is 5-fold. So what did you understand? That your resolution is 5-fold. Now what if this line is written minimum detectable change in analog output? Look, if I ask you how much change is there from here to here, from R to 3R, what is the change? You will say 2R. But if I ask you what is the minimum detectable change? Minimum detectable change is this, from 0 to R, from R to 2R, from 2R to 3R. So what is the minimum detectable change? That is equals to R only. So that is also resolution. So these all are the other name of resolution. You can call it step size, or you can say that only LSB bit is active, then what is your analog output, or you can say difference between two successive analog outputs, or you can say minimum detectable change in the analog output. Okay, so these will be the different names. If your concept is clear, then you will be not getting confused. You will get to know that only the value of resolution is given, nothing else, right? So I hope the concepts are being cleared. These kind, like in DAC, people get confused in this topic because they mug up a lot of formulas, but we are not going to mug up any formula. We are going with pure concept. Okay, so let's see one more concept, very simple concept. Okay, so what will be your resolution? Resolution will be Vref by 2 to the power n minus 1. We are not going to mug up this formula. How we will derive it? That V naught is equals to R into D. One thing I know, that if my output voltage is maximum, that means certainly the input would have been the maximum decimal value, and that would be 2 to the power n minus 1. So my resolution will be Vref by 2 to the power n minus 1. Okay, can I call it as Vref by number of steps as well? Vref by number of steps. Number of steps was 3 only. Okay, so not that important formula, but they can write down the number of steps. So 2 to the power n minus 1 will be the number of steps only. Or this is very important. Resolution is Vref by maximum possible decimal equivalent of input, right? V naught is equals to R into D. If this is maximum, then certainly this is also maximum, right? Because this is a constant value. Resolution is a constant value. It can change with respect to temperature. So these kind of problems also we will see. But as of now, you consider resolution is a constant value. For a particular DAC, resolution is a constant value. If this is maximum, that means certainly this is also maximum. What is the maximum value of this? That is Vref. Or what you can call this? Maximum decimal equivalent of input. Maximum decimal equivalent of input. So Vref by maximum possible equivalent of input is equals to resolution. Okay. So what is your V naught max? Or you can say what is your Vref? That is equals to resolution into maximum decimal equivalent of input. So can you remember this thing? Very simple thing. V naught is equals to R into D. If I know that my output is maximum, that means certainly the input must have been also maximum. The decimal equivalent of input must have been also maximum. So maximum possible decimal equivalent of input. Well and good. Now there is one more term, percentage resolution. So once you see the specification of a DAC, so their resolution will never be defined in this form. It will be defined in percentage resolution. Okay, it will always be defined in percentage resolution. So it can be asked sometime. So what is percentage resolution? It is resolution divided by Vref. It is nothing but percentage resolution is resolution divided by Vref, or this Vref is known as full scale value as well. This is your Fs means full scale value. Full scale value. This is the other name. Full scale value. So Vref, or I can write V full scale. So what I will get here? What is my resolution? Resolution is Vref divided by 2 to the power n minus 1 into 100%. Sorry, I always forget this point, into 100%, because this is in percentage now. So into 100%. So what I am gonna get? What is my resolution? Resolution is Vref divided by 2 to the power n minus 1 into Vref into 100%. So what is the answer? 100% divided by 2 to the power n minus 1, right? Or what you will write? Percentage resolution. Can I write in this manner? That is equals to 100 divided by maximum possible decimal equivalent of input. This is maximum possible decimal equivalent of input. So we are never going to mug up this formula. We will just mug up, what we will mug up? 100 by maximum possible decimal equivalent of input. There you go. Okay. So always you will remember this thing only. What is the meaning of percentage resolution? 100 by maximum possible decimal equivalent of input. Okay. And if you need to remember the formula of resolution, what you will do? You will write down V naught is equals to R into D. So if this is maximum, this will also be maximum. So what is your maximum output? Maximum output can be taken as Vref or V full scale. And what is your D maximum? That means maximum possible value of the input. Maximum possible, or you can say maximum possible decimal equivalent of the input. Okay, well and good. Why I am doing so? Because what if at the DAC, in the DAC, what if in the DAC your applied input is a BCD code? Do you remember the BCD code? Let's revise BCD code yet again, because people might not be remembering it. You need to represent 9 in BCD code. How will you represent? 1001. You need to represent 6 in BCD code. How will you represent? 110. Is that correct? No. You will always represent in 4 bits. You need to represent 11 in BCD code. Will you represent in this manner? No. In BCD code, each number will be defined by 4 bits. So how will you represent 1? In that manner. How will you represent this one? In that manner. So this is the BCD code, right? Are you getting this point? So now tell me one thing. For a 4-bit BCD input, what will be the maximum possible decimal equivalent? That means using 4-bit, what is the maximum possible decimal equivalent you can get when you are using BCD code? Using 4 bits. Can you get 10? No, using 4 bits you can only get 9, because 10 will be represented in 8 bits, not in 4 bits. So maximum possible decimal equivalent using 4 bits will be 9 only. Tell me what will be the maximum possible equivalent using 8 bits. Can you represent 100 in 8 bits? To represent 100 in BCD code, how many bits required? 12. To represent 100, 12 will be required, because 1 will be represented as this, 0 will be represented as this, another 0 will be represented as this. So this will be the BCD code of 100. So what is the maximum value you can get using 8 bits? 99. This can be represented in 8 bits. 1001, 1001. So 99. Using 12 bit, what that would be? 999, right? Because for 1000, you need 4 plus 4 plus 4 plus 4, 16 bit. For 16 bit, what will be the maximum value? 4 times 9. Say yes or no. I hope you remember BCD code. What was the BCD code? Here we have revised it. 10 cannot be represented by this. Okay. This is unused case in case of BCD. This is the unused case. All these are unused case. This is also unused. This is also unused. This is also unused. This is also unused. Whole are unused. Okay. So these are unused case which will never come in BCD. So they may say that I have a DAC, I have a digital to analog converter which is having 8 bit of BCD input. What will be its resolution? What do you think? What will be the resolution? For finding resolution, we remember only one formula. V naught is equals to R into D. Now, if this is maximum, that means if this is Vref. So now you will write the maximum decimal value of input. Maximum decimal equivalent of input. And if there are 8-bit BCD code, at the input you are having 8-bit BCD code. So what is the maximum value you can get? 99, right? So your resolution will be Vref by 99. And believe me, like a lot of students get confused in this simple concept. So that's why I told you, only remember one formula, V naught is equals to R into D. If V naught is maximum, that means decimal equivalent is maximum. So you just need to write what could be the maximum decimal equivalent of input. That's it. This is your complete concept of DAC. The DAC is completed. Okay. It's not completed. We will take, I guess, more 1.5 hours to complete it. But this is the fundamental concept which we will go with. Okay. Now for 10 bit, For 10 bit, what will be the maximum value of, what will be the maximum decimal equivalent of input in case of BCD? These all are in case of BCD. So someone will say that, sir, for 10 bit, that means I need to use 10 bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here I can get 9. Here I can get 9. And here I can get double 1. So someone will say that, sir, 3, 9, 9. So this will be the maximum equivalent. The thing is, no BCD code can be represented using 10 bit. So this question itself is needless. I told you one thing, BCD code can have either 4 bit or 8 bit or 12 bit or 16 bit or 20 or 24, 28. There is no concept of 10 bits. No BCD code can be represented in 10 bits or 11 bits. You can represent in 4 bits. That's why I told you, if you need to represent 2 in BCD code, how will you represent? 1 0? No. 00 10. This is the correct BCD code. 10 is not the correct BCD code. 0010 is the correct BCD code. Okay. So this is how you represent. So this question itself is needless. So it will never happen that they will say that this is a 10-bit DAC. You are having 10-bit DAC and your input is BCD. They will never say that. Your input will be binary only. Okay. And if nothing is mentioned in the question, if they are not mentioning whether the input is BCD or binary, then you will by default take binary input. Okay. So I will write input of DAC by default is binary. If the input is BCD, then they will specifically mention that my input is BCD. Or if the input is gray code, then they will specifically mention that my input is gray code. So if they are not mentioning specifically, then you will take only binary input. Okay. So there 11 can come, 12 can come. So with 4 bits, what is the maximum value you can go? 15 in case of binary. But in case of BCD with 4 bits, you can go 9 only. Okay. So that's the difference. Right. Now let's solve this question. Binary input is there. Number of bits are 6. B5 is the MSB. So B0 will be the LSB. Input is 110011. Sorry, 110010. Output is 25 volt. Find the full scale value. This is what you need to find. So one thing I know, only one formula I know, that is V0 is equals to R into D. I know that my output is 25 volt. For which value of input? For this decimal equivalent. So what will be the decimal equivalent of this? 1, 2, 4, 8, 16, 32. So what that would be? 50. So what I am getting here, my resolution is 0.5 volt. So this is the one thing I got. Now what they are asking, full scale value. V full scale, what that would be? R into maximum decimal equivalent. D maximum, right? So V full scale will be equals to R is 0.5. What could be the maximum value? 1, 1, 1, 1, 1, 1. This is the maximum value, right? Maximum value of input. Or you directly remember what that would be? 2 to the power n minus 1. So how many bits are there? 6 bits are there. Right? So what will be 2 to the power 6? That would be 64. So 63 into 0.5 into 63. With 6 bits you can go up to 63, right? With 2 bit you can go up to 3. Then 7. Right? Then 15. Then 31. And then 63. 2, 3, 4, 5, 6. 6 bit you can go up to 63. Okay, or you can remember the formula 2 to the power 6 minus 1. Okay. So what that would be? What you will get? 32.5 volt. No, 31.5 volt. Okay, just divide by 2. So this is the answer. So just don't use any formula. You just only know one thing. V0 is equals to R into D. That's it. From there we will solve all the problems. Let's see this question. 8-bit DAC is there, but BCD input is there. Input is BCD. Vref is given, that is 10 volt. Find the resolution. What will be the resolution? Resolution. So we don't remember anything. We just remember one thing. V0 is equals to R into D. So if I put the maximum value, maximum value of output, this is the maximum value of output. That means certainly I need to put the maximum value of input as well. So what will be the maximum value of input? In case of 8-bit DAC, in case of 8-bit BCD input, that would be 99. Right? I told you one thing, if 8 bits are there, then 99. So what will be your resolution? 10 by 99. Okay, this is my resolution. And what will be the percentage resolution? Percentage resolution. I told you one thing, 100 by maximum value of input, that is 99. So approximately equals to 1%. Okay, 100 by 99%. 100 by maximum value of the maximum decimal equivalent of input. What is the maximum decimal equivalent of input? 99 only. Okay, you are not going to write 2 to the power 8 minus 1 here. Now, 2 to the power 8 minus 1 you are not going to write. What will be 2 to the power 8 minus 1? That would be 255. So 255 will not be there. Here there will be 99. Why 99? Because maximum decimal equivalent of input could be 99. Why is that so? Because input is BCD. Okay. So these kind of questions you need to solve. Let's go to the next one. 8-bit DAC has a full scale output of 2 milliampere. Now you will say that, sir, you said that output will be in voltage. It could be in current as well. Okay. So output is full scale output is 2 milliampere. Now there is this new term, that is full scale error is plus minus 0.5%. So this is something new. So that we will see. Now range of possible output for the given input. What I know, output is equals to R into decimal equivalent. That thing I know, right? Okay. Full scale value is 2 milliampere. Full scale value is 2 milliampere into, if this is the full scale value, that means decimal equivalent must have been maximum only. If this is the full scale value, that means decimal equivalent must have been maximum only. If this is maximum, then certainly this will also be maximum. And how many bits are there? 3, 6, 8 bits are there. That would be 2 to the power 8 minus 1. Maximum value of input will be 2 to the power 8 minus 1 because 8 bits are there. 8 bits are there. So what will be your R? R will be 2 milliampere divided by 255. So it's not necessary that output will be voltage only. It could be current as well. It could be any electrical quantity, voltage or current. Okay. Any linear electrical quantity, I should say, linear electrical quantity, voltage or current. So R is 2 milliampere divided by 255. So this is your resolution. Now what they are asking? Range of possible output. So what will be your possible output? Forget about the error. Okay. So what should be your output? If you forget about the error, what will be your output? Resolution into decimal equivalent of this. What will be the decimal equivalent of this? 1, 2, 4, 8, 16, 32. 1, 2, 4, 8, 16, 32, 64 and 164 का डबल कितना होता है यार, यही मैं भूल गया हूँ. 128, राइट. मेमोरी एकदम खराब हो गई अभी. 1248. Now what that would be? 138. So this would be 138. Okay. So this should be your output. Let's calculate this. Then we will see what we are getting. Then we will take the action and we will take error in action. But first let's calculate this. Two milliampere divided by 255 into 138. So I'm getting 1.08235 milliampere, or I can write 1082.35 microampere. Okay. Now what do we mean by this error? Full scale error of plus minus 0.5%. That means the error can be plus minus 0.5% of full scale value. Okay, error can be plus minus 0.5% of full scale value. So what is the full scale value? That is 2 milliampere. So 0.5% of 2 milliampere. Okay, plus minus as well. So what you are getting? This would be 1 by 100. 1 by 100 means 10 microampere. So this could be your error, plus minus 10. So what will be your output? Output will be 1082.35 plus minus 10 microampere. So did you understand the meaning of this line? What is the meaning of this line? Full scale error of plus minus 0.5% means plus minus 0.5% of the full scale value. Error could be plus minus 0.5% of the full scale value. That is 2 milliampere. So plus minus 0.5% of 2 milliampere would be 10 microampere. So this could be the range. So what could be the range? 1072.35 microampere to minus 10, then plus 10. So in this range you will receive your output. Okay, so that's the solution. Let's see another question. For the input of, if the input of the DAC is changed from 1010 to 1101, then output changes by 18 millivolt. What will be the step size, percentage resolution, and full scale reading? So what do we know? We know only one thing about DAC. Now, let's just say my output was V naught when my decimal equivalent was 1010. What is my decimal equivalent here? 1010. 10, right? 1248, it is 10. So my output was V naught. At that time, my output was V naught. Now, if my decimal equivalent is 1101, what is that? 13. So if my decimal equivalent is 13, my output got changed by 18 millivolts. So output must have been increased by 18 millivolt, right? Say yes or no? Did you understand this point? When decimal equivalent was 10, then output was 10R. Output was 10R. When decimal equivalent is 13, then output would be 13R. And 13R is equals to increased by 18 millivolt. So subtract equation 1 from 2. What you are going to get? 18 millivolt is equals to 3R. So from there, what is the resolution you are getting? 6 millivolt. So this is your resolution, and that is equals to your step size. So this is your step size or resolution, you can say. What will be the percentage resolution? So for percentage resolution, you do not need to care about anything. You just need to know what will be the maximum value of input. So what will be the maximum value of input? That would be, so I am going to write 100% divided by maximum possible value of input. That would be 1111 maximum value. And what that would be? 15. So 100 by 15, what you are going to get? 100 by 15, 6.67%. So this is your percentage resolution. What about full scale reading? Full scale reading. So we know only one thing. What is that? V naught is equals to R into D. If I need full scale, that means what do I need to take? This will be constant into maximum value of maximum decimal equivalent of input. What is that? 15. Right? Maximum decimal equivalent of input, that is 15. So what will be your V full scale? 90 millivolt. That is the V full scale value, 90 millivolt. How did we get it? V naught equals to R into D. Resolution is my 6 millivolt. Decimal equivalent, maximum possible decimal equivalent. What that would be? 15 only, right? So 6 into 15, 90 millivolt. Let's see the next question. So very easy questions are there. If you just mug up the formula, then it will be difficult for you. But if you understand the concept, it will be easy. What they are saying? For a n bit of DAC, percentage resolution is given. You need to find the value of n. Percentage resolution is given. So 0.4 is equals to what? 100 divided by maximum value of input. What would be the maximum value of input? 2 to the power n minus 1. That's it. Percentage resolution is 100 divided by maximum value of input. 100 divided by maximum value of input. What would be the maximum value of input for n bit of DAC? 2 to the power n minus 1. So 2 to the power n minus 1 divided by 0.4. So from here, what you are going to get? 250. So 2 to the power n is equals to 251. So n, what you are going to get? You would require 8 bits, right? To get to 251. By using 7 bits, where I can go? 127. 1 1 1 1 1 1 1 1 3 3 6 3 3 6 7. So this will be equivalent to 127. If I need 251, then I would need 8 bits. Because with 8 bits you can go n equals to 7, n equals to 7, you can go till 127. N equals to 8, you can go till 251. N equals to 9, you can go till 511. N equals to 10, you can go with 1023. Right? Okay. So n equals to 8 is the answer. Let's see the next one. So there is a clock. There is a clock here. 3-bit up counter is there. This is a 3-bit DAC. This is your MSB, this is your LSB, and this is your output. Did you understand this particular diagram? Clock is there, counter is there. The output of counter, this is the output of counter, could be Q2 and Q0, is fed to the input of DAC, and we are receiving a final output V0. Draw output waveform with respect to time. With respect to time, we need to draw the output waveform. Okay. So initial value they are not giving, so we will take initial value as 0 only. Initial value of counter. Initial value of counter we will take as 0. So when clock is not there, or better I should write time as well. Clock, time, Q0, not Q0, Q2, Q1, Q0 value, and then I will write down the decimal equivalent I can write down, and then I can write down the output voltage. So when 0 time was there, 0 second was there, everything was 0, 0, 0, decimal equivalent was 0. So V0 is equals to R into D, right? It will have a resolution of R, that should be mentioned. So output will be 0. Now just as the positive edge comes, at t equals to 0 only positive edge will come, just as the positive edge comes. So till 5 seconds, from 0 to 5 seconds, from 0 to 5 seconds, time in seconds I am writing. This is your clock. Just as the positive edge come, so till this time you will hold the value and it will count up. So from 0 to 5 seconds you will hold the value of 0, 0, 1. Say yes or no. And your decimal equivalent will be 1 and your output will be R. Now another positive cycle will come. When it will come? At 5 seconds. If this is 0 second, this will be 5 seconds. So at 5 second positive cycle will come and it will remain there till 10. So 5 to 10 seconds it will remain there. And what will be your decimal equivalent? That will be 2R. In that manner it will keep on counting up, right? It will keep on counting up. So till what it will reach? 1, 1, 1. Decimal equivalent will be 7. Output will be 7R. After 1, 1, 1, what will happen? It will come back to 0, right? After 1, 1, 1, it will again come back to 0. This is up counter. How up counter goes? 0 to 1, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and then come back to 0. So again it will come back to 0. What will be the decimal equivalent? Again it is 0. Again it is 0. So can you draw the output waveform? Yes. 0 to 5 seconds 0, 5 to 10 R, 10 to 15 2R, 3R, 5R, 6R, 7R, then again come back to 0. 0, then again it will rise. In that manner it will keep on repeating. So this will be the output waveform. Very easy question, very straightforward. It may seem like that what they are asking, but they are asking very straightforward thing. In digital electronics, you will feel like that they are asking a very big block diagram. What will happen? We will take a lot of examples where there will be a very big block diagram, but you just need to take them as a block level and the question will be solved. If they ask the internal structure, okay, when we solved the question in latches and flip-flop, if you remember, we solved a lot of question with internal circuitry. The question, if they are asking from internal circuitry, that would be difficult. But if they are asking on a block level, that would be easy only, because you just need to know the working. What do you think? Which was easy? Counter or latches? Initial part of latches was easy or counter was easy? Counter was easy, right? Because there we were dealing with the block level. But in latches, when we were studying, we saw active low, active high, then from active low to how I will make it active high. So these kind of things we were seeing on a block level. And then we saw a random example of latches as well, where there was no standard circuit. So how to solve those particular standard circuit, that also we saw. So these kind of questions are good, but on a block level it will be easy. So never drop a question of digital electronics when it is coming on block level. Okay. Let's see this question. Output of a DAC is given by this particular formula. Okay, where B3 is MSB. You need to find its resolution and full scale value. So let's write down the output of DAC. What is that? So if you put n equals to 0, what you are going to get? B0 by 2. Then if you put n equals to 1, what you are going to get? B1. If you put n equals to 2, what you are going to get? 2B2. If you put n equals to 3, what you are going to get? N equals to 3, you are going to get 3, 4B3. I can write it down in this manner. 4B3 plus 2B2 plus B1 plus B0 by 2. Okay. Can you see one thing here? What if I take 1 by 2 common? If I take 1 by 2 common, what will happen? 8B3 plus 4B2 plus 2b1 plus b naught. What is this? Decimal equivalent. If my bits are b3, b2, b1 and b naught, what will be its decimal equivalent? This will have a place value of 1, 2, 4, 8. Let's just say if it was 1, 1, 0, 1, how would I be writing? 1 into 1 plus 0 into 2 plus 1 into 4 plus 1 into 8. Or I can write b naught into 1 plus 0 into b1 plus 1 into b2, sorry, 4 into b2. What I am doing? Again, let's start. Okay, let's start this line. b naught into 1 plus 2 into b1 plus 4 into b2 plus 8 into b3, where your b naught is 1, 1 plus b1 is 0, 0 plus b2 is 1 and b3 is again 1. So this is just decimal equivalent only, no? Place value 1, 2, 4, 8. This is the decimal equivalent. So what you are getting here? My target was to make it v naught equals to r into d. Say yes or no? Right? So what is the r value I am getting? Half. Okay. This was the method 1. If let's just say if this is not clicking to me, but till now this thing will click, no? That at least I can write down the final value 4b3 plus 2b2 plus b1 plus b0 by 2. At least till this point you can write down, right? If let's just say if my all bits are 0, for b3, b2, b1 and b0, if I put all of them equals to 0, what will be my v0? v0 will be equals to 0. And if I just take LSB high, okay, I am only taking LSB high, what I am getting? v0 equals to, all these are 0, v0 equals to 1 by 2. So if your only LSB is high, LSB is only high, then your analog output, this is your analog output, and what is that equals to? Resolution. Okay, this is method 2 and this is method 1. Are you getting this point? Look, if it was 0, 0, 0, my output was 0. If there is one change, if there is change in one decimal, v0 is equals to r into d. If this was 0, my v0 was 0. If this is 1, my v0 is equals to r. There you go. Okay. I will just make a change here in this point. Here I will write down a note that is considering 0 offset. What is the meaning of that? You will understand. But I forgot to write it down. Considering 0 offset. Okay. Let me explain the meaning. So in this case, what we were taking, v0 equals to 4b3 plus 2b2 plus b1 plus b0 by 2. All over 0, my output was 0. But what if there is some offset? What do you mean by offset? That what was our waveform? We were starting from 0, right? We were starting from 0, in that manner we were going. In that manner we were going. But it may happen that you might have started from some higher value. So there is this offset needlessly. Even if your applied input is 0, even if your applied input is 0, then your v0 will not be 0. There will be some particular value. It could be 2 millivolt. So this 2 millivolt will be your offset. When the decimal equivalent of input is 0, what you would expect at the output? You would expect 0 volt at the output. But even if after applying 0 decimal equivalent, you are getting some output, that means that is known as offset. So that means you are starting from here. Okay. So here you would have gotten some output. So these kind of examples we will solve where there will be some offset present. Some offset will be present. So here you would be getting 2 millivolt and here you would be getting 0.5 plus 2 millivolt, because this offset is already present. So you would be getting 0.5 plus 2 millivolt. So your resolution will not be 0.5 plus 2 millivolt, that would be 002. This will not be your resolution. Your resolution will be 0.5 only. This is the offset that you need to ignore. Okay. So in this example there is this no case, but just now I remember it. So these kind of examples I have already written. We are going to solve these kind of examples, so no need to worry about that. Okay. So just one point I wanted to write, that they're considering 0 offset. So this is your resolution. Now what we need to find? Full scale value. So what will be your full scale value? That would be resolution into maximum decimal equivalent. There are 4 bits, 1111, that would be 15. So full scale value will be 7.5 volt. Okay, and what will be your, okay, that's it. This is what you need to find. Okay, there you go. Very easy question. Let's solve this question. A 4-bit DAC is having an offset of 2 volt. This is an unrealistic data because offset cannot be this much high. It would be in millivolt or in microvolt. But let's take it just for the sake of understanding. Okay, is there any other question left? No. After that, we will see in next lecture. So yeah, let's see this question. It is having an offset voltage of 2 volt. For input this much, output is 10 volt. Find its resolution and what will be its output voltage when these are the bits. Okay, so this is my DAC. Which is having 4 bit of input. It will have some resolution. It will have the analog output. Okay. Now if applied input is 0 0 1 0. So what would be your ideal V node? It would be R naught into D, right? R into D, not R naught. R into D. What is the decimal equivalent? 2. So V naught should be equals to 2R, and that you will say that is equals to 10 volt. But no, that's not the case. It is having an offset of 2 volt. What do you understand by that? That V naught is equals to R into, even if your decimal equivalent is 0, then it can have 2 volt output. Offset of 2 volt. Actually, offset can be positive or negative anything. Okay, offset can be positive or negative anything. They are mentioning positive offset, so I will put plus 2 volt here. Okay, but actually offset can be plus minus 2 volt. But here I will put 2 volt. So still your output is, even if your decimal equivalent is 0, still you are having 2 volt of output. That means this is known as offset. So your V naught offset is 2 volt. So it will always be there. So basically you are starting your output waveform. Your output waveform should have been started from 0, but you are starting your output waveform from here. So in that manner you are going. So this is known as offset. Okay, this is your 2 volt. So this is your offset, which is 2 volt. Okay, so your V naught is equals to plus 2 volt, plus 2 volt. So extra 2 volt is added. So 2R, and that is equals to 10 volt, right? This is equals to 10 volt. When decimal equivalent is 2, my output is 10 volt. So 2R plus 2 is equals to 10 volt. So R is equals to 4 volt. So this is my resolution. Okay. Now what you need to find? You need to find the output voltage when this is the input. So what will be the output voltage? 4 into, what is the decimal equivalent? This is the second question I am solving. 4 into, what is the decimal equivalent? 10105. 20? No. Along with that you will have 2 volt also added. So this will be your output voltage. That would be 22 volt. Okay. This is your output voltage. So this is the answer of second question. This is the answer of first one. Understood? So that's it about the basic introduction of DAC. Now we were treating this as a black box, right? Now we are going to design this DAC. We are going to design this black box now. So how we are going to design? There are two ways: weighted register type DAC and R2R ladder type DAC. Very simple thing. One trailer I have already given in the first slide only, when you were studying the first slide. Here in this slide only I gave you a trailer how would we design it, because this was the design only. This was the black box, and here these were my controlling inputs. So that trailer I have already given. Now we are actually going to design it. Okay. So that we are going to see in the next lecture. So I hope now you are comfortable with these basics, which are most important part of a DAC. Okay, then let's meet you in the next lecture. Yeah, so now we are going to design that DAC. Okay, now we are going to design our digital to analog converter. We have already studied what do you mean by digital to analog converter and what all are the specification of a DAC. Now we are going to design it. So there are two ways: weighted register type DAC and R2R ladder type DAC. Okay, so first we are going to study about weighted register type DAC. So forget about the name. Just this is a simple circuit in front of you. There are three inputs. I will call this as B2, this as B1, and this as B0. You will understand why did I wrote down in this manner, and this is my MSB and this is my LSB. You will understand it why I wrote down in this manner. Okay, this is my MSB, this is my LSB. Now you need to find out the output voltage. This is your task. What is this switch? That if B2 is 1, it will be connected to VREF. If B2 is 0, it will be connected to ground. If B1 is 1, it will be connected to VREF. If B1 is 0, it will be connected to ground. If B0 is 1, it will be connected to VREF, otherwise ground. Okay. I'm not solving it by voltage, I'm solving it by current. One thing I know that there will be I feedback current flowing through the resistor. And if this I feedback current is flowing through the resistor, then what will be my output? Because of the virtual short, this will be 0. So my output will simply be minus IF into RF, that I know, right? And what is my IF? My IF is simply equals to I2 plus I1 plus I0. Say yes or no? I2 plus I1 plus I0 into RF. So till this point I know. Now my target is just to write down the value of I2, I1 and I0. Let's talk about I2. Okay, now I am talking about I2. What will be my I2? If B2 is 1, that means it will be connected to VREF. So VREF by R, I2 will be what? VREF by R. This is 0, this node is 0 and it is connected to VREF. So what will be I2? VREF minus 0 by R, that means VREF by R. And if B2 is 0, that means this is connected to 0. So here also there is 0 and here also there is 0. 0 minus 0 by R, I2 will be 0 only. Did you understand this point? This is your R. Here there is 0 fixed voltage. This is your B2. If B2 is 1, that means it is connected to VREF. So what will be this current? I2. That will be VREF by R. Right? And if B2 is 0, that means it is connected to ground. Right? It is connected to ground. And if it is connected to ground, that means here 0 volt will come. So 0 volt minus 0 volt, current will be 0. Right? So these are the two values of I2. Now based on these two values, can I write down my I2 expression in this manner? That my I2 is VREF by R into B2. Do you agree to this point? This is my I2. Do you agree to this point or not? And this is my V0 expression. Because if B2 is 0, then I2 will be 0. If B2 is 0, I2 will be 0. And if B2 is 1, I2 will be VREF by R. So I can write down my I2 in this manner. VREF by R into B2. Similarly, what I can write down my I1? What will be my I1? I1 will be VREF by 2R into B1. Say yes or no? Because if B1 is 0, 0 minus 0, 0 current. And if B1 is 1, that means it will be connected to VREF. So VREF by 2R. So if B1 is 1, my I1 will be VREF by 2R. And what about I0? My I0 will be VREF by 4R into B0. So this is my I0. Okay. So now I can write down my V0. What will be my V0? V0 will simply be equal to minus. What is my I2? VREF by R into V2. VREF by R into B2. What is my I1? VREF by 2R into B1. And what is my I0? VREF by 4R into B0. VREF by 4R into B0. Okay. Into RF. What I can take common here? Can I take common as VREF by what will I take common? VREF by 4R. Can I take common VREF by 4R? Yes, you can take common VREF by 4R. So what you are going to get here? 4B2 minus sign is already there. 4B2 plus 2B1. Right? I took VREF by 4R common. So 4 will be multiplied here, 2 will be multiplied here, plus B0 into RF. Do you understand why did I take this common? Because now what this will be? In the previous question, in the previous lecture, we solved a question. What this will be? This will be your decimal equivalent. Decimal equivalent. So what you are getting? Minus VREF into R by 4R into D. This is your V0. Okay. So what should be my V naught? In a DAC, what I target? That my V naught should be proportional to D. And when I remove the proportionality sign, what I will get? This value I am getting. That is minus Vref into RF. Minus Vref into RF divided by 4R into D. There you go. So isn't it acting as a DAC? We just designed a circuit. I don't know whether it was DAC or not. When I analyze it, I got to know that it is acting as a DAC only. So it is a DAC. Okay. So from this analysis, what you need to remember? I will only tell the things which you need to remember. First thing is you should remember this circuit. I am not saying you need to remember this circuit. I am saying you should remember this circuit. Okay. You should remember this circuit. What you will remember? Inverting op amp is there. RF is there. R, 2R, 4R. This is weighted resistor type DAC. So weight of resistance is increasing now. R, 2R, 4R. So how will you remember that whether R will come upward or 4R will come upward? How will you remember it? So one resistance is R, one resistance is 4R. Which is having more weight? 4R is having more weight, right? In a bag, if you need to put things, will you put the things which is having lesser weight first or which is having more weight first? That means if things are lined up like this, so this will be having the maximum weight, no? Because if you are putting the thing which is having the least weight and then more weight, then more weight, then more weight, so that is of no use, because the least weight thing can be destroyed because of the more weight. So when you put the things in a bag, you put the maximum weight downward. So maximum weight downward. So 4R, then 2R, and then R. So in that manner you can remember R, 2R, 4R, weighted resistor. Now whenever you write down the bits, how do you write down? MSB and then in last LSB. In that manner you write down. You don't write down in this manner, no? And then you say that, sir, this is my MSB and sir, this is my LSB. You don't write down in this manner. You always write down in this manner, right? So first MSB should come and in the last LSB should come. So first MSB will come and the last LSB will come. This is how you can remember it. This is just a way to remember. So from here, what is the conclusion you are seeing? That LSB bit is connected to the maximum resistance. Or you can say it will drive the least current. LSB bit will drive the least current because I naught is Vref by 4R. Resistance is highest, that means it will drive the least current. Okay. So this is like in some previous year gate question paper, this was asked that in a weighted resistor type DAC, the LSB bit will be connected to which resistor? Okay, so that was asked in one of the previous gate year question paper. Should not be asked, like these kind of things should not be asked, they should ask the analysis. But what if they ask? So you should remember this circuit. RF, R, 2R, 4R, 8R. Yeah, one more thing. What is this 4R? What is that? It is 2 to the power n minus 1 here. R. Say yes or no. This resistance is 2 to the power n minus 1 R because there are 3 bits. So what is the resistance? 2 into 3 minus 1, 2, 4R. There are 3 bits are there. So resistance is 4R. So this you will remember eventually because you will know that, sir, we studied the example of 3 bits. So in that example, we took R, 2R, 4R. Okay, so the final resistance was 4R. If the final resistance was 4R, in case of 3 bits, that means certainly the formula is 2 to the power n minus 1 into R. So you are eventually going to remember it. No need to worry about that. The only thing you need to remember is that I will start from upward. R, 2R, 4R, 8R, 16R, 32R. In that manner, I will keep on going. And then this will be my MSB, then lower than that, and last will be my LSB. So if they ask you what will be the resistance connected to LSB bit, 2 to the power n minus 1 into R. In a 10-bit DAC, what will be the resistance connected to LSB bit? In a 10-bit DAC, what will be the resistance connected to LSB bit? 2 to the power 10 minus 1, 9 into R. 512 R. Okay. In a n-bit weighted resistor type DAC, how many resistance you will require? How many resistors you will require? In a n-bit weighted resistor type DAC, how many resistors you will require? These n resistor plus this one resistor, n plus 1 resistor you will require. Look, These may seem like senseless questions to you, but these have been asked in the GATE examination. Okay, so that's why I am putting these questions up. But now the level has been increased. I don't think they will ask these kind of questions. But in the worst case, what if they ask these kind of questions? Okay, so this is a standard circuit. You should remember R, 2R, 4R, 8R, 16R. This you have understood. Okay, so let's write down all the conclusion. So I hope I have given all the points here. So this will be the conclusion. This is your n bit weighted resistor type DAC. This will be your input because you will be starting from the maximum. Okay, and this will be connected to R, 2R, and then 2 to the power n minus 1R. So you will be starting with MSB and will be going towards LSB. R, 2R, 2 to the power n minus 1R. So MSB bit resistance will be R and LSB bit resistance will be 2 to the power not n minus 1. No. 2 to the power n minus 1 into R. Okay, in that manner you will go. Right? So this will be the configuration and number of resistance they can ask n plus 1 that you can write down. And what will be your R naught? So what will be your V naught? Sorry, V naught will be R into D, where decimal equivalent you can write. How you can write R? Okay, how you can write R? So Vref into RF by what? RF by LSB resistance. Minus sign will also be there into decimal equivalent. As an educator, I remember it, but if you don't remember it, then also you will be able to solve the problems. Okay, but if you remember it, it is pretty good. Vref into RF by the resistance which is connected to LSB. What is that? 4R. Resistance which is connected to LSB, 4R. And minus sign is certainly there. So yes, this is the output. Okay. So just like I just taught it for now n bits. 4 bits, 5 bits, 6 bits, 7 bit, anything could be there. So this slide, if you want to remember, you should remember. But at least these two things you will remember. Okay. At least these 2 points you will remember, that MSB bit in a n bit weighted resistor type DAC. MSB bit will be connected to resistance R and LSB bit will be connected to resistance 2 to the power n minus 1 into R. V naught will be R into D. And if you want to remember this expression of resolution, then also you can remember. Okay. Let's solve a question. So these kind of questions can come. So this particular circuitry is given. The step size of given DAC is 1 volt. Step size is given, that is 1 volt. Digital input could be 0 or 5 volt. If logic 0 is there, that means it is 0 volt. If logic 1 is there, it is 5 volt. You need to find the value of RF. If you don't know anything, how would you solve it? Step size you know. Step size means resolution you know. What is the resolution? That is 1 volt. So let's try finding resolution of this particular circuit. So how will you find the resolution of this particular circuit? What is the first task? I told you one thing, that put D, C, B, A, where D is the MSB and A is the LSB. Put all those equals to 0. If you put all those equals to 0, what is the output you are getting? All are 0. So 0 current, 0 current, 0 current, 0 current will be there. V naught will be 0 volt. What does that mean? That there is no offset. This you got to know. That there is no offset. If my output is R into D only, my output is R into D. There is no offset, because if I put decimal equivalent 0, I am getting output equals to 0 only. Now if I put decimal equivalent 1, if I put decimal equivalent 1, what I am writing? Decimal equivalent equals to 1. Then what will be my V naught? V naught should be equals to R, right? V naught should be equals to R. Because decimal equivalent is 1, V naught should be equals to R. Now if you put 1 here, that means MSB bit 0, these bits 0, and only this bit is 1. So what is the output you are getting? This will be 0 only, these will drive 0 ampere current, 0 ampere current, 0 ampere current. This will only drive the current. How much current it will drive? 1 by 8 kilo ohm into RF. So what is the V naught you are getting? 1 by 8 kilo ohm into RF, negative sign is also there. Okay. So this is the output you are getting. This is the output you are getting. So from here, what did you get to know? That your RF by 8 kilo ohm is equals to your resolution. And that is equals to 1 volt. Okay. So what is the value of resolution is equals to 1 volt. Okay. RF in kilo ohm I am considering, okay, RF in kilo ohm I am considering. Wait a second, is there something error? Yeah, this is also RF by 8 kilo ohm, RF by 8 kilo ohm. Wait a second. Yeah, actually this answer will be in volt only, and this is also in volt, so volt to volt will get cancelled. Basically RF by 8k, this will give voltage, no, it will be in volt. This will also be in volt. V naught will be equals to volt only. So this volt and volt will get cancelled. So what is the value of RF? 8 kilo. That's it. Without even mugging up any formula, without even writing down any formula, we solved the question. Very basic concept. I told you one thing. Put all bit equals to 0. What is the output? You will get to know there is no offset. If there is no offset, that means if I put decimal equivalent 1, my output should be equals to the resolution only. Decimal equivalent is 1. So what is the decimal equivalent 1? So what is my output? RF by 8 kilo ohm. So RF by 8 kilo ohm is equals to the resolution. What is my resolution? That is 1. So my RF is 8 kilo ohm. There you go. Very easy question. Without even mugging up any formula, I should be able to solve it. And what would be the method 2? This I would know that it is a standard DAC. Standard DAC it is, weighted resistor type DAC it is. So I know what is the output. Output is Vref into RF by maximum resistance, that is 8 kilo ohm, into D, and minus sign is there. This is the resolution. So resolution, that is equals to 1, and that is equals to Vref. What is the Vref value? Okay, here I did some mistake, I guess. Vref value is 5 volt. This is 5 volt here. Sorry for that error. This will be 5 volt here. 5 volt. So this will be 5 RF by 8k. So 8k by 5. 8k by 5. What that would be? 1.6 kilo. Okay. Now here if I directly remember the formula, then Vref is 5 RF by 8k. So RF is equals to 1.6 kilo ohm. Okay. So without even remembering any formula, here I remember the formula, I got this answer, but without even remembering the formula, I can also get the answer. In any DAC, it is given, just the name is written DAC. What you are going to put? 0, 0, 0. You will get to know if there is any offset. If there is no offset, then if I put decimal equivalent 1, my output should be equal to the resolution. So if I put decimal equivalent 1, my output should be equal to resolution. So these will be 0, 0, 0. My output will be minus RF by 8k into decimal equivalent, which is 5 volt. Decimal equivalent 1, it means it is 5 volt. So minus RF by 8k into 5. Okay. And that is equals to 1 volt. So from there I got my RF value equals to 8k by 5, 1.6 kilo ohm. Otherwise by this formula. But remembering formula is not an easy task. You will eventually forget it in the examination. Okay. So that's it about your weighted resistor type DAC. Very straightforward topic. Very straightforward topic. Only this I am asking you to remember. Otherwise you know all the things already. Only this thing I am asking you to remember. Now we are going to study about R2R ladder type DAC, but before that, let's solve a question. Okay, forget about R2R ladder type DAC. Let's solve a question. This question is given in front of you. You need to find the Thevenin equivalent at node X. VTH, RTH you need to find with the different values of B naught, B1. So if B naught is 0, B1 is 0, both will be connected to ground. If B naught is 1, B1 is 0. If B naught is 1 and B1 is 0, this will be connected to Vref. This will be to ground. Okay, in that manner we need to go. If B1 is 1 and B0 is 0, this will be connected to Vref, this to ground. And if both are 1, both will be connected to Vref. So you need to find the Thevenin equivalent at node X with respect to B1 and B0 value. Okay, with respect to B1, B0. And B1, B0 you need to take as MSB. So what I am gonna do is that I am just gonna replace this circuit in this manner. VTH. This is my RTH. Yeah, one more thing. If someone asks you what is the drawback of this DAC, what is the drawback of this DAC? If the number of bits increases, what will happen? This resistance value will also decrease. This resistance value will also increase. No, if number of bits increases, 1 kilo ohm, 2 kilo ohm, 4 kilo ohm, 8 kilo ohm, then 16, 32. In that manner, it will keep on increasing. Now, using these much high resistance is a tough task. Like these resistance will be bulky. Okay, the size of resistance will be large. So this is one of the issue. Also, there will be, if the size of resistance is large, that means there is high chance of error as well. Let's just say I thought that the resistance is 32 kilo ohm, but because this is very large, it could be 30 kilo ohm or 34 kilo ohm. So in the output you will have the errors. If the resistance value changes, then output value will also change. So these kind of error you will go through if you use this kind of DAC for a higher value of number of bits. If number of bits are high, then you cannot use this weighted register type DAC. So this is one of the drawback which you need to remember, that if resistance value increases, then size of resistance will increase. So that is one of the issue, the size will increase. Another thing, error will also increase. Okay, so that's why we came with this kind of DAC R to R. Here only two kind of resistance we are using, R to R, not more than that. Okay, so only we will use R and 2R. Okay then, so now let's solve this problem. Try it on your own. First take, this is what we need to do, B1 B naught 0 0 0 1 1 0 and 1 1. So let's see, and then we need to fill this RTH and VTH. So if B1 B naught, if both are 0 0, then both will be connected to ground. This was your B naught, this was your B1, both are connected to ground. Tell me what is your RTH, Thevenin voltage. If you see from here, R to R will come in parallel. Sorry, 2R to R will come in parallel, it will be R. R and R will come in series, it will be 2R. 2R parallel to R will be R only. Very easy. 2R parallel to R, R. Okay, let me make it here because some guys might be not that good in network analysis. But we have studied these kind of things very deeply, right? Now R and R will come in series, that will make 2R and this will be gone. 2R to R parallel would make R. Okay. Very easy thing. What will be your VTH? There is no source available. All are 0. So how will you get the voltage? 0 volt. VTH is 0 volt, right? Let me pause the video. I will drink some water and then you try to solve this on your own. Okay. Yeah, so I need to find VTH and RTH. Let's first find RTH. How will you find RTH? For finding RTH, whatever the independent sources you see, you need to nullify that. What is the independent sources here? VREF. This is my B naught, this is my B1. So I will nullify this. Nullify means I will connect it to ground. So what is the RTH I see? RTH will be equals to R only, because 2R to R in parallel will be R. R plus R, 2R. 2R to R in parallel will be R only. So RTH is R only. Okay. To get the Thevenin equivalent, I nullified all the independent sources. So I just nullified it. Now what do I need to find? I need to find VTH. What is my VTH? VTH is always an open circuit voltage which is a function of input independent voltage, that is your VREF. So it will be a function of VREF. How you can find it out? Okay, so what I can do, first I will find out Thevenin here. At this node I am finding Thevenin. So what that would be? VREF by 2, voltage will be VREF by 2, and what will be the resistance? R parallel R, but that will be 2R parallel with 2R, that will be R only. And then another R is there. Basically at this node I have found the Thevenin resistance and Thevenin voltage. Do you understand this point? This is your 2R and this is another 2R and this is your VREF. Here you are finding Thevenin again. First you are finding Thevenin here. So that would be VREF by 2, 2R to R in parallel will be R only. VREF by 2, how I am getting? I need to find the potential here. Simply potential divider, that would be VREF by 2. And what will be the Thevenin resistance? That will be 2R parallel with 2R, that will be R only. So this I have found. Okay, you should be comfortable with these kind of analysis if you are studying network analysis. Okay, now this will be my R and this will be my 2R. And here I am getting my VTH. It is open circuit voltage, that means this will drive 0 ampere current. It is open circuit voltage. So you can say all the current will be same here, right? So what will be your VTH? VTH will be VREF by 2 divided by 4R into 2R. Or you can directly see this R and R are in series. So 2R and 2R are there. So simply potential divider you can do. So what is the answer you will be getting? VREF by 4. Okay. So RTH you are getting R and VTH you are getting VREF by 4. So you should have a good practice that you don't need to make these diagrams again and again. Without even making the diagram, you should have the practice that you can write down VTH and RTH. What did I do? Here I will be getting VREF by 2 in series with resistance, that is R, R and R 2R, 2R in series with 2R. So here I will be getting Vref by 4 and total equivalent resistance will be RTH equals to R only. Say yes or no? Okay. So you should have the good practice. So VTH is this, RTH is this. What about this? Here you can see this is R parallel, 2R parallel to R. This will be R only. R series with R, 2R, 2R parallel to R. What that would be? 2R parallel to R, what will be R? R series with R. What that would be? 2R. R series with R, 2R. This is your 2R. This is your Vref. This is your 2R. And here you are getting your VTH and RTH. RTH you can directly see, you will nullify this. If you nullify this, 2R parallel with 2R, RTH will be R only. What will be your Vref? Vref, sorry, not Vref, VTH. VTH here also I can directly see VTH is Vref by 2. Okay, VTH is Vref by 2. Because you can see both will have the same current because VTH is open circuit voltage, so this will drive 0 ampere current. So Vref by 2. Simply potential divider I can do Vref by 2. For this case, what will be the answer? RTH will again be equals to R only. Because Vref will be gone, Vref will be gone. So 2R to R will come in parallel. R series with R, 2R, 2R and 2R again will come in parallel. RTH will be equals to R. What about VTH? So for finding VTH, what I can do? I can apply superposition theorem. That first I will consider this Vref and this as ground. So if I consider this Vref and this as ground, what I will get? Vref by 4. How I am getting Vref by 4? You remember here. Only consider this and remove this. So what you will be getting? Sorry, Vref by 2. Vref by 4 only. That's what I was thinking. Here I wrote wrong. So here I am getting Vref by 4. Okay, if I consider only this and this as ground, so Vref by 4. And when I consider only this and this as ground, I will get Vref by 2. So Vref by 4 plus Vref by 2. Right? First I consider this and this as ground, so Vref by 4. Then I consider this Vref and this as ground. So what I get? Vref by 2. Okay, so this is the answer I am getting. Let's write down in a table and let's see what we are getting now. So what is your RTH? RTH is always R. In all the condition, RTH was always R. What was your VTH? You don't need to remember anything here. Okay, whatever that we are studying, you don't need to remember a single thing. Just you need to see the analysis because that is required for the derivation. And what is your VTH? In this case, VTH was 0. Then what was the VTH? Vref by 4. Then what was the VTH? Vref by 2. And then what was the VTH? Vref by 2 plus Vref by 4. Say yes or no? So always your RTH is R. Now can I write down my VTH in this manner? Okay. Vref by 4 plus 2B1 plus B0. Say yes or no? Put 0 0 here, it will be 0. Put 0 1 here, it will be Vref by 4. Put 1 0 here, it will be Vref by 2. And put 1 1 here, what you will get? Vref by 4 into 2 plus Vref by 4 into 1. So Vref by 2 plus Vref by 4. So what did you understand? How you can write down VTH? So this particular circuitry where B0 and B1 are those bits can be represented by this equivalent VTH and RTH. This equivalent VTH and RTH where this is your VTH and this is your RTH. So what do you see here? This is my decimal equivalent. Say yes or no? This is my decimal equivalent and this is your VTH, right? What if I was collecting my output V0 here? What if I was collecting my output V0 here? So this is an open end, so this will not drive any current. So my V0 will simply be equals to VTH only. And VTH will be equals to Vref by 4 into 2B1 plus B0. So what you can see here, this is your decimal equivalent. So your V0 is equals to R into D. Say yes or no? Okay. How you will write down for 3 bits? Try writing down the RTH first. First tell me what will be the RTH. Always it will be R only. Look what you need to see. Start with 2R, 2R R, 2R R and then end with 2R. This is what you need to see. Start with 2R 2R, and with 2R. This is your R to R ladder. What this is known as? R to R ladder. Start with 2R, 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 and with R. Okay. VTH and RTH you need to write. RTH will always be R only. What do you think? Yes. Oh, let's take all these as ground. So 2R will come in parallel, R plus R, 2R will come in parallel, R plus R, 2R will come in parallel, R. RTH will be R. Now these are bits B0, B1 and B2. B0, B1 and B2. These are the bits B0, B1 and B2. It can be either connected to ground or it can be either connected to VREF. How do you write down VTH? How did we write down VTH here? VREF by 4. VREF by 2 to the power n. Here what I am going to write? VREF by 8. Okay. Into. What did I write here? 2B1 plus B0. Decimal equivalent. What will be the decimal equivalent of this? 2B2. Sorry. 4B2 plus 2B1 plus B0. Okay. This will be your RTH. For n bit will not be useful and you don't need to remember it as well. Okay. Just telling it for the sake of derivation, nothing else. Don't need to remember it, just you need to see the analysis. RTH will be equals to always R. What will be VTH? VREF by 2 to the power n. VREF by 2 to the power n and then decimal equivalent. Just decimal equivalent. Okay. VREF by 2 to the power n and then decimal equivalent. And you can see this is R into D. Say yes or no. This is your resolution into D. We will see how the questions are asked in the examination. You don't need to remember anything. Just for the sake of derivation, we are doing it. Well and good. One more thing. This is a 3-bit R to R ladder, right? 3-bit R to R ladder. I would say 3-bit R to R ladder. How many resistors are used? How many resistors are used here? 1, 2, 3, 4, 5, 6. 6 resistors used. This was your 4-bit R to R ladder. How many resistors are used? 4-bit, sorry, not 4-bit, sorry, 2-bit R to R ladder. This was your 2-bit R to R ladder. How many resistors are used? 4 resistors used. Okay. So for n-bit R to R ladder, this is RTH, this is VTH, resistance used, number of resistance used, 2n. Okay. This also you need to remember, in the gate examination it has been asked that for n-bit R to R ladder, number of resistance used will be 2n. But what will be the resistance? Resistance will be R and 2R only. Okay, here in this particular configuration, how many resistance you are using? N resistance in this particular configuration. This was 4 bit, so you were using 4 resistance only. But the value was R, 2R, 4R, 8R, 16R. Here you are using 2N resistance. Here you are using 2N resistance, right? Here you are using 2N resistance, 2R, 2R, R2R, R2R. But the values are R2R only. So resistance are not bulky here. And if they are not bulky, they will take less area. And also, if they are not bulky, then error will be less. If I am taking resistance of 2R, then it will be near to 2R only. It's not that it can be vary. Okay. But if you take a resistance of 32R, it can vary from 34R to 30R as well. But if resistance are small, then error will also be less. So that's why this is preferable if the number of bits are large. Because if the number of bits is increasing, still the resistance will always be R and 2R. That's why it is known as R to R ladder type deck. But this is not the final deck. what we actually do is that we use an op-amp. Okay, we use an op-amp. So this is my R to R ladder. This is my complete R to R ladder, and then there is a inverting op-amp. I know the analysis of this R to R ladder. Now derivation will be very easy for me. But if I had started right from here, then it would be difficult for you. R to R ladder. Okay, 3-bit R to R ladder. So this will be known as R to R ladder type DAC, 3-bit R to R ladder type DAC. This is your 3-bit R to R ladder. But before that, let's solve a question. Simple network analysis problem it is. Pause the video and write down answer on your own. You need to find the Thevenin equivalent. Pause the video and write down the answer on your own. Final answer you need to write, very easy. So how we will solve it? Look, how you will go. First we will find the Thevenin equivalent here. What you will get? Vref by 2. What you are going to get is that Vref by 2 plus resistance R. How I should write it? Vref by 2 with resistance R. This will be the equivalent here. Then R and R will come in series. It will be 2R. So 2R and 2R. Again I am finding Thevenin resistance here. I will just keep on going in that manner. First I found the Thevenin resistance here. Vref by 2 and R I am getting. So R and R, 2R. 2R in series with 2R I will take. They are not in series, but when I am finding Thevenin, Thevenin means open circuit voltage. So this will be open circuited. So this will not drive any current. So 2R and 2R will come in series now. So what will be the voltage you will be getting here? Vref by 4. And what will be the resistance? Resistance will be R only, because R and R, 2R. Now 2R and 2R will come in parallel for resistance. This is your 2R, which is connected to some Vref by 2. And this is your 2R again. It is connected to ground. And from here you need to find the Thevenin. So this will be connected to ground. So 2R, 2R will be in parallel. What that would be? R only. So this will be R. Okay. Now R again becomes 2R. 2R, 2R, the same circuit is there. Just this will be half Vref by 8 with the again resistance R. Now again R, and this is your 2R. R. Again there is 2R. So 2R and 2R, it will divide again half. What you will get? Vref by 16. And 2R, 2R in parallel, what will be the equivalent resistance? That will be R. So what is your VTH? Vref by 16. And RTH is equals to R. Okay, so this is how you will go. Vref by 2, R, 2R, 2R, Vref by 4, parallel in series with R, 2R, 2R, Vref by 8, this will be R, 2R, 2R, Vref by 16, 2R parallel with 2R, that would be R. So Vref by 16 in series with R. This will be your Thevenin equivalent. Okay. Say yes or no. So this will be used in some of the questions. That's why we are dealing it here. Let's see the analysis of this one. What I'm gonna do? I'm gonna replace this with the Thevenin equivalent. What will be the Thevenin equivalent here? I'm gonna find VTH and RTH. We usually use op-amp. Okay, after this R to R ladder, we use op-amp so that we get an enhanced output. VTH, RTH. We will amplify the output simply. Okay. So what is the VTH we will get? What will be the VTH? 3 bits are there. So Vref by 8. If you remember it, then it is good. Otherwise, you don't need to mug it up. Vref by 8, 2B2 plus B1. Till now in the gate examination, never any question has been asked where you had to remember this kind of formulas. Okay. Without even remembering the formula, you can solve the problem. And here 2R, 2R all will come in parallel. 2R, 2R will become R, 2R, 2R, 2R will become R, 2R, 2R, 2R will become R. So RTH is equals to R. So these are your VTH and RTH. Okay. So simply this will be replaced with the battery and a resistance. So this is how your circuit would look like. This is your VTH, this is your R, this is your RF is connected. So what will be your V naught? V naught will simply be minus RF by R. R is R plus RX into VTH. So what will be your V naught? V naught is minus RF by R plus RX into what is your VTH? VTH is Vref by 8 This is your B naught. Okay, sorry. Yeah, I have written it. I thought I forgot. B naught plus 2B1 plus 4B2. So what do you see here? This is your decimal equivalent. And what is your resolution now? This is your resolution. So resolution has increased. Previously resolution was VREF by 8. Now resolution is RF into R plus RX into VREF by 8. Okay, so resolution has increased. So to increase the resolution, you do these kind of things. You connect a op-amp there. Otherwise, R to R ladder is also working as a DAC only. This was a DAC only, but we just connect a op-amp. Okay, so this is the standard circuit. No need to remember the final answer. Okay, no need to remember this particular final answer. It's all fine. Without even remembering the answer, we will be able to solve the problems. Let's see this one, analyze it on your own. Where you can see R to R ladder. Here I can see R to R ladder. This is my R to R ladder. 3-bit R to R ladder. Can you replace this with VTH and RTH? Yes. This is how it will look like. VTH will be VREF by 8. Same VTH will be there. Same RTH will be there. RTH will be equal to R only. VREF by 8. B naught. The same expression. Right? Same expression. Now, this will not drive any current, right? RTH will not drive any current. So, there is no use of this RTH. See, this VTH will directly come here. So, what will be the gain of this? V naught will simply be equal to 1 plus RF by R into VTH. This will be your V naught. 1 plus RF by R into VTH. And what is the value of VTH? VTH is VREF by 8 into V naught plus 2B1 plus 4B2. So, this will be your final answer. Okay, just for the sake of derivation we are doing, let's see what kind of questions can be asked in your examination. So, this was asked in GATE 2022. So, try solving it on your own. Nothing DAC or anything like that, nothing is mentioned. You just need to find the final output of V naught of a op-amp. This question is based on op-amp, not on DAC or anything like that. Okay, so just solve it. What I'm gonna do, there are two sources, 1.6 volt, 1.6 volt. So what I'm gonna do, first I will consider only this 1.6 volt. So let's remove it. Let's keep it ground. So what will happen? 1.6 R. What I'm gonna do, I will keep on finding the Thevenin. Okay, so 2R to R, here I'm gonna get 0.8. R and R, 0.8 and R, right? Then R and R will come in series. 2R in series with 2R. Here I'm gonna get 0.4. Then again I will be having R. Here what I'm gonna get? 0.2. Again I will be having R. R to R, R to R. Here I'm gonna get 0.1 in series with R. So what is my final circuit? 0.1. This is your R. This is your 2R. This is your 3R. And this is your V naught. This is the final circuit. 0.1, 3R, RR, and this is op-amp. People usually forget this R. Okay, this was asked in GATE 2022 and I also forgot this. So I got my answer wrong. It costed me 2 marks. So people usually forget this R. Okay, so keep that R with you. Basically, Thevenin equivalent of this is, you are finding the Thevenin equivalent as well, no? So Thevenin equivalent here is resistance R as well. So you will forget this R. Okay, so always remember it. From here you will go 0.8, 0.4, 0.2, 0.1, but take the resistance with you. Resistance R is also there. In all the Thevenin equivalent, we are getting resistance R as well. So finally it is being carried. Okay, so this is the final circuit. So what you are gonna get? V naught is equals to minus RF by R. So RF is 3R and this is also 3R only. Minus RF by R into 0.1. Minus RF by R into 0.1. So 3R divided by 3R into 0.1. So minus 0.1. But this was only considering one of the source. We have one more source. What is that? This 1.6 volt. So let's solve for that. If I am considering this 1.6 volt, that means I will keep this as grounded. So if I keep this as grounded, 2R to R, it will become R. R and R, 2R. Here there is no voltage. I am directly finding the equivalent resistance. R and R, sorry, 2R and 2R, R. R series with R, 2R. 2R in parallel with 2R, R. R plus R, 2R. Now what is your circuitry? 2R, then here 2R, 1.6 volt. Till now everything is clear. 2R, 2R, R plus R, 2R, 2R parallel with R plus R, 2R. So this is your 2R, this is your 2R, this is your 1.6 volt. Now what you will get here? 0.8 volt. And 2R in parallel with 2R, that will be R. Okay. So here what you are getting? 0.8 volt. Here you are getting 0.8 volt carrying resistance R. Now R plus R, 2R. Again I am finding Thevenin equivalent here. So R plus R, this is R plus R, 2R. 2R, this will be simply divided 0.4, and 2R parallel with 2R, this will be R only. So what is your final circuitry? 0.4. Here you are having R. Here you are having 2R. I hope all these things are clear. If you just study only if you are studying digital electronics, then it might be difficult for you. But if you have done network analysis and analog electronics, it will be a cakewalk for you. Just finding the Thevenin equivalent, nothing else. Here we started this 0.8 R, then RR comes in series, 2R, 2R, 0.4, and then R plus R, 3R, 0.4 here. This is 3R, this is 3R. So what you are going to get? Minus 0.4 volt, right? You are going to get minus 0.4 volt. So once you are done with op-amp and once you are done with analog electronics and network analysis, after that it will be very easy for you. Okay, it will not be that difficult. So simply your output will be minus 0.5 volt. So do not think that this question is based on DAC or anything like that. Simple op-amp based problem it is. Output is becoming minus 0.5 volt. Let's solve this particular problem. You need to find the current through resistance R. Solve it on your own. R and R, 2R, 2R and 2R, it will be R. R plus R will be 2R. So here what do I see? This is your 2R, this is your 2R, and this is voltage V. So this will be your V by 2. V by 2, this will be your V by 2, and 2R, 2R in parallel will give me R. Okay, so here I am getting V by 2 in series with R. V by 2 in series with R. So R, 2R, 2R in series with 2R again, because here I am going to find Thevenin now. So here I am going to get V by 4 and resistance will be what? R. So what is my circuit? V by 4, resistance R is there, then another resistance 2R is there. Okay, then there is an op-amp, this is grounded, and this is resistance R. Okay, this is your V naught. So virtual short is there, this will also be 0. So what will be the current here? V by 4 divided by 3R, V by 12R. The same current is flowing here. V by 12R is flowing in this one as well. So this is your current I. So current I is equals to V by 12R. There you go. Okay. Very easy question. V by 3R, sorry, V by 4 divided by 3R. Let's write it down here. V by 4 is the voltage, total resistance is 3R. So V by 4 divided by V by 12R simply. So I is equals to V by 12R. This current is V by 12R. Let's solve this question. Will you solve this question by voltage? Will you solve this particular question by voltage? In all the questions, our voltage was applied here. Remember this thing? Here. 2R was there. Here was voltage applied. Here voltage is applied here. Reference voltage is here. So this question will be solved by current. Okay. In these, our voltage was divided. V by 2, V by 4, voltage was divided. Here current will be divided. So I tell you a very simple trick. Whenever you see any problem in network analysis, analog electronics, or anywhere in your question paper, if you see a problem and your voltage V, let me use different color of pen. If your voltage V is not directly connected to a series resistance, but it is connected like this, your complete voltage V is coming across this resistance, then always solve the problem by current. Are you getting this point? If this would have been the scene, R and voltage V, then I would have find Thevenin here and would have proceed. Okay, Thevenin here, so what will be Thevenin? V by 2, and what will be the Thevenin resistance? R by 2. I would have proceeded in this manner. But if this is the case, that my complete voltage is exposed to this resistance, complete V voltage is exposed to this resistance, always solve that problem by current. That would be very easy. And these kind of questions you should be solving by voltage. It would be very easy. Okay, so if the voltage is there in parallel to a resistance, that means complete voltage is exposed to a single resistor, then solve that problem by current. Well and good. Okay, solve that problem by current. That means I will assume that I current is getting out of this battery. Capital I current is getting out of this battery. Now what do I see? If this is 0, this is also 0. Virtual short is there. This is also 0. Right? So here what will happen? R to R will come in parallel. So 2R to R will become R. Then R and R will come in series. Are you getting this point? Both are grounded, right? If this node is X, between X to ground you are having 2R. Between X to ground you are having 2R. So 2R and 2R are in series, parallel. What do you mean by parallel connection? A to B you are having R, A to B you are having R. Then you say it is R by 2. X to ground you are having 2R, X to ground you are having 2R. So from X to ground you are having 2R parallel with 2R. That means X to ground you are having R. Okay. So now equivalently this resistance is replaced by R. Okay. This resistance is replaced by R. Now R and R, this complete resistance will become 2R. Now 2R in parallel with 2R, again it will become R. Now R and R, it will become 2R. 2R parallel with R, it will become R. Now R and R, again 2R. 2R parallel with 2R, it will become R. So what did you understand here? That till here what did you understand? That all this resistance can be replaced by 2R only. We are not finding Thevenin equivalent here. We are finding resistance, equivalent resistance we found. 2R, 2R, R, R, 2R, 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 R, R, 2R, 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 R. And R, 2R. So this is what we have found. That across V we are having 2R and 2R. This is what we have found. Now if I current is there and what do we see? This is my 2R. So across V I am having two resistance, 2R and 2R. So how much current this resistance will drive? I by 2. This resistance will drive I by 2 current. And where will be the next current going? Like from I by 2 current is flowing here, rest I by 2 current will be going here. Now what was the equivalent resistance of this? This was also 2R. You can again check 2R, 2R, R, R plus R, 2R, 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 R, R plus R, again 2R. So equivalent of resistance of this was also 2R. So this I by 2 current sees 2R and 2R again. So here half current will go, rest half current will go here. Now what about this? This is 2R, this is also equivalently 2R only. You can check 2R in parallel with 2R will be R, R plus R, 2R. So if this is I by 4, this will be I by 8 and this will be I by 8. And here you can check 2R, 2R in parallel. So this will take I by 16 and this will take I by 16. Say yes or no. Right. So from here what did you get to know? That your small I which you need to find, that is equals to I by 16. Now what is your I? Do I know potential here? That is VR. So VR by 2R, VR by 2R, VR by 2R is equals to I by 2. Say yes or no. VR by 2R is equals to I by 2. So VR by R is equals to I. So what is your small I? Small I is equals to VR by 16R. Did you understand this point? VR by 2R is equals to I by 2, I is equals to VR by R. So from there I is equals to VR by 16R. What is your VR? 10 volt divided by 16 into 10 kilo ohm. Okay, so 1 by 16, 62.5, it should be 1 by 16. 1 by 16 कितना होता है? Calculation में मैं कोई risk नहीं लेता हूँ भाई कभी. I never take risk in the calculation. So 62.5 microampere. I do all the small calculation with calculator only. Okay, so from here I am getting 62.5 microampere. Next, what they are asking? What is the output voltage V naught? Now, for output voltage V naught, if I know this current, let's just call this current as IF. So what will be my V naught? This node will be 0 only. There is no doubt about that. This node will be 0. So what will be my V naught? V naught will be minus IF into R. right? Minus IF into R. Now what is the value of IF? So IF is I by 4 current is coming from here, from this branch I by 4, and from this branch I by 16 current is coming here. So what will be this current? I by 4 plus I by 16, and both current combined will be going in the resistance R, because input of op amp will drive 0 current. So the current will be I by 4 plus I by 16 into R. Okay, so what that would be? 4 if I multiply here, 5 I by 16 into R. And do you know the value of I? Do you know the value of I? I is VR by R. So I is VR by R. So minus VR by R, 16R into R. So answer is minus 5 by 16 into VR. So what that would be? Minus 5 by 16 into VR. So 50 by 16. 50 by 16. So minus 3.125. Minus 3.125 volt. Okay. It was a simple question. Just one. Why did I pick this question? Just I wanted to tell you, whenever the complete voltage is exposed to a resistance, always solve the question by current. And if there is a series resistance with the voltage source, then solve the question by voltage. Okay. So that way it will be easy for you. So this way we have solved and you are getting our final output. So use of Thevenin equivalent is very useful here. Right. Let's go to the next one. Okay, this question is designed by me only. So here we are considering offset. So what they are saying, the given op amp is having an offset current of 100 microampere. It is having an offset current of 100 microampere. What do you mean by input offset current? This current is 100 microampere. So let's not make it here. Okay. Now find the output range for the input 101 and take R equals to 1 kilo ohm and Vref is 5 volt. Vref is 5 volt. Take R equals to 1 kilo ohm. Try doing it on your own. Make the circuit. 101 you need to take. So this will be connected to 5 volt. This will be connected to ground. This will be connected to 5 volt. So first make the circuit. It will look something like this. 5 volt, ground, and these are there. And input offset current is 100 microampere. This is your input offset current. So if all these were 0 because of offset only, now I am going to apply superposition theorem. Now this is a simple circuit you need to solve and you need to tell me the final answer of V0. That's it. This is what they are asking. Find the output range. Output range means what will be the range of output. So you just need to find the V0 voltage. So what will be your V0? Because of the offset. Because of the offset. What will be your V0? 100 microampere current will be flowing here. So I will write 100 micro. Only offset I am considering. So all these sources are gone. This is also grounded. This is also grounded. If I am considering only offset. So all these will be grounded. This will be 0. This will be again 0. So only output will be 100 microampere into 5 kilo ohm. If you have studied op amp, then you can solve it very easily. If you haven't studied op amp, then you can study the op amp. Then later on you can come to this question. Okay, it will be very easy for you if you have studied op amp. Otherwise you may feel like that, sir, what you are doing. But you will feel like that in complete lecture if you haven't studied analog electronics or op amp chapter at least, or Thevenin equivalent, because these are highly used here. And that I cannot teach right from the scratch, right? Because that will be needless. So if you have studied, then it will be all easy for you. 100 microampere into 5 kilo ohm. But always, whenever I consider offset, I will always put plus minus sign. Do you remember this thing? Even in the analog electronics, I told you. Even in digital electronics, I told you. Whenever there is offset, always take plus minus sign. So what you are going to get? 5 into 10 to the power 3, 10 to the power 4. So plus minus 0.5 volt. This is your offset. This is your output offset voltage. That is plus minus 0.5 volt. So your actual output can vary from, okay, should not remove it. Your actual output can vary from plus minus 0.5 volt. Now what is your actual output? That you can write down by considering these two sources. So I will directly write it down now. 5 volt, I am already considering this 5 volt, I am considering this as ground. So from 5 to here I will get 2.5, here I will get 2.5 by 2, and here I am going to get 2.5 by 4. Okay, 5 to 5 by 2, 5 by 4 and 5 by 8. So 5 by 8 into whatever the Thevenin resistance I get, that will be of no use because this will drive 0 ampere current. So directly into 1 plus Rf by R. 1 plus Rf by R. 1 plus 5 by 6. sorry 1 plus 5 by 1, that would be 6, plus if I consider only this 5 volt and this as ground, if I consider this as ground, so what will happen? This will be R, R, this will be again R, this will be again 2R. So this will be 2R and 2R in series, so this I will get 2.5. So I am gonna write 5 by 2 into 1 plus R by R, that would be 6. So what you are getting? 5 by 8 plus 5 by 2, 5 by 8 plus 5 by 2, that is 2.5 into 6, 18.75, 18.75 volt. Okay, so this is the V0 output you are getting, but this is not the complete. This is because of the bits I am writing, because of the bits. What is the final output? V0 you are going to get 18.75 plus minus 0.5. This is the final output of V0. And what will be the range of V0 now? V0 range, that will be 18.75 plus 0.5, that would be 19.25. Let's write down the least value first. So 18.25 volt to minus 0.5, 18.25 to 19.25 volt. Okay, so that's the range of V0. So that's it about your deck. Very easy topic, very straightforward. Only formula you need to remember, V0 equals to R into D. Otherwise, just solve the problem whatever that is given in the circuit. You have all the concept clear. I hope you enjoyed it. So that's it about our deck. We can solve more problems that we will solve when we see the assignment. Okay then, thank you very much. Hi everyone, so we have already studied digital to analog converter. We have studied our deck. Now we are going to start analog to digital converter. So ADC we are going to study now. So what deck was doing? A digital word was the input and analog value was the output. Now what ADC will do? It will take analog value as the input and will give digital word as the output, or you can say bit stream as the output, right? But there are some prerequisites. In DAC, when we were studying DAC, we were using op-amp as an amplifier, inverting amplifier or non-inverting amplifier. We studied about weighted resistor type DAC and R2R ladder type DAC. So there we were using op-amp as an amplifier. But in ADC, we will use op-amp as a comparator. Okay, what do you mean by comparator? Very simple thing. If the positive voltage is greater than negative voltage, then your output will be 1. And if positive voltage is less than negative voltage, then your output will be 0. Okay, very easy. 1 means active high. I should not say active high, logic high. And 0 means logic low. If you have already studied analog electronics, then you would know that output will be plus Vset or minus Vset, plus saturation voltage or minus saturation voltage. So plus saturation voltage is represented by 1 and minus saturation voltage is represented by 0. Okay, so that's the scene. This is an ADC. Now in the next slide, in the upcoming slide, I will be using a block that is sample and hold. So those who have studied this circuit, they would know what is sample and hold circuit, but those who haven't, so let me explain you. What do you mean by sampling? So this is a pure sinusoid signal that you know. Okay, sinusoid signal it is. It has a time period of 2 seconds, right? Time period of 2 seconds, or you can say frequency of half second. Now if I say I am sampling this particular sinusoid signal, I am sampling this particular sinusoid signal at a sampling frequency of 4 Hz. So what does that mean? Sampling frequency is 4 Hz. Fs I am writing, that is 4 Hz. That means what will be my sampling time? That would be 1 by 4 seconds. So it means that after every 1 by 4 seconds, I will be capturing the input value. I am sampling this particular waveform. So what does that mean? My sampling frequency is 4 Hz. So after every 1 by 4 second, I will be capturing the input value. This is your 0. This is your 0 second. This will be, if this is 2, this will be 1. And this middle one will be half. So this will be your 1 by 4. This will be your 3 by 4. So how I am going to capture? This is 0. So after 1 by 4 second, I will be capturing this. This is at 1 by 4. After another 1 by 4, 1 by 4 plus 1 by 4 will be 1 by 2. Then I will be capturing this. Then another 1 by 4, I will be capturing this. Then another 1 by 4, I will be capturing this. Then another 1 by 4, I will be capturing this value. Another 1 by 4, I will be capturing this value. Another 1 by 4, I will be capturing this value, and then this value. In that manner, I will keep on capturing. Right? Okay, the same cycle will keep on going. Now if I say this is sample and hold, sampled and hold, what does that mean? That means that initially 0 value was captured, nothing was captured. At 1 by 4, what was captured? This value was captured. I don't know what is this value. Let's just say this value is some a. So this value is captured at 1 by 4. Now next value is captured at 1 by 2. So from 1 by 4 to 1 by 2, only this value will remain there. This magnitude is, I am calling this magnitude as x, not x, some alpha. This magnitude I am calling some alpha. So from 0 to 1 by 4, 0 was captured, nothing was captured. At 1 by 4 I captured alpha. After that I will capture this value. So from 1 by 4 to 1 by 2, alpha will remain there. Then at 1 by 2 I captured a new value. So that value will remain there till the next capture. What is the next capture? Next capture is at 3 by 4. Okay, at 3 by 4 I am capturing this particular value, which is equals to alpha only. So at 3 by 4 I am capturing alpha, that will remain there till 1. Then what will happen? Then from 1 to next here till this point I am not capturing anything. 1 plus 1 by 4, that will be 5 by 4, but let's not write down the values because that will make the diagram complex and nothing else. Okay, then from 1 by 4 to this value I am capturing this, and then again this is the way I am capturing. Right, so now this cycle will keep on repeating. This is 1, this is 5 by 4, this is your 3 by 2, this is your 2, 3 by 2 plus 1 by 4, what that would be? 2 minus 1 by 4, that would be 7 by 4. So isn't it somewhat like sinusoid only? This waveform is somewhat like sinusoid only, no? So did you actually got the meaning of sample and whole circuit? Let me give you a practical scenario. What do you mean by sampling? Okay, just see my hand movements. I am moving my hand in this manner. This is not a dance step. Just I am moving my hand in this manner. Okay. Now what do I tell you? That bro, click a picture. Okay, I am moving my hand in this manner. Bro, click a picture. So what did you do? In first try, you first click the picture here, and the next picture you clicked here. Then you show me those pictures. This is the first picture. This is the second picture. Now, do you know how my hand moved? First picture is this, second picture is this. I can tell that my hand must have moved like this, or my hand must have moved like this. Okay, I am not a good dancer, just I am telling, or my hand must have moved like this. Right? You only captured two data, this and this. You only clicked two pictures. Now, what if you click 100 pictures? Okay, I was moving my hands. First you clicked this picture, then you click this picture, then this, 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 and then you combine all those pictures. So how that picture will look like? In this manner only, no? Basically, I am moving and you are clicking the picture. You are clicking the picture with a great frequency. Great frequency means you are clicking the picture at a higher frequency. Higher frequency means in very less amount of time you are clicking the picture. Click the picture, click the picture, click the picture. So in 1 second you are clicking a lot of picture. What do you mean by frequency? How many rounds you take in 1 second? How many rounds you take in 1 second, that is known as frequency. So in one round only you are clicking a lot of pictures. That means you are clicking a picture at a higher frequency. So if you are clicking a picture at a higher frequency, then my hand movement will look like the same that I was doing. This was my video. This is my video. But you are capturing the values. If you are capturing the values at a good frequency, then those photos will look like the same movement that I was doing. The same thing we are doing here. I am capturing the value at 4 Hz. What if I was capturing the value at 1 Hz? That means I will capture the data after every 1 second. So what I would have captured? Initially starting from 0, then after every 1 second, what is the reciprocal of this? That is 1 only. So after every 1 second, then next I would have captured this. Then next I would have captured again 0. The next again I would have captured 0. So I don't know how the waveform would go. This is a simple straight line which is always at 0. So there should be a minimum sampling frequency, right? So that is defined as the Nyquist theorem. The detail of that we are going to study in signals and system. So as per the Nyquist theorem, your sampling frequency should be greater than or equals to 2 times of the maximum frequency of input. Okay. Your sampling frequency greater than or equals to 2 times of the maximum frequency of input. What is the maximum frequency of input here? 1 by 2. So at least your frequency, wait a second, time period is 2. Yeah. So at least your sampling frequency should be 1 second. This is what they are saying. It should be greater than 1 second. Even if you take the sampling frequency equals to 1, then also you are not getting a good waveform. So it should be greater than 1. This is what they are saying. We are taking the sampling frequency here 1 by 4 second. We could have taken 1 by 2 second as well. Sampling frequency as frequency as 2 hertz. Wait a second, what I have written here. This is 1 by 2 hertz. Why I am writing seconds? So this was 1 by 2 hertz. So here we have taken sampling frequency equals to 4 hertz. I could have taken sampling frequency equals to 2 hertz as well. 2 hertz means after every half second I will be collecting the sample. So here, so this is how the waveform will go. Here, then here, then here. This is how I would be collecting the sample. So if I make the sample and whole circuit, it will look something like this. It will be holding here. So yeah, again you can say it is like kind of sinusoid, you can say, but not perfectly sinusoid. But what if my sampling frequency is 100 hertz? So after every 1 by 100 second I am collecting the sample. After every 1 by 100 second, this, in that manner I will be collecting a sample, right? If my sampling frequency is 100 hertz, so after every 1 by 100 second I am collecting the sample, here sample, here sample, here sample. So how will my sample and whole circuit will look like? In this manner it will look like. So it will seem like that it is sinusoid only. It will feel like that it is sinusoid only. So if your sampling frequency is high, that means you are capturing the data in a better manner, right? So that's the meaning of sampling. So just you need to know about sampling and hold. So this is just an extra fact that I told. What do you mean? How much sampling frequency you need to have? Because questions can be asked from it. And why questions can be asked? Because the first block of ADC is sample and hold circuit. Okay. The input of ADC is not an analog signal. Listen to this line again. The input to an ADC is not an analog signal. The input to an ADC is analog value. Okay, here I should have written input analog signal. So why this is required? Think about it. Why this block is required? Let's just say this was my analog signal. This is rapidly changing. At this time your input is, let's just say 2 volt. Next time your input will be 3 volt. Very rapidly it is changing. So what will happen? Let's just say I directly apply this input. That is 2 volt here. I directly apply 2 volt here. What will happen? Now this ADC will take some time to convert it to digital output, right? This ADC will take some time that I will convert 2 to my digital word. I am converting in this manner. Let us say I am converting 2 volt to 2 volt in the digital word in this manner. So it will take some time. But what will happen is that your analog signal is very fastly changing. So just your analog input was 2. The very next second it became 3 volt. Now ADC will take input as 3 volt. It will change the output as 3. So now it will make it 0011. So if the input is very rapidly changing, then there will be error in the output because ADC will not be that fast. ADC is not very fast to give the digital word correctly. Like your applied input has reached to 3 volt or even more. Your applied input has reached to 5 volt, but it is still processing this 2 volt. Your input has reached to 5 volt, but your ADC is still processing the 2 volt. Still it has not given this output. So first it will give this output, then it will process 3, then it will give this output, then it will process 5, then it will give the output of 5. Until then you must have reached to another values. So if analog signal is very fast, right? In case of digital signal, what will happen? In case of digital signal, in DAC, why we were not using this sample and hold circuit in DAC? Because digital signal doesn't change very fastly, right? We were applying bit 1, let's just say 1110. Then what will happen? This bit would be coming from some counter output, right? from the output of counter, this 1110 from any digital circuit it would be coming 1110. So this counter will work after T clock only, no? For the T clock window, this 1110 will remain constant. For next T clock window, again whatever the next comes, like let's just say 1111 is coming, so that will remain constant for the next T clock window. But analog signal has nothing like that. Analog signal, you can see temperature. Temperature is an analog signal. Okay, so that can change very rapidly. But the digital signal will come from a counter or from a digital circuitry, and that will work if it is coming from counter. So till T clock it will remain 1110 only. So there is no issue with that. Are you getting this point? So in a ADC, always the first block is sample and hold circuit. Always remember it. A very good question has been asked in GATE examination on this particular point. Okay, sample and hold circuit, that we are going to solve in assignment or in video lecture. I will see where we will solve. But there this concept I will be using, concept of sample and hold circuit. So a lot of students don't know this thing. They will directly study ADC and they will say that applied input is analog signal. No, applied input is an analog value that is coming from a sample and hold circuit. Are you getting this point? Okay, so that is very important point which is usually missed by a lot of students. So that I wanted to deliver here. Okay, so this is what I have written. If the input signal changes during the conversion, if input signal changes during the conversion very fastly, then the output value V, then the final value D, not V, sorry, the final value D, that means digital word could be erroneous or it can have some error. Okay, and sample and hold circuit is used to sample the input data and hold it for a constant value while conversion is in progress. So what it will do, it will hold it for a constant value. For this particular time, it will hold it there. That your conversion will take place. Okay, let's just say this is 2 volt. So 2 volt is constant from 1/4 to 1/2 second. Until that time, your ADC can work and give you the output. Getting this point? Then 1/2, this is like 4 volt. Then 4 volt is constant for 1/2 to 3/4 second. Then your ADC can work in this particular window, that your ADC can work in 1/4 seconds and give that particular output. Okay, so that's why sample and hold circuit are used. So always the first block is sample and hold circuit. Now we will start studying about ADC. So this was just a basic introduction about the ADC, what ADC will do and what is the first block and what is the meaning of sample and hold. Now we will move towards our first ADC, that is counter type ADC. Very easy, very straightforward. So this is your counter type ADC. Do not worry about this particular block diagram, that sir what is this. You know every block. This is comparator, you know it. This is AND gate, you know it. Counter, you know it. Here, and this is your DAC. So in ADC we will use DAC as well. This is also, you know it. Okay, so let's start the working of this. Let's just say my analog applied input voltage is 5.4 volt. I told you it will be sampled and this will be your analog value, which is VA. So that I am assuming that is my 5.4 volt. Okay, initialize, I will initialize the counter as 0000 only. So this is your initial output 0000. Initializing counter at 000 only. I am assuming by my DAC is having resolution of 1. Okay, so what will happen? This is your DAC output. DAC will give analog voltage at as the output, right? DAC will give analog voltage at the output. This is your VDAC. So this VDAC will go here. So if 00 is applied, resolution is 1. What it will give? 0 volt. So this 0 volt will come here. 5.4 volt here, 0 volt here. So positive value is high. What it will give? 1 as output. And if it is giving 1 as output, 1 into clock, what that will be? Clock only. So clock will be fed to the counter. Now what clock will say? That count up. This is a binary up counter. So clock will say count up. So 0001 has been applied. What DAC will say? 1 has been applied. 1 into 1, I will give output as 1. What is the job of DAC? Do you remember the output of DAC? That is R into decimal equivalent of input. So R into 1, it will give output 1. So what will happen? 1 will go here. 5.4 and this is 1. So 5.4 is more. Again output will be 1. Again output is 1. Then clock will be fed here. Again it will say count up. What will happen? 2 will come. This output will be 2. 2 will go here. Again it will be high. VDAC will be 2. 5.4 is greater than 2. So again this will be high. Again clock will be fed. What clock will say? Count up. 3 will be coming here. 3 will go here. Again it is high. Again it is high. And again clock. again count up. The same cycle is going. Now in the next cycle 4 will come, in the next cycle what will come? 5 will come. So this is your 5. So what will be the DAC output? 5 volt. This DAC output will be going here. So 5.4 minus 5, again it is 1, again clock is fed. Now what clock will say? Count up. So again you are counting up. Again you are counting up. So okay, that was 5, now 6. Again you are counting up. Actually previously I made it 4 by mistake and I called it 5. Okay, here I should have made it 5 only. That 5 is fed, 5 into 1 5, and this cycle was going. Now next will be 6. So from 0 we started 0 1 2 3 4 5 6. Now 6 has come. Now 6 will come, then what will happen? 6 into 1, this value will be 6. This value will be 6 volt. So 5.4 and 6. Now negative potential is high. I should not say negative potential, negative terminal is high. So if negative terminal is high, so what will be the output here? 0. Clock into 0, what that will be? 0 only. Right? So now no clock is fed. So counter will stop. When the input is 0, when the input to the counter is 0, at that time counter will stop, no? Right? So counter will stop. Where the counter is stopping? Counter is stopping at 0 1 1 0. So you applied 5.4 and with respect to that you are getting this output. That is 0 1 1 0. Are you getting this point? So 5.4 is mapped into 0 1 1 0. So this is how your ADC is working. This is known as counter type ADC because you are using a counter here. Okay. 5.4 is mapped into 0 1 1 0. You are using a DAC, all the circuitry was there. So I hope you must have understood that working, right? So we cannot write all these kind of things. Let's not disturb the diagram. Diagram will remain there as it is, but you must have understood the working. This we can keep, this also we can remove. Okay, so all these I have written on the next page, how I have written in this manner. Okay, consider initially we are starting from 0 0 0, considering my resolution of the DAC is 1, 4-bit DAC is there, and this is my VA, that is 5.4. So what will happen? 0 0 0 applied, so DAC output will be 0 only. Now that will be compared with your 5.4. 0 will be compared with 5.4. You will get comparator output equals to 1. This was your clock cycle 0. Basically you started from 0 0 0 0. No clock cycle was applied. Now the first clock cycle is applied. This is the first clock cycle. This was your initial condition. 0 0 0 0. 0 was here. 0 was here. 0 was here. 0 0 0 was fed here. This 0 was fed here. This comparator output was 1. And then clock was fed. So now clock cycle will keep on coming, and just as the clock cycle came, just as the first clock cycle came, this would become 1. Again comparator output is 1 only because decimal equivalent of this is 1 only. Decimal equivalent of this is 2. Decimal equivalent of this is 3. This is 4. This is 5. So this you are able to understand, right? Comparator output is 1 1 1 only. So these are the clock cycle. First clock cycle is coming. Second clock cycle is coming. Third clock cycle is coming. Fourth clock cycle is coming. Fifth clock cycle is coming. In the sixth clock cycle, what did you get to know? That my comparator output has become 0, right? And if the comparator output has become 0, now my counter will not start. Now my counter will not work. So here also you will keep a control signal. Okay. So what happens in this particular ADC is that just as it becomes 0, this will give a signal to this guy that again start from 0 0 0. So again it will go down. This is like a drawback, you can say. Why it is a drawback, that we will see. So just as it gets to know that here this output has become 0, that means now clock is not fed. So there will be some control input that I have not drawn in that particular diagram because that is not important. The thing is, just as this becomes 0, it will give a signal to this start signal that again you need to start from 0 0 0 0. So this way we were going 0 1 2, from I should write 0, then 0 0 0 1 I should write, 0 0 1 0 I should write, 0 0 1 1, 0 1 0 0, 0 1 0 1, and then 0 1 1 0 we got, and then I got to know that my comparator output has become 0. So my counter will receive a signal that you need to start from 0 0 0 0. So that's the thing with this counter. Okay. So generally this is how the circuit is drawn, but there are some control unit as well, okay, which will say whenever it becomes 0, the counter should receive a signal that you again need to start from 0 0 0 0. It's like a clear input, okay. At this time the clear input will become active. You can assume this as a clear input, active low clear input. Until it was high, there was no issue. Just as it became 0, until it was equals to clock. This is not actually a clear input. I am just giving you as an analogy. So until it was equals to clock, there was no issue. Just it became equals to 0. It will give the message to this counter to restart from 0 0 0. Okay. How it is a drawback, that we will see. But this is how your counter type ADC works. I hope you must have understood. Now let's see important points regarding this. Okay. So there will be a term called quantization error. So what do you mean by quantization error? Quantization error is the difference between these two. It has nothing to do with the output, okay. It has nothing to do with the output. Quantization error has nothing to do with the output or decimal equivalent of output. It has nothing to do. Quantization error has, listen to the statement very carefully, quantization error has nothing to do with the output or the decimal equivalent of output. It is simply the difference between these two, VA and VDC. So what will you call? Quantization error is the difference between the applied analog input voltage and the voltage output of, or simply the output of the DAC, VA minus VDC, and it can be shown by plus minus. So plus minus VA minus VDC. Okay. Now considering that DAC has a resolution of 1 volt, what will be your quantization error? Okay. Final quantization error I am asking, like at the steady state quantization error. This is defined at the steady state only. Like basically this DAC output in this scenario only we saw that DAC output will go from 1 to 2, 2 to 3, 3 to 4 and 4 to 5, and at 6 it will stop. But whatever the value it stops at, that we will calculate quantization error. So at steady state only we will define it. Now you cannot say that VA minus 1 will be your quantization error, VA minus 2 will be your quantization error. Your quantization error will be VA minus 6. Condition that your applied input was 5.4. Okay. So let's see one thing. What is that? If my applied input was 5.9, then what would have been your DAC output? So here I will write VDAC. What would be your DAC output and what will be your quantization error? DAC output at steady state. Okay. So if applied input was 5.9, 5.9 would have been the input. Then starting from 0 0 0 not satisfied, 1 not satisfied, 2 not satisfied, 3 not satisfied. Even if 5 comes, then 5.9 is greater than 5. So again it will be 1. If again it is 1, then clock is fed. Okay. This we remove it. Again it will be 1, clock will be fed. When 6 comes, when here 6 comes, at that time this will be 0. Again, at that time this will be 0. No clock will be fed. So at that time what was your DAC output? So when 6 was coming, then this was becoming 0. So 6 was the steady state, right? So 6 was the steady state. Basically, till this point you reached. After that the DAC output again goes to 0, but that was the count, right? Here you got to know that my output has been collected, that is 0 1 1 0. So this was your output collected. So at that time what was your DAC output? It has nothing to do, quantization error has nothing to do with this output. VA minus VDC it is. So at that time what was your DAC output? That was 6. So 5.9 minus 6, the error would be plus minus 0.1. What about the next one? 5.6. For 5.6 only it will stop at 6 only, no? Even for 5.6 as well it will stop at 6. 1 will come, 2 will come, 3 will come, 4 will come, 5 will come. Just as 6 comes, at that time your counter output will go to, the clock of the counter will go to 0. That means counter will stop there, right? Counter will not count up, counter will stop there. So that is the point. So 5.6 minus 6, 0.4. What about 5.1? Even if 5.1 is applied, 1 will come, 2 will come, 3 will come, 4 will come, 5 will come, still your counter is counting up. In the next cycle 6 will come. If the 6 is coming, at that time counter will receive clock equals to 0, and if clock is 0, counter will stop. So again 6. So what is the error here? 0.9. And if input was 5.00001, then 1 will come, 2 will come, 3 will come, 4 will come, 5 will come, still output is, still your counter is receiving the clock. Now in the next cycle 6 will come. If 6 is coming, that is greater than 5.0001. At that time your counter will receive 0 clock. So output will stop there. Right? Counter will stop there. So what is the error? VDAC will again be 6. Error is plus minus 0.9999. So let's not come to any conclusion. We will come to the conclusion later on. So it is nearly equals to 1 only, no? I can say nearly equals to 1. Error is nearly equals to 1. Right? So let's not come to any conclusion. We will come to any conclusion later on. We will see another example. Let's see more things. Maximum detectable analog input value. Very important thing. What is the maximum detectable analog input in the counter type ADC? So this was our scene. I was assuming R equals to 1. Let's just say at the input, if I apply 14 volt, will that be able to detect? Yes. First counter will give 0. This will be 0. Here DAC output will be 0. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's just call it 14.1. Otherwise you will be getting confused. At boundary we will never take. This is 14.1. So 11, 12, 13, 14. Till 14 again you are receiving the clock. In the next cycle, here DAC output will become 15. 15 will go here. Okay. Clock will be 0. Right. 15 will go here. This will become 0. So this will be 0 here. Now counter will not stop. The counter will not count ahead. And you will always be looking at this guy. You will get to know that this guy has become 0. That means this is my steady state output. This is my output. So output would have been 1, 1, 1, 1. So 14.1 you can perfectly measure here. But what if my input was 15.1? What if my input was 15.1? So 0 not happening, 1 not happening, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Even in the next cycle 15 will come. Still this comparator output is 1. So still this guy is 1. So this guy is not becoming 0 anytime. Now in the next cycle what counter will say? You are counting from 0 to 1 till 15 you have counted. This is up counter. So again it will go to 0. So again the cycle will keep on going. So never you are getting this output as 0. Your steady state is when you get this output 0. But you are never getting this output equals to 0. So you cannot measure 15.1. So your VA has to be less than VDAC. Do you agree to this point? Right? Your VA has to be less than VDAC. VA can be 14.99999. There is no issue with that. Because 15 will come, it will make it 0, this will be 0. So yeah, I will get to know that certainly this is my output that I am getting, 15. So it can be 14.99999, but it cannot be greater than VDAC. So VA should be less than VDAC, right? So that I am gonna write. Let's not make any error here. Okay, let's keep it as it is, because this you need to keep in mind. This is the diagram. If you can keep in mind, that's pretty good. If you cannot keep in mind, then what we can do? Okay, but it will be in your mind because that is a very simple diagram. Counter is there which is fed with the clock, that's it, and comparator is there. So we are not doing anything with these things. So you got to know that, you got to know one thing, that your applied input at the comparator, what will be coming. So I will make a diagram here so that you remember it for a longer time. So at the comparator you are having VA and VDC. So at least your VA should be less than VDC, because if it is always high, then this will always be high only, and if this is always high, so counter will keep on receiving the clock. This is what you don't want. Okay, so VA should be less than VDC. And what is your VDC? From where VDC is coming? VDC is coming from DAC, right? DAC is receiving some bits and it is giving you VDC output, right? So what you can write? What will be your VDC? It has some resolution R, so that would be R into decimal equivalent of input. So that would be R into, what will be the maximum decimal equivalent of input? Basically VA should be less than VDC, maximum value of VDC, right? I should have written VA should be less than maximum value of VDC. And what is the maximum value of VDC? VDC max. What is VDC max? That is equals to VREF only. Say yes or no? What is the maximum value of output of a deck? Reference voltage. It has a reference voltage, no? Maximum value of output of a deck is its reference voltage. So your VA should be less than the reference voltage of deck. Reference voltage of your deck, right? And what is the reference voltage of a deck? That is R into D, and maximum decimal equivalent of D would be 2 to the power n minus 1. So your VA should be always less than 2 to the power n minus 1. Did you get this point? Basically here maximum value you can get 15. So at least it should be 14.99999, so that this can become 0 at least. But if it is 15.1, this will never become 0, right? So VDEC, what is the maximum output it can give? That is 15. So by this manner you will be able to remember it, right? You will see that there is a comparator. Okay, this is the analog input, and here I will have VDEC. So counter will start 0, it will give 1, it will give 2, it will give 3, it will give 4, it will give till 15, it will give. So if my input is greater than 15, then my clock will never become 0. Clock will never become 0. And clock never becomes 0, that I don't want, because if clock is never becoming 0, then you are never receiving a signal that you have reached the steady state. Okay, there is no actually steady state. In the next cycle only it will go to 0, but at least here your signal will be 0, here your clock will be 0, here your clock will be 0, and you will get to know that yeah, this is the output I want to collect. Okay, so I told you here there will be control signal which I am not making here, right? So this is the thing which you keep in mind. All the conclusion I will write down, no need to worry. These all the conclusion we will write down. Only 4 conclusion will be there. So let's solve a question now. A counter type ADC use a 4-bit DAC resolution of 0.5 volt. What will be the maximum value applied? What will be the maximum value of analog input that can be applied to the input of your ADC? Okay. So resolution is 0.5 volt now. So what will happen? First 00 will come. First 000 will come. DAC output will be 0. Then 0001 will come. DAC output will be 0.5, right? R into D, decimal equivalent of input is 1, but R value is 0.5. So your output will be 0.5. DAC output will be 0.5. Next DAC output will be 1. Then DAC output will be 1.5. Are you getting this point? First 000 will be applied. DAC output will be 0. 0001 will be applied. DAC output will be 0.5. 0010 will be applied. So decimal equivalent is 2 into 0.5. Output will be 1. So in 0.5 it will go 0, 0.5, 1, 1.5, 2, 2.5. In that manner it will go. What will be the maximum value? Maximum value will be 0.5 into the maximum value of decimal equivalent that can be applied. And what is the maximum decimal equivalent that can be applied? 1, 1, 1, 1. And what is the maximum value of that? That is 15. So maximum value you can receive here is 7.5. So you cannot apply greater than 7.5. Okay. So this is the pure concept, or how you could have solved. The simple formula we have written, that my VA should be less than 0.5 into 4-bit DAC is there, 2 to the power 4 minus 1. So VA should be less than 7.5, because this is the maximum DAC output I can receive, and your analog input should be less than that, because if it is higher than that, then there is an issue. If your analog input is higher than that, then never your clock is going to 0. Okay, very simple concept. Let's come back to quantization error once again. So what would be your quantization error if your resolution was 0.5? Resolution means resolution of DAC. Okay, resolution of DAC. So if the resolution of DAC was 0.5, then what would be your quantization error in these cases? So applied input is 5.4. Applied input is 5.4. Let's talk about these outputs. First 0 will come. DAC output, I am saying 0 will come. Then just now I explained it, 0.5 will come. Then 1 volt will come. Again it will keep on going. 1.5 volt will come. It will keep on going till what point it will go? When 5 volt is coming. When 5 volt is coming, still it is high only, clock is being fed. In the next cycle what will happen? 5.5 volt will come. DAC output will be 5.5 volt. If DAC output is 5.5 volt, what do you think what was applied as the input? 11 was applied, right? If DAC output is 5.5 volt, that means 11 was applied. 11 into 0.5 will be 5.5. So if this is 5.5 volt, then here VC will become 0 and 0 is fed. You will get to know that, yeah, this is my steady state output. So this will be my steady state output. It has a decimal equivalent of 11. So it doesn't mean that you will say that, sir, 11 is applied. You know that the resolution is 0.5. Now your resolution is 0.5. So you would know that 11 into 0.5, something must be near to 5.5 would have been applied. Okay, so that you will get to know. So did you get my point, that where it will stop when DAC output is 5.5? From 0 it will start, 0.5, 1, 1.5. So when DAC output is 5.5, at that time it will stop. Okay. So it was very easy to understand. Just you need to use your brain, nothing else, right? So along with that, I will write DAC output as well, and then I will write down the quantization error. VDAC. So it will stop at 5.5 volt. What will be the quantization error? Plus minus 0.1 volt. For 5.1, where it will stop? At 5.5 only. For 5.1, where it will stop? 5.5 only, no? Because 0 will come 0.5, 1, then 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. At 5 as well, your comparator output will give you high voltage only. But 5.5, it will give you low voltage. So 0.4 volt is the quantization error. What about in this case? 5.5 volt again, because greater than 5 it should be. So what is the quantization error? 0.49999, right? This is the quantization error. For 5.6, where it will stop? It will stop at 6 volt, right? At 5.5 it will not stop, it will stop at 6 volt. So here the quantization error is 0.4 volt. What do you see? What is the maximum quantization error? This is your maximum error. Maximum error. In this case, what was your maximum error? This was your maximum error. So what is the conclusion you are making? Your maximum quantization error is equals to plus minus R, which is equals to resolution, which is equals to Vref by 2 to the power n minus 1. Say yes or no. So will you be able to remember it? That my maximum quantization error in case of ADC will be equals to my resolution only. Say yes or no. Okay, very easy thing. Let's solve a question. A counter type ADC is having 4-bit DAC with resolution equals to 0.5 volt. Find the digital output of the DAC if applied input analog value is 5.4 and 5.7. Do it on your own. Okay. So what will be my DAC output? DAC outputs. That could be 0, 0.5, 0, 0.5, 1, 1.5. In that manner it will go 5, 5.5, 6. Since it is 4-bit DAC, V0 will be equals to R into D. So V0 max, what that could be? My resolution is 0.5. And what is the decimal equivalent? Maximum decimal equivalent, that is 7.5. So it can go up to 7.5. But our inputs are 5.4 and 5.7. So here it will stop. For the first case, DAC output will be, when it will stop, when DAC output is 5.5 volt. Right? DAC output is 5.5 volt. That means what should be my decimal equivalent of input? Decimal equivalent of input will be 11. And what is 11? That is 1011. So that would be my output. Are you getting this point? First 000 will come. Comparator output is still 1. Then it will keep on coming. When the counter is giving you 1010, at that time what is the DAC input? This is the DAC input. So it will say that what is applied? 10 is applied. Decimal equivalent 10 is applied. 10 into 0.5. 10 into 0.5. What that would be? 5 volt. So 5 volt will be fed to the comparator. Here you are having 5.5, 5.4. Here you are having 5. Again it is 1. In the next cycle what will happen? 1011 will come. So that is 11. 11 into 0.5 will be 5.5. Now 5.5 is fed here. So that will give output equals to 0. And that is giving output equals to 0. That means now you will get to know that yes, I have to stop. So 1011. Okay, do the next one on your own. You will get to know what will be the answer. Next will stop at 6. Next will stop at 6. So DAC output will be 6 volt here. Okay, so 6 is equals to 0.5 into D. So decimal will be 12, which will be 1100. So this is the way where you have to think. But I will tell you a simple answer. My analog output will be what? What is the analog input? 5.4 divided by my resolution 0.5, and then I will take least integer function of that. This is your least integer function. Least integer function. So 11.8 I am getting, no? 5.4 divided by 0.8, 11.8. No, sorry, 10.8. What I am doing? 10.8. Least integer function means it will take the higher integer of this. What will be the higher integer of 10.8? That will be 11. So yeah, your answer will be 11. And what is the decimal equivalent of 11? Sorry, what is the binary equivalent of 11? 1011. In this case, what will be the output? That would be, I should not write analog output, sorry, digital output of DAC. Digital output of ADC, not digital output of DAC, digital output of ADC. So what will be the digital output? This we are going to write, okay? In the next slide only we are going to write. So what we are going to see, 5.7 is applied, divided by 0.5 volt. Then what we will get? 11.4, right? And you need to take least integer function of that. What do you mean by least integer? Least integer means higher value having the least integer. Greatest integer means lower value having the greatest integer. What will be the greatest integer of 10.2? Greatest integer function. This is the sign of greatest integer function. That will be 10. That means lower than 10.2. What is the greatest integer? And what do you mean by least integer function? Greater than 10.2. What is the least integer? Greater than 10.2. What is the least integer? That is 11. So this is known as least integer function. It feels like that 10.2 in least integer function should give me 10, but no, we need to get the higher one. Okay, and in greatest integer function you get the lower integer value. So here 11.4 will give you 12. Okay, and what is the binary equivalent of 12? That is 1100. So all the things that we have studied, we are going to compile it. But one more important point is there, that is conversion time. Conversion time. What do you mean by conversion time? Okay. So what is the conversion time? Time taken by analog input to convert to the digital output. Digital word we should say. The analog input, how much time it will take to convert to the digital output. So let's go back to our circuit. We will assume that this comparator is having 0 delay. This AND gate is having 0 delay. This counter is having 0 delay, and this DAC is having 0 delay. Okay, all these delays are 0. So this we are assuming. Now, if my applied input was, what is the first case? If my applied input was 0.1 volt, then what would have happened? 0.1 volt, initial state was 0, 0, 0. This would have been 1, clock would have been fed. So just as the clock is applied, it will receive 0, 0, 0, 0, sorry, it will receive 0, 0, 0, 1. Then resolution I am assuming as 1 only. This 1 will go here. 0.1 and 1. This will become 0. This will become 0. So now you get to know that you need to stop. So how much time you required? 1 clock, right? How much time was required? 1 clock. Okay. For 0.9 as well, at 1 only it will stop. So again you required 1 clock. For 1.9 volt, what will happen? It will stop at 2, right? Decimal equivalent of 2. First 0, 0, 0 will come, not satisfied. 0, 0, 0, 1 will come, not satisfied. 0, 0, 1, 0 will come. So this is coming at, you will say that, sir, this is coming at t equals to 0 only, no? Because this was the initial condition and all are having 0 delay. So just as the clock is applied, this will come. Yeah, but it will remain there for the complete clock cycle. So you will say that you are receiving your output at t clock. Okay, this will come at t clock and this will come at 2t clock. Okay, so 1.9 2t clock, and this is the maximum value you can apply considering the resolution is 1 volt. So this is the maximum value you can apply. How much time it will take? 15 t clock. So yes or no? So what is your maximum conversion time here? 15 t clock. If applied input was 0.1 volt, how much conversion time it would have taken? 1 t clock only. DAC resolution is 0.5. So initial DAC output will be 0, not satisfied. Next DAC output will be 0.5 volt. Yes, the comparator output will go to 0. If the comparator output goes to 0, it will be captured. Same goes for 0.4. If the input was 0.9 volt, then it would be captured at 1. So 1 clock cycle, another clock cycle, 2 t clock. What about 7.4999? Because this is the maximum value you can apply. For 7.4999, your DAC input has to be 1111. Because 1111 will be 15 and 15 into 0.5, 7.5. And at 7.5, this will go to 0. DAC comparator output will go to 0. So how much cycle it took? How much cycle it took? How much cycle it took? 15 cycle. So conversion time is 15 t clock. So whether your resolution was 1 volt or 0.5 volt, your conversion time is becoming 15 t clock only. But the analog values are different. Are you getting this point? If I wanted 7.499 voltage to be detected in this case, when my DAC is having resolution equals to 1, then how much cycle it would take? 8 t clock, right? When my DAC is having 0.5 volt resolution, it will take 15 t clock cycles. When my DAC is having 1 volt resolution, it will take 8 t clock cycle. So now I will tell a statement. What I will say, the conversion time of ADC will not depend on the resolution. No, it depends on the resolution. Now another statement, the maximum conversion time of ADC will not depend on the resolution. Yes, this is correct. This is the maximum conversion time. That maximum it will take 15 t clock. So maximum at 15 t clock you will be receiving your final output. So maximum conversion time does not depend on the resolution of your DAC. Okay, but if you are asking for a particular analog value, that means for 7.499, if I am asking in case of resolution equals to 1 and in case of resolution equals to 0.5, so that would be different. Okay, and the one having 0.5 volt resolution, that will take more time. Okay, but if they are asking what is the maximum conversion time, this is only it is asked. Okay, they will not ask about a particular value or anything like that. They will ask maximum conversion time. So what is the maximum conversion time? What is the minimum conversion time? In first clock cycle you will get to know. So that is t clock. What is the maximum conversion time for a n bit counter type ADC? N bit counter type ADC means the DAC is of n bit. Are you getting this point? They will write n bit counter type ADC. That means the DAC is of n bit. They will write resolution of ADC. That means, what does that mean? Resolution of ADC, that means resolution of the DAC that is used there. If I am saying that my counter type ADC is having a resolution of 0.5 volt, that means the DAC which is being used in the ADC, that is having a resolution of 0.5 volt. Okay, so here n bit again means that your DAC is having n bit of input, right? So what will be the maximum conversion time? That would be 2 to the power n minus 1 t clock. Okay, you can directly see here. If it was for 4 bits, for 4 bits we were writing, did I mention anywhere? No, you need to take 4 bits. For 4 bits we are writing all these things. So you are getting 15 t clock. So 2 to the power n minus 1. Okay, here n was 4, n is equal to number of bits. This you will remember as well, that sir, maximum, if there are 4 bits, that means maximum clock cycle can be coming is 15 only. First clock cycle, second clock cycle, so 000, 001. So maximum 15 clock cycle will come. You will just remember it by counter. that sir there will be a counter and it is having n number of bits as the output. It is having n number of bits as the output. Then how much clock cycle can be applied to it? Maximum clock cycle. First 0 0 it was there, then it could become 1 2 3, then maximum it can become 2 to the power n minus 1. So maximum clock cycle that can be applied is 2 to the power n minus 1 into t clock. So that will be the maximum conversion time. So this is how you are gonna remember it. Average means take the average of both two. Okay, minimum conversion time and maximum conversion time, take the average of both of them. What will be the average? 2 to the power n minus 1 into t clock plus t clock. What will be the average? 2 to the power n by 2. What I am doing is that t clock plus 2 to the power n minus 1 into t clock divided by 2. So what you are going to get? So t clock will get cancelled. So 2 to the power n minus 1 t clock. So like very rarely it is asked, but if they are asking what do you mean by the average conversion time? Average conversion time of your ADC will be, you take minimum and maximum, just take the average then. Okay, no need to remember this formula. You just need to remember maximum conversion time. Minimum you will anyway remember. If they are asking average, just take the average. That's it. Maximum quantization error plus minus resolution. This is equals to resolution. Okay. Maximum detectable analog input. What is that? So for this I will write my VA should be less than R into 2 to the power n minus 1. Okay. And what is the detectable digital output? That is applied analog into input divided by resolution, and take the least integer function of that. So this is just the summary of your n bit counter type ADC. Only these things you need to remember. You will be able to solve all kind of problems. Okay. Very simple thing. Conversion time, very important. Conversion time is very important. Then quantization error will be equal to resolution. Maximum detectable analog input will be this, and how to write down the digital output in this manner. Okay. Let's see this question. For a 8-bit counter type ADC, 1 megahertz clock is applied. Maximum conversion time. So what is the maximum conversion time? Conversion time, that is 8-bit is there. That means certainly it can have 2 to the power 8 minus 1 this much of clock cycle, right? This will be 255 into, if this is the frequency 1 megahertz, so what will be the time period? Reciprocal of that will be 1 microsecond. So 1 microsecond. So what is the answer? 255 microseconds. So this is the maximum conversion time it can take, right? Let's see the drawback now. So I told you this is a drawback, that just as it is detected, it will go down. So let's just say this is my analog input. Now you said that sir, at the input of ADC, you will always apply sample and hold out input, right? This should be sampled, but here you are applying a purely analog signal. I told you one thing, just assume this is sampled at a very high frequency. If my signal is sampled at a very high frequency, that means I will be connecting the dots like this. Sample at a very high frequency, connecting the dots like that. So this is becoming in this manner only. So just consider that it is sampled at a very high frequency. So this is my input, right? Sampled at a very high frequency. So if my input is sampled at a very high frequency, then how would my output look like? So first it will start detecting. This is my VA and this is my VDAC. This is what? This is my VDAC. VDAC. 0 volt, not 0 volt is lesser than this voltage is lesser than this voltage is lesser than this, less. Just as it gets higher, it got to know that yes, output is detected, I will again go to 0. Now what will happen? It will take this much of cycle to detect this value, and these values are not even detected. Right? This value is also not even detected. Only this value was detected. My input signal was sampled at a very high frequency. So my input was changing very rapidly. So first this was detected, but just as it was detected, even though there was a very minute change in the input, this input and this input, there was very minute change, still it was not detected. Again you had to wait for this much of cycle. How many cycles are there? 1, 2, 3, 4, 5, 6. Again you had to wait for 6 clock cycle to get your another output, and this is not even detected. Okay, so this is the drawback. I hope you must have understood. Now it is known as digital ramp type ADC as well. So you have seen the ramp signal, right? This is known as ramp signal. So this kind of ramp output you will get. So it is known as digital ramp type ADC as well. So this kind of name can also be written digital ramp type ADC. Okay, so this is just a fact that I have written. Drawback you must have understood, right? So what we came up with, what is the issue? That it is again going back to 0. But what if when it gets to know that now my clock has become 0, so instead of going completely to 0, it could have gone down, no? Directly a down counter can be used. Then again it get to know that my again clock is 0, again it will go down. Then here your VC output will be 1. At this point your VC output will be 1 because this is your VA and this is your DAC output. So DAC output is low, VC output is 1, again it will go up. Now here VC output will be 0, again it will go down. Here VC output will be 1, again it will go up. So in that manner it will be able to detect better, right? So for that what we are going to do, we are going to change our circuit, and instead of this up counter, we are going to use a up down counter, and the input is directly coming from the comparator. This is your comparator, directly it is coming here. So if the input is 0, if the applied input is 0 here, it will count down. You know the meaning of this up down, right? Up down. If input is 1, it will count up. If input is 0, it will count down. Okay, so let's see the waveform and let's see how it will go. So this is my VA input and how my output will go. One thing you know, what do you know? That if this is your VDAC, this is your VDAC. So if VA is greater than VDAC, I should write here. If VA is greater than VDAC, what does that mean? That VC will be equals to 1 up count. And if VA is less than VDAC, VC will be equals to 0 down count. And what will be your VDAC? R into decimal equivalent of this. I am assuming R equals to 1 only. So 1 into decimal equivalent of this. Okay, so it is starting from 0, 0, 0. So my VDAC will be 0, 0, 0 only. My VDAC will be 0, 0, 0. Then it will go up. Then it will go up. Then again it will go up. Because this is my VA and this is my VDAC. VDAC is still struggling. VDAC is nowhere near to your input signal, that is VA. So until it reaches VA, it will keep on going like this. Don't know how many clock cycles it will take, but it will keep on going like this. It is still less. Now in the next cycle what happened was, it became higher. So here what is the scene? Here what is the scene? Your VDAC is higher than VA. That means now it needs to down count. I don't know wherever it is, 0, 1, 2, 3, 4, 5, 6, 7. It was at 7. Okay, it go to know that here VC is equals to 0. Now what is the job? Count down. So from 7 to 6 it will go. From 7 to 6 it will go. Just as it went to 6, what did it get to know? Just as it went to 6. Here, just as it went to 6. So in this case, your VDAC again became lesser than VDAC is, this is your VDAC and this is your VA. So your VDAC is again lesser than VA. So what will happen? Count up. So again it will count up. Then again it will get to know I will have to count down because VDAC is again becoming 1. Count down. Again you need to count down, right? Again you need to count down because again it is high. So count down. Then count up again. Then it gets to know that count up, but I will have to again count down. Here it gets to know that VDAC is again low. So again I will have to count up. Again it is high. Again I will have to count down. So what did you get to know? That if there is very minute change, then my output is also It's not changing that much. It's not like this case. Okay, it is again coming down, then it is going there. So here it is getting to know that my output will revolve around this only. So this is my final output you are getting. Okay, so that is a good thing, no? You are able to detect this data. Once it has detected once, after that it is not taking much time. If it has detected this guy, then for the next guys it is not taking that much of time. Here it was first, it took this time. This time was same for both of these guys. This time was same, but here again it was taking, then again it was taking the same time. But in this case, what is the scene? Took this time, but after that it is detecting very well. So in this previous case, if they ask what is the average conversion time, average conversion time. So average conversion time, here it was given by 2 to the power n minus 1 t clock, right? You don't need to remember this formula, this is how it came. Please don't get confused between this and this, okay? In the examination, I hope you are not going to apply this formula when they are asking maximum conversion time, because there is very high probability, 99% chances are there that they are going to ask maximum conversion time, not average conversion time. So for maximum conversion time, you will think, okay, there is a counter, n bit of output will be there, n 2 to the power n minus 1 clock will be there. Okay, if n bit of counter are there, you must have studied counter, you know how many clocks will be required to receive the maximum output. So there will be, if 4 bit is there, so 15 clock cycle will be required. So in that manner you will remember. Okay, don't get confused. This is just a fact I am writing. So in this case, they will say that your average conversion time is 2 to the power n minus 1 t clock. Basically, if this was your signal, so then they would say that to detect this particular signal, average time it will take this. But in this case, the average time, the conversion average time will be lesser than 2 to the power n minus 1 t clock. Okay, it is not about the maximum. I am not talking about the maximum conversion time. Okay, maximum conversion time will be same for both. T conversion max, that will be 2 to the power n minus 1 t clock. Maximum conversion time will be same. Maximum conversion time, that would be same. No one can change it, because if applied input is maximum, if applied input is 15, then it will take 15 clock cycles only. So this they cannot change. But the thing is, average conversion time is higher in counter type ADC, and average conversion time is lesser in tracking type ADC. Okay, so this is known as tracking type ADC. So this kind of questions can come in 1 mark. Statement type of questions can be there. So what they are going to write, the maximum conversion time in tracking type ADC is lesser than counter type ADC. Wrong, because maximum conversion time is same, but average conversion time in tracking type ADC is lesser than counter type ADC. Yes, that is correct. So this is the advantage, that average conversion time is less. Okay, so that's it about our counter type ADC. This is the most important slide where everything is written, and then after that we go to know this thing. So this was all the conclusion that we have written. Everything is crystal clear now. In the next lecture, we are going to study about successive approximation register type ADC, SAR type ADC, okay, SAR type ADC, very important, very important. So in the next lecture, we are going to see it, and from a very scratch we will build up, because a lot of guys get confused in this particular topic, but you are not going to get confused. Okay, so let's meet in the next lecture. Hi everyone, so we have already studied counter type ADC. I hope you understood that. Now we are going to study successive approximation register type ADC, SAR type ADC. So what is this successive approximation register? So what is the word there? Register. Register means it will be made from flip-flops. We have studied shift register, CISO, PISO, PIPO, SIPO, all kind of shift registers we have studied. That was made from flip-flops only. Now if it is made from flip-flops, that means it will give us some bit output, because flip-flop can store 1 bit of data, so it will give us 1 bit of output. So let's just say I am saying that this SAR is made and it is giving me 3 bit of output. What does that mean? There would be 3 flip-flops in between. Okay, so in this particular structure there will be 3 flip-flops and they are giving me 3 bit of output. There will be 1 extra input and a clock signal. Okay, now how this SAR will work? Okay, now it can have input 1 as well, it can have input 1 as well or 0 as well. Now if it is having input 1 and clock signal is applied, it is having input 1, this is your input, and clock signal is applied, then what it will do? It will make the bit into action. What is the meaning of this word bit into action? That I will explain. Okay, when we see the example, make the bit into action equals to 1, mix. So only job is this, if applied input is 1, it will make the bit into action equals to 1, that's it. This is its job. If the applied input is 0, it will make the bit into action equals to 1, and it will take the previous bit, write previous bit, immediate previous bit equals to 0. I know you are not understanding this, just hold on to the video for next 15 to 20 minutes, everything will be clear. You will also understand why we are doing so, why we are doing this action, why we are doing this particular thing. For now, you just need to remember there will be one SAR device we will be using. This is not the ADC. First, we are studying about SAR. So that particular, you can say smart device or you can say any device. So this particular block we will be using. What is the use of this block? If applied input is 1, it will make the bit into action equals to 1. What do you mean by bit into action? That you will understand. And if applied input is 0, it will make the bit into action equals to 1 only. Okay, the same thing it is doing, but it will do one more thing, that is, it will take the right previous bit equals to 0. Now let's understand the example. SR is given, which has these 3 state output. I should not say 3 state output. This have a 3 bit of output. Initial condition is 1 0 0. Applied input can be anything, and it have a clock. Okay. Now applied input could be 1 or 0. So taking the initial state equals to 1 0 0. Now we need to make the output tree. What do you mean by output tree? That initial state is 1 0 0. If applied input is 1, where it will go? If applied input is 0, where it will go? So this is how you need to make the output tree. Now actually the SAR should start from 0 0 0 only. Okay. And when the applied input is 1, so what it will do? It will take the bit into action equals to 1. So which will be our bit into action? There are 3 bits. Which will be our bit into action? We will start from MSB. So it will take our MSB equals to 1. So this they have already given that you are starting from here. Actually we started from 0 0 0, then applied input was 1. So it took the bit into action equals to 1. That's it. Now this bit has been already treated. So now this bit will be treated. This 0 will be treated. So this is our bit into action now. This second 0, this is our bit into action. So what it will do? If applied input is 1. So do not do anything with the rest of the bits. 1 0 will remain as it is, 1 and 0. The one which is bit into action, this 0 is the bit into action, it will be 1, and rest all will be as it is. Here, this is the bit into action which is 0. So that will become 1. If applied input is 0, the previous bit will become 0. That's it. So your initial SAR output was 4. What is the decimal equivalent of 1 0 0? 4. Then if applied input is 1, I am going ahead. How much I will go ahead? From 4 to 6 I will go, from to 5 I will go, from 4 to 7 I will go. That I don't know. That I have to analyze. Okay. And if applied input is 0, I am going back. Where I will go? 4 to 3, 2 or 1 or 0, I don't know that. But I will go back. That I know. Okay. Now again, this can have applied input equals to 0. This can have applied input equals to 1. Applied input 0, applied input 1. Basically the scene is, this is our input, this is the clock we are having, okay, and we are having these 3 bit output. So now our output is 1 0 0. If this is our current output and applied input is 1, then where it will go? So now this bit has been already treated. This was treated here only. This bit has also been treated. Now this bit will be treated. Basically this bit will be treated. I should not make the correct here, because in this diagram this bit was treated. Now in this diagram, this bit has been treated, this bit has been treated, this bit has been treated, this bit has been treated. Now this bit will be treated, 0 will be treated. So if applied input is 1, it will take that bit into action equals to 1. All other bits will remain as it is. What about 0 1 0? 0 is treated. If applied input is 1, it will take the bit into action equals to 1. Rest all will be there as it is. No need to worry about that. What if applied input is 0? It will take the bit into action 1, but it will take the previous bit equals to 0. It will take the previous bit equals to 0. What about this thing? If applied input is 0, it will take the bit into action 1, but it will take the previous bit equals to 0. So you are getting the rough idea why we are doing so. Here also you got to know that from 2 to we are moving to 1. So if I am taking the previous bit equals to 0, that means I am moving back. Are you getting this point? If I am taking the previous bit equals to 0, that means I am moving back only. And here I am not doing anything with the previous bit. I am making the next bit equals to 1. So that means I am moving ahead. From 2 to 3 I am going. Where I will move from 2 to 7 I will go or 4 I will go, that I have to analyze. So that I am analyzing. Okay. We will see more examples. It will be more clear to you. Do not worry about that. So from 6 to 5 I am going because applied input is 0 and here I am going to 7. Now applied input could be 1, 0, 1, 0, 1, 0, 1, 0. Tell me one thing, all the bits have been treated, right? All the bits have been treated. Say yes or no. 1, 1, 1, all bits have been treated. This was also treated. So all the bits have been treated. Now very simple thing is there. What is that? If applied input is 1, if your applied input is 1, then this will remain there as it is. And if applied input is 0, it will go back 1 bit. From 7 to 6 I will go. If applied input is 1, remain there as it is. If applied input is 0, go back 1 bit. 5 to 4 I will go. Applied input is 1 as it is. Applied input is 0, go back 1 bit because all the bits have been treated now. Applied input is 1 as it is. Applied input is 0, go back by 1 bit. Okay, so this is how your SAR works. Pause the video, rewatch it. Once it is clear, then proceed in the next part. Okay, I will also pause the video, drink some water, and then we will proceed to the next part. Now we are going to see the SAR type ADC. So now we will start studying about SAR type ADC. Okay, so this is the diagram. You know all the blocks. You know this is a comparator. This is a SAR register, or you can say successive approximation register. This is a DAC. This is a control unit. What do you mean by SOC and EOC? SOC stands for start of conversion. Okay, so no need to worry about this block. You will understand the meaning of this start of conversion, and this means end of conversion. So let's understand this block and let's understand this with the question. Okay, so what they are saying, you assume the resolution equals to 1 and applied input is 4.6. Applied input is 4.6 volt and assume the resolution equals to 1. So what will happen? They do not give any initial state, so we will start from 0, 0, 0. Now from SAR 0, 0 is applied. And this is your Q2, Q1 and Q0. 0, 0, 0 is applied to the DAC. So at the input of the DAC you are having 0, 0, 0. This is your final output. This is my final output. This is where I receive the final output. Okay, which I have made from the green. Same kind of structure that we saw in counter type ADC. Same kind of structure is there. Here we were using counter, but here we are using successive approximation register. 0, 0 will be fed to the DAC. What DAC will do? R into what will be the DAC output? This I am calling V DAC. So that is equals to R into decimal equivalent of the applied input. So 0 into 1 will be 0 only. So decimal equivalent of this is 0 only. Okay. So now 0 and 4.6, which is larger? 4.6 is larger. So what will be the output? 1. So now my output is 1. When 0, 0 was fed, DAC was giving me 0 here. 4.6 and 0 I compared, my DAC output was 1. So if my DAC output is 1, not DAC output, comparator output is 1. So if my comparator output is 1, DAC output is 0, comparator output is 1, then this one is fed to the input of your SAR. What it will do? It will start from the bit into action, which is this. It will make the bit into action equals to 1. So now what will be fed? 4 will be fed. What will be fed to this? 100 will be fed. If 4 is fed, 100 is fed. So 4 into 1, it will give 4 here. 4.6 and 4, which is larger? 4.6 and 4. 4.6 is larger. So this will go to 0 now. Oh, sorry, this will be 1 only. 4.6 and 4. 4.6 is larger, this will be 1 only. So again, it will take the bit into action. Now what is the applied input to SR? That is 1. Applied input to SAR is 1. Here, when the T clock came, then only it started its operation. Okay, applied input is 1, then it will not start the operation. It will start the operation when it will get the rising edge of the clock. So again it will start the operation when it gets the rising edge of the clock. So this is the second T clock. We started from 0 0. When it got the rising edge of the clock, it started the operation. When again it is getting the rising edge of the clock, it is starting its operation. Now applied input is 1. What it will do? Take the bit into action equals to 1. So what it will give now? It will give the output 110. That is being fed to the DAC. Decimal equivalent is 6. 6 is fed here. 4 is gone. What will be the output? 0. Output will be 0. Okay. Now the third clock cycle will come. This bit has been treated, this bit has been treated, now this bit will be treated. Applied input is 0. What it will do? Make the bit into action 1, but the previous bit equals to 0. So we have reached to 1 0 1. Now all the bits has been treated. This bit has been treated, this bit has been treated, this bit has been treated. Now to get the final output, this is not our final output. Okay, this is not our final output. We will have to check back again. Once more we will have to check back. What is the decimal equivalent of this? 5. So 101 is fed here. Look, all the bits has been treated. In the last cycle, what did we get to know? Here all the bits were treated, but again we have to analyze once more. Once more we had to analyze, right? So all the bits has been treated, but once more we have to analyze. So this will give it 5. Which is greater? 5 is greater. So again it will be 0 only. So applied input will be 0 only. Okay, and if applied input is 0, that means you will go to one previous state. That is 1 0 0. You are at 5, you will go to one previous. That is 1 0 0. Are you getting this point? Now if someone asks you how many cycles it took for the conversion, this is your final output. Okay, 4.6 is mapped to 1 0 0. This is your final output. 4.6 is mapped to 1 0 0. Are you getting this point? Now someone will ask you how much cycles it took for the conversion. 4 T clock or 3 T clock? T clock, 2 T clock, 3 T clock. Another cycle you took. Final output you are getting here. So if you see this diagram, you will say that sir, 4 T clock should be the final answer, that you took 4 T clock of the time for the final conversion. Okay, but in 100% of the textbook, okay, even the gate will follow this thing, that they say that this is the time it is taking. Till this point only this is the time it is taking. The final one, this final cycle, they do not assume it as a T clock. That means this is not the steady state. The final state is this. From here to here it will go one more cycle. But in 100% of the textbook you will find that if number of bits are 3, then the maximum time taken or the time taken will be 3 T clock for the conversion. If number of bits are 10, then time taken will be 10 T clock. Look, I am also not sure about the reason behind it, because what do I see is that T clock, and then one more cycle I need to take. After all the bits are treated, one more cycle I will take. All the bits are treated, one more cycle I will take, but I am not sure why they do not consider that. For 3 cycles, for 3 bits they will always say 3 T clock. For 4 bits they will always say 4 T clock, and I am actually not sure about this. Why they do not consider this one more cycle, because one more cycle will be required to get to the final output. So whenever if they are asking in the examination the final output, you will follow this procedure, that once all the bits are treated, again you will see once more. But if they are asking what is the conversion time, what you need to see? You just need to see how many output bits are there. If 4 output bits are there, if these are 4, then conversion time will be 4 T clock. If 5, conversion time will be 5 T clock. Because you will start from here, first you will treat this bit, then this bit, then this bit. If another bit is there, then another bit. So what will happen? It will take 4 T clock of the time, or 5 T clock of the time, or 6 T clock of the time, depending on the bit. But after treating all the bits, one more cycle you will take to get to the final answer. Are you getting this point? So in this question, 4.6 is mapped to 100. Okay, let's solve the next question on our own. Let's remove it all. Now in the examination, I will not be having this circuit, so how I will be solving it, that I will tell in the examination. It will be all written in our theory form, so how I will be solving. Okay. So first I will see that my resolution is 1. So my VDAC will be that will be R into D. And I know one thing, always I just need to make a comparator. Here always VA will be applied, which is in our case 4.6 volt, and here VDAC will be there. That's it. Based on this, I can tell my output. And what is my resolution? Resolution is 1. So 1 into decimal equivalent, that will be decimal equivalent only. So I will be starting from 0, 0, 0. That means this is my SAR output. If my SAR output is 0, 0, 0, that means VDAC will be 0 only. So now what it will compare? 4.6 and 0. What will be the output? I will be getting 1. So with next T clock, if output is 1, what it will do? Take the first bit into action. So it will make it 1. Okay. Now what will happen? 1, 0, 0. This 1, 0, 0 will be fed to the DAC. 1, 0, 0. Let me remove it. 1, 0, 0 will be fed to the DAC. So R into decimal equivalent. What is the decimal equivalent of this? That is 4. So 4.6 here, 4 here. That means one output I will be getting. Another T clock will come. It will take the bit into action, which is this. So it will make it 1. Okay. Now, what is the decimal equivalent of this? 6. So 6 into 1. So VDAC will be 6 now. If VDAC is 6, 4.6 and 6. 4.6 and 6. What will be the output? 0. Next clock cycle will come. Now it will take the bit into action, which is this 0. It will take it to 1, but previous bit equals to 0. Is this my final output? No. Another cycle I need to take. If they are asking what is the conversion time, always it will be 3 T clock. But now I will need to take one more cycle. Okay. So what is the decimal equivalent of this? That is 5. 5, 4.6 and 5. What should be the output? 0. So if 0 is output, you will go to 1 previous state. 1, 0, 0. So this is the final output. So 4.6 will be mapped to 1, 0, 0. So this is your final digital output. Final digital output. But if they are asking the clock cycle taken, that will be your 3T clock only. Even your educator is not sure why this is not taken as a clock cycle. I am also not sure. Okay. Now if they ask you what is your digital output after second clock? What is your digital output after second clock? So after first clock this is the output, after second clock this is the output. So they can ask these kind of questions as well. What could be your digital output after third clock or after first clock? So these kind of questions they can also ask. Okay. Now one reasoning why this is not taken as a clock could be like you are having these outputs, no? 0, 0, 0, then you are having 1, 0, 0, then you are having 1, 1, 0, and then you are having 1, 0, 1. Now after this applied input is 0. It could be 1 as well. If applied input was 1, then where you would have stayed? To the same state. I told you one thing. Here you can see this diagram. In the last, if applied input is 1, when all the bits are treated, when applied input is 1, I will stay there only. And when applied input is 0, I will go 1 back. After all the bits are treated, then I need to perform one task. 1 and 0, 1 and 0, 1 and 0, 1 and 0. If applied input is 1, I will stay there only. If applied input is 0, I will go 1 back. Say yes or no? Understood? So here all the bits are treated already. If applied input is 0, I am going back. And if applied input is 1, I am staying there. So this thing is certain that from here to here, this state must have been already occurred. Look here, 4 have been already occurred. You are getting 1, 0, 0. So this has been already your output. So this might be the reason that they do not consider the final clock as conversion time. Okay, I am not sure about it. In 100% of the textbook, you will always find that the conversion time they will tell as 3T clock. For 5 bits, they will tell 5T clock. For 10 bits, they will tell 10T clock. Why they do not consider the final one could be the reason that this output must have been already occurred. If we stay at 1, 0, 0, that means here I am. If we go to 1, 0, 0, that means here it has been already occurred. So this might be one of the reason. Okay. So, but always if they are asking the final output, you will treat one more cycle. But in the end, I will tell you a trick. You will never have to do this analysis if they are asking the final output. Okay. If they are asking the final output in SAR type ADC, then you do not have to make this diagram. Then you do not have to make this tree diagram. I will just tell you a simple trick. By applying that trick in 1 second only, you will tell the final output. So no need to worry about that. But this is just one of my observation that I am also confused why they do not take the final state. So just I wanted to tell, and this is how the tree will go. So if they are asking after 1T clock, what is the scene? After 2T clock, what is the scene? After 3T clock, what is the scene? So for that, you will have to make that tree diagram. Okay, so we will solve these kind of problems. No need to worry. Now make the clock tree diagram for 6.2. So where we will be starting from? 0, 0, 0 only, right? We will be starting from 0, 0, 0. Let me remove it off. So we will be starting from 0, 0, 0. What will be the decimal equivalent? 0 only. So 0, 1 into 0, here 0 will be fed, 4.6 and 0, which is larger? 4.6 is larger. So output will be 1. So just as it gets a T clock, what it will do? Makes the bit into action 1. So from here to here, this is certain, no matter whatever the input is applied, even if the applied input was 0.1 or 0.000001, if applied input was this, then from 0, 0, 0, where you would have gone? If applied input is this, that means at the DAC you are having, here you are having 0, 0, 0, 0, 1, not DAC, at the comparator. And here what will happen? Decimal equivalent of 0 will come, which is less than this value. So certainly you will have one output. If you are having one output, this cycle will come. So no one can avoid this. From 0, 0, 0 to certainly you are going to 1, 0, 0. The first bit will always become 1. No one can avoid that thing. Okay. So this will always become 1. Now, what will be the decimal equivalent? That will be 4. Now 4 and 4.6, which is larger? Not 4.6. Now the scene is, it is 6.2. Sorry. Now the scene is 6.2. 6.2 and here you are having VDAC. So 4 and 6.2, which is larger? 6.2 is larger. So again output will be 1. Just as the another clock comes, it will take the bit into action equals to 1. Or what you can say, that sir, if applied input is 1, then it is happy with this analysis, that it is happy with this bit 1, 0, 0, it is happy. Now it will take the next bit also equals to 1. Are you getting this point? Let's take this case. When applied input was 6 and output was 0. So it is not happy with this configuration. What it will do, I will take this as 0 and now I will try to take next bit 1. When next bit became 1, 1, 0, 1. So 4.6 and 5, again output was 0. So again it was not happy with this analysis, that you do not take this bit as 1. So again go back and you come to 1, 0, 0. Are you getting this point? If just one more approach I am trying to give. One more approach I am building. What is that? If 1 is coming, I am not sure what is my bit into action, but I know one thing, that if output 1 is coming, then he is happy. Comparator is happy, then what it will say, SAR is happy. SAR is happy, what it will say, take the next bit equals to 1. This is already 1, take the next bit equals to 1. So that will be 1, 0, 0. Now, what is the decimal equivalent? 6. 6.2 and 6. What is the output? Again output is 1. Again output is 1. So I am at least happy with 1, 0, 0. Now what I will do, I will take the next bit equals to 1. So next bit equals to 1. So how many clock cycles has come? Here I should stop, but I will go with one more cycle. I will go with one more cycle. So what will be the decimal equivalent? That would be 7. So what it will say? 7, 6.27, output will be 0. Output is 0. So what it will say? No, I am not happy with this decision. That you made it 1. I am not happy with this decision. You made it back 0. Or you can go to the analysis that we have studied. First, this bit will be treated. Then this bit was treated. Then this bit was treated. Now, all bits have been treated. If applied input was 1, I would have stayed there. If applied input is 0, I will go 1 back to the previous state. That is 1, 0, 0. So I will go 1 back. So from 1, 1, 1, I will go 1 back. So from 7 to I will go to 6. That's it. Okay, so 6.2 will be mapped to what? 1, 1, 0. 6.2 will be mapped to 1, 1, 0. So this is how we do the analysis. I hope it is getting cleared. In this example, everything will get cleared now. Yeah, so let's solve this question. So SAR type ADC is there. Resolution of DAC is 0.5 fold. 4 bit. Okay, you are having 4 bit SAR type ADC. It could be written, it is 4 bit SAR type ADC. Resolution is 0.5 fold. VA is 5.3. So basically you need to treat 5.3. Your applied analog input is 5.3 volt. Okay, this is what you need to treat. This will be at positive terminal and here you are having VDAC. But what is your VDAC now? My output of VDAC is R into D. R is 0.5 into decimal equivalent. This will be my comparator output VC, I can say, and that will be fed to SAR. So I hope the diagram is clear. In the previous scene, in the previous counter type ADC, comparator output was going to a AND gate and clock was there. If it was 1, then clock was fed, otherwise it was 0. So I hope that is clear in your mind. So now from where we will start? We will start from 0, 0, 0, 0. 4 bits are there. Mark this thing. 4 bits are there. So what is the decimal equivalent? 0 only. So 0 into 0.5. Here 0 will be fed. 5.3 and 0. Which is greater? 5.3 is greater. So what will be the output? 1. So 1 is fed to SAR. If 1 is fed to SAR, what it will do? It will take the bit into consideration. Will make it 1. Rest all will be 0. This will be the first clock cycle. So 1248. 1248. So decimal equivalent is 8. 8 into 0.5. This will be 4. So VDAC output will be 4. 5.3 and 4. Which is larger? 5.3 is larger. So again output is 1. So what it will say? That I will take the bit into consideration equals to 1. Bit into consideration or bit into action equals to 1 and rest all will be 0. Or how you can assume that I am happy with 1 0 0 0 at least. I am happy with 1 0 0 at least. Now I will take this bit equals to 1. Because your applied input is 1. SAR will say that my output is 1 0 0 0. Now applied input is 1. So at least certainly the number would be greater than this. So I will take 1 1 0 0. Now I will again analyze. If the number is greater than this, then I will again make the next bit equals to 1. And if number is lesser, then I will take this decision was wrong. This decision to taking this bit as 1, that was wrong. So I will take this as 0 and I will try to take next bit as 1. So this is how your SAR will behave. Are you getting this point? So what your SAR will say here, or you can take this approach as well, that take one by one. First I consider this bit, then I am considering this bit, now I am going to consider this bit. So take one bit, or actual approach is, what will be the decimal equivalent of this? 1100. That would be 12, but 12 into 0.5, so VDAC will be 6. So 5.3 and 6, which is larger? 6 is larger. So output will be 0. So what your SAR will say, that taking this bit as 1, that was the wrong decision. So what I will do, I will take this bit as 0 and take the next bit as 1. Or how you can solve it, that this is my bit into consideration and applied input is 0. So I will take the bit into consideration equals to 1 and previous bit equals to 0. So this is just a method, and what actually happened was that it said that to take this bit as 1, that was a wrong decision from my side. So I will take this bit as 0 and I will try to take the next bit as 1. Now I will again analyze. So what it will again do? 1, 2, 4, 8, this is 10. So what is that? How many cycles have come? 2t clock, 3t clock. One more cycle will come because 4 bits are there. So what is the decimal equivalent of this? 10. 10 into 0.5, VDAC will be 5. Here I am writing VDAC. VDAC is 5. So 5.3 and 5, which is larger? 5.3 is larger, right? So again output will be 1. So again one more clock cycle will come. Okay. So output is 1. What it will say, that at least I am happy with this. I will take after this I will take this bit as 1. So this should be our final output, but no, this is not our final output. We will again take one more cycle. So what is the decimal equivalent of this? This is 11, that is 5.5. Okay, decimal equivalent of this 5.5. Now 5.3 and 5.5, which is larger? 5.5 is larger, so applied input will be 0. So if it is 0, I will go back one state. All bits have been treated, I will go back one state. So I have told you two methods. One is the trick, other one is the actual thing what is happening. What is the actual thing happening? From here to next state I need to go. I got the output equals to 1, or I can say I got the SAR input equals to 1. So what SAR will say, that at least I am satisfied with this thing. That at least I am satisfied with 1010. Now I will go to I will increase it. So how I will increase it? From 10 to 11 I will go. Someone will say that, sir, why you did not increase it in this manner? No, I will increase one by one. No, here how did I increase? 1100. Applied input was 0. So I need to go back. So how will I go back? I will make this bit as 0 and next bit as 1. I need to go ahead I need to go to the maximum. From 0 0 I need to go to the maximum. I will go to 1 0. Now I got to know that I am not satisfied with 1 0. What I will do? I will take this as 0 and make the next bit as 1. If I get to know that I am satisfied with this, then it is okay. If I am not satisfied with this, what I will do? This 0 is already there, 0. I will take this as 0 as well. First I am starting with maximum, that is 1 0. Are you getting this point? This is how I am proceeding. So this is the core concept which I want to do, which I wanted to give here. Otherwise you can directly consider that take bit into action one by one, take bit into action. So first started with this, then these two bits, then the third one, then the fourth one. All bits are treated, then one more cycle. So this is the final output. Final output 1010. Now if you solve by this method, then it will take a lot of time. Now if they are asking what will be the output after third clock pulse, what will be the output after third clock pulse? 1010. What will be the output after second clock pulse? 1100. What will be the output after first clock pulse? So this they can ask in the examination. For that you will have to make the tree. But if they are asking the final output, how will you make it? How will you write down the final output? What you are gonna do? Final digital output. What did we do in counter type ADC? Analog input divided by resolution. You remember this thing, right? In the last we studied it. And then we took the least integer function. But here we are going to take the greatest integer function. Okay. So this is your greatest integer function. So what is my analog input? 5.3 divided by what is my DAC output? Sorry, DAC resolution 0.5. So 5.3 divided by half, that would be 10.6. Greatest integer function, what is that? Does takes the immediate previous bit. Okay. How you are gonna remember it? That I need to take greatest integer function or least integer function. So because in the examination you get confused that in counter type I need to take least integer, and in what do we say, in this SAR type I need to take greatest integer. So how will you remember this? So to remember anything we always make a trick, right? So now again we are going to make a trick. So if it was counter type ADC, what would have been the scene? 5.3 divided by 0.5. What you will get? 11.6. Where you need to go? In counter type ADC you will get output equals to 12. Right? In counter type ADC you will get output equals to 12. Yeah, here 10 volt is not our final output. I should not write 10 volt. This is not our final output. 10 volt is in the decimal form. I need to take it to binary equivalent 1010. In this case 5.3 divided by, sorry, this will be 10.6. So 10.6, just the next I need to take. For counter type I will get 11 output and binary equivalent will be 1011. So if the same question was asked for counter type ADC, then this would be my answer. If the same question is asked for SAR type ADC, then this will be my final output. Okay. So how you are going to remember? Counter starts from C. If you are getting the grade C, that means you need to improve, right? If you are getting the grade C, you need to improve. So you will have to go to the next integer. And how SAR start? S. And S stands for super. If you are super in your class, if you are the topmost, then what you can do? You can go back. You cannot increase. You can go back. So here I need to go back from 10.6. So this is how I usually remember. In counter type ADC, I am getting the grade C, so I will go ahead. So I will go from 10.6 to 11, and in SAR type ADC I will come back. Just a way to remember, okay? If they are asking the final output, if they are going to frame a good question, they will ask after one clock cycle or second clock cycle or third clock cycle. But if they are asking the final output, it is very easy. In case of counter type, what we did, we remember it, right? Analog input divided by resolution, and then simply we took this output. And in SAR type, what we are going to do? Same formula, just I need to go back. In counter type, I was going ahead. Well and good. So this trick you can write down anywhere in your rough notebook, or you can keep it in mind as well. Counter C starts from C. If I am getting grade C, that means I need to improve. So I will go ahead. I will take one integer larger. And super S, SAR, super, I will go back. Okay. First let's solve this question because this is based on whatever that we have studied just now. So counter type ADC. What is given? 4 bit is given, 0.5 volt, analog input is 6.6 volt. What will be the digital output? Counter type 6.6 divided by 0.5. What you are gonna get? Forget about counter type or anything. Just first divide this thing. 6.6 divided by 0.5. What you are gonna get? Double of this. So that will be 13.2. Counter starts from C. Counter is starting from C. So I need to improve. So from 13.2 I will go to 14. And what is the binary equivalent of 14? 1110. That's it. Starts from S. If I am super, I can come back only. So I will go back from 13 to 13.2. I will go to 13. 13 is this. That's it. Okay. So very simple thing, very simple output. You don't need to analyze everything. In the examination, all this analysis doesn't come. When we are studying the thing, it will feel like that, sir, why I should mug up any formula? I will analyze in the examination. But you will be under pressure in the examination. So these kind of short trick you will find very helpful in your examination. Okay, you are not going to find these things in your textbook. It is just the tricks made so that we can solve the question quickly in the examination and without taking much stress on our brain. Otherwise, I will analyze it. I will start from 0, 0, 0 in the same manner I will analyze it. Analysis I am telling no. But this I am telling because they can ask in between the cycles. Okay. But if they are asking the steady state value, then that's it. That's the steady state value. In between the cycle also now you can analyze input is 1 or 0. If 1 is 0, move ahead. If applied input is 0, then take the bit into action equals to 1 and previous bit equals to 0. This is a very complex topic for a lot of students. Okay, but now we have made it very clear. We have developed the problem solving skills. In the examination, we can solve it. Well and good. Try to solve this question on your own. SAR type ADC, 3-bit ADC, DAC is used having a resolution of 0.54. Yeah. What should be the maximum value of applied analog input? What do you think? What do you think? What should be your maximum value of an applied analog input? Let's come back to this example. Here, 3-bit ADC was there, resolution was 1. So what will be the maximum value I can receive for VDAC? That would be 7 volt. If I apply 8 volt here, what will happen? I will always keep on receiving 1. Let's start. I will start from 0, 0, 0. 0 is greater than 8. 1, 1, 0, 0. 4 is greater than 8. Here VDAC will be 4. 4 is greater than 8. Again I will receive 1. So 1, 1, 0. Again I will receive 1 because this is 6. 1, 1, 1. If it is 9, the same cycle I will have. After that, again I will have to do one more thing. If this is 8, this is 7. So this I will not assume as a T clock. This will be my third T clock. This will be my second T clock. This will be my first T clock. This I will not assume as a T clock. What I will do, what I am going to receive 1 only. So I will stay at 1, 1, 1 only. For 9 as well, I will get 1, 1. For 8 as well, I will get 1, 1, 1 only. So I am not able to differentiate, right? For 7.1 as well, I will get 1, 1, 1. For 8 as well, I am getting 1, 1, 1. So what is the meaning of that? After 7, you are not able to get the correct mapping. That 8 is also mapped to 1, 1, 1, 9 is also mapped to 1, 1, 1, and that I don't want. That is not desirable. So, what is your answer? That what should be the maximum value of VA? The maximum value of VA should be less than VDAC, right? I hope you must have understood. So, it is same as the counter type, exactly the same as the counter type. Okay, so my VA should be less than VDAC, and in this case, what will be my VDAC? That would be 0.5 into the maximum decimal equivalent. So maximum decimal equivalent will be 2 to the power 3 minus 1. So my VA would be less than 3.5. Okay, that is the maximum that we can apply. They are not going to ask this question in the examination. Okay, it is very rare. But as a designer, you should know, or not as a designer, I would say, but you should know that what is the maximum you can apply, because if you apply greater than that, there is no meaning of that, right? Because SAR will always keep on receiving 1, and if SAR is always keep on receiving the 1, the steady state will be at 1, 1, 1, 1 only. So no meaning of that. 8 volt is giving you 1, 1, 1, 9 volt is giving you 1, 1, 1, 10 volt is giving you 1, 1, 1. So you are not gonna apply above 7, right? If you are gonna apply above 7, then you will at least make the resolution better. Better means you will make the resolution equals to 2, resolution equals to 2 or 3. Or what you can do, you can increase the number of bits. So this kind of questions can be asked in an interview, but ADC is also not that famous for interviews purpose as well. Because this is a very basic thing you are studying. Okay, ADC and DAC is a very vast topic. If you ever want to do a course on ADC or DAC, you can go to YouTube and do the course on Shanti Pawan sir by Shanti Pawan sir. So ADC and DAC, that has been greatly covered in that particular course. But what are the prerequisites of that particular course? You need to know signal system. You need to know analog electronics. Because in any analog company you go, in any analog company, there will be certainly a DAC team or ADC team. No chip can work without ADC or DAC. Okay, so that is a vast topic, but here we are studying on a very surface level. If I teach that particular first thing, I am not that comfortable with ADC and DAC. Like no gate teacher is comfortable with ADC and DAC. If we go into the depth, but whatever that is required for that, I am more than comfortable. So that you can already see. But if you go to the depth of DAC and ADC, that is a very complex topic, I would say. The toughest topic of any analog company. The most important team will be DAC and ADC only. Amplifier teams are also important, radio amps are also important, but the most important team, I guess, that would be ADC and DAC, because no chip can work without ADC and DAC. Okay, so yeah, that's it about our SAR type ADC. I just wasted a lot of time of you guys, I guess. They just wanted to give a information about the industry. Okay, so let's solve this question now. 10 bit of SAR type ADC has a resolution of 10 millivolt. What will be its digital output for analog input? This. So what will be my digital output? So what I can say, here I have this formula, final digital output. Final digital output they are asking. So what that would be? 4.365 divided by 10 millivolt. 10 millivolt is 10 millivolt means 10 to the power minus 2, right? So 0.01. So what you are going to get? 436.5, right? 436.5. Where you will go? Ahead or back? SAR, S, super, I can go back only. So where you will go? Go back. 436. So this will be in a decimal. You can convert it to binary. But even if in the examination, if they are asking this question, they will ask only the decimal equivalent. What will be the decimal equivalent of final binary output? And 10-bit SAR type ADC has a resolution of 10 millivolt. Determine that decimal equivalent of the digital output for analog input of 4.365 volt. So they will ask this thing only. No one will ask you to convert in 10 bits. So how you can convert it? That also you know. 436. You will start dividing by 2. We have already studied number system, right? 218. Then again you do, and this you keep on following. So 218 you get. 0 is that. 0 is your remainder. Then again you start with 2, 0 is again your remainder. Again you start with 2, then again 1 is your remainder. In that manner you keep on going. Okay, so 10 bits you will get, and from bottom you will take to up. Just a revision I am giving, number system. Okay, so these are the conclusion for SAR type ADC. This is the maximum you can apply, R into 2 to the power n minus 1, and where n is the number of bits at the input of the DAC. Or you can say output of SAR. Conversion time will be NT clock. So I told you conversion time will be NT clock. Tell me one thing, this conversion time, if my applied input was 4.6, then also conversion time was 3T clock only. If my applied input was 6.2, then also conversion time was 3T clock only. Because always you will go till the last state. In case of counter type ADC, if my applied input was 0.1, then my time was T clock. If applied input was 15, then conversion time was 15 T clock. You remember this thing? If applied input was 14.99, so it was 15 T clock. But here, even if applied input is 4.6, or it is 6.2, or it is 6.5, always the time will be same. So here I am gonna write one thing, that this is the time, but same for all possible analog input. Okay, so in counter type ADC, what was the catch? That you were having different time for all that different inputs. For 0.1, conversion time was T clock. For 14.9, that conversion time was 15 T clock. Here I am not writing maximum conversion time, right? I did not write maximum conversion time. Here there will be maximum and minimum, both are same. Maximum, minimum, both same. because there is no concept of maximum or minimum here. All will have the same conversion time. Okay, so these kind of things can be asked in 1 mark in true or false, that maximum conversion time will be this or minimum conversion time will be this. So nothing like that, maximum and minimum both same. Okay, so I hope all the things are clear about SAR type ADC. One more thing we can write, digital output will be equals to analog input divided by resolution. Okay, and this is your greatest integer function. So this is just the summary, whatever you need to remember from SAR type ADC. And one more thing you need to remember, or one more analysis you need to know, that is, this is how we are going to analyze. If they are going to ask in between the clocks at 3t clock or at 4t clock, so this is how we are going to analyze. Okay, so I will write down one more question here where I will ask the output in between the clock. Okay, so let's write down this question here only. I will pause the video and I will write down the question. So one more question we can see where in between the clock at 40 or at 3rd clock or at 4th clock I will ask you the final output. So let me write it down by pausing the video, then we can see. Okay, so this is the question. 8-bit SAR type ADC is there. It is converting 3.5 volt. Reference voltage is 5 volt. You need to tell the output of ADC at the end of 3rd clock. Okay, 8-bit SAR type ADC is there. 8-bit SAR type. That means the DAC that is used, that is of 8-bit. Right? If they are saying 8-bit SAR type ADC, that means the DAC which has been used, that is of 8-bit. This DAC is of 8-bit. Okay. So we will start from 0, 0, 0, 0. 8 bits are there. Now, what is the resolution here? That we don't know, but we have the reference voltage. So what will be the resolution? Reference voltage divided by 2 to the power n minus 1. So 2 to the power 8 minus 1. Right? You remember this thing? Vref divided by the maximum decimal equivalent, that would be 2 to the power 8 minus 1. But 2 to the power 8 minus 1 is nearly equals to 2 to the power 8 only, no? So I will write resolution equals to 5 divided by 2 to the power 8 only. Why we are doing so? Because calculation will be a bit easier. Let's see. So what is our scene? We are going to have a comparator where one will be 3.5 volt. Here I will be having 3.5 volt. And other input will be VDAC. So if I take the resolution 5 by 2 to the power 255, that would be like a bit complex calculation will be there, but here easily I will do the calculation. Let's see. So here my decimal equivalent is 0. So what will be my VDAC? VDAC will be R, which is 5 by 2 to the power 8 into decimal equivalent. 5 by 2 to the power 8 into decimal equivalent. So here my VDAC will be 0 only, which is pretty known only, which everyone knows. Okay. So after one clock cycle, this bit will be 1, first bit will be 1, rest all will be 0. 1, 2, 3, 4, 5, 6, 7, 8. Now, what is the decimal equivalent of this? What is the decimal equivalent of this? 2. What is the decimal equivalent of this? 4. What is the decimal equivalent of this? 8. You see number of zeros, 2 to the power 3. You see number of zeros, 2 to the power 2. See number of 0, 2 to the power 1. So what will be the decimal equivalent of this? Number of zeros 7, 2 to the power 7. So DAC output we are writing. This is always we write DAC output. So 2 to the power 7 into this value. 2 to the power 7 into this value. So 5 by 2, 2.5 volt. So this value is 2.5 volt. So at one node you are having 2.5, 3.5. What will be the output? 1. So 1 output will be 1. So if 1 is fed, then this has been already treated. Next bit will be 1. 1, 1, then 0, 0, then 4 times 0. 1, 1, 2 times 0. Sorry, 3 times 0. Yeah, 3, 3, 6, one more 0 would come here, no? 3, 0 and 4, 0, right? Yeah. I hope you are understanding this. This bit became 1 and then these 7 0 remain there as it is. So 4, 5, 6, 7 0 remain there as it is. Now next bit becomes 1s and this 6 0 will remain there as it is. Now what will be the DAC output? DAC output will be What is the decimal equivalent of this? That is 2 to the power 7 plus 2 to the power 6. Are you getting this point? How I am writing the decimal equivalent? This will have the place value of 2 to the power 7 and this will have the place value of 2 to the power 6. 5, 4, 3, 2, 1. Are you getting this point? This is, here again I did one more mistake. So here 6, 0 and 2, 1, 1. So this will have the place value of 2 to the power 7. This will have the place value of 2 to the power 6 into 5 by 2 to the power 8. So what you are going to get? This you can solve. 5 by 2 to the power 8 and then 2 to the power 6 will come common. Then 2 plus 1 will be 3. Very simple calculation. What I am going to get? 5 by 4 into 3. 15 by 4. So 3.75. So this I am getting 3.75, which is greater than 3.5. So what output I will get? 0. So taking this as 1, that was my mistake. So I will take this as 0 and next bit as 1 and rest zeros will remain there as it is. 4. So this is your final output. Okay, this is your answer. Did you understand this point? To make the calculation easier, I took the resolution 5 by 2 to the power 8. I should have taken 5 by 2 to the power 8 minus 1, but calculation will be easier. Why is that so? Because I know that I will start from 0, 0, 0, then it will become 1. So the decimal equivalent of this is 2 to the power 7. 2 to the power 7 into resolution, 2 to the power 7 into 5 by 2 to the power 8. That will make it 2.5. That I know it would be somewhat around 2.5 only. It is not exactly 2.5 because there is this approximation I am taking, but somewhat around 2.5. So if it is somewhat around 2.5, so output will again be 1. So if it is again 1, I know one thing. What is that? The next bit I will take equals to 1 again. So here this is already 1, next bit I will take 1. Here output, here 3.75 I am getting, so output is 0. That means taking this as 1 was my wrong decision. So I need to take this as 0 and next bit I will take as 1. So what I need to analyze? 1 T clock, 2 T clock and 3 T clock. This is not my final output. They are just asking the output after 3 T clock. So that's it. This is the output after 3 T clock. This is 2 T clock. Okay, so they are asking the output after 3 T clock. So that I have done here. So this is my final output. So this is how I am gonna do it. Okay, so let's remove it off. Everything is necessary. Let's remove this circle. Yeah, so now it is all clear. So this is the final output. Now in the next lecture we are going to study about flash type ADC. That is a very fast ADC. So we are going to study about flash type ADC that we are going to do in the next lecture. Okay, I will write it down in a better manner because when you read the notes you are not going to understand this. So I will write it down in a better manner, but we'll do it by pausing the video. I hope you must have understood this question. So in the next lecture we are going to study about flash type ADC. Before that we will study about this priority encoder, which we have already studied, just a revision, and then we will start studying about flash type ADC. 1-bit flash ADC we will see, 2-bit flash ADC we will see in the next lecture. Okay, thank you very much. Hi everyone, so now we are going to start studying about flash type ADC. Very simple ADC, very straightforward. The thing is, in this we are not going to use any sequential circuit, we are going to use only combination circuit. So there we will use priority encoder as well. So if you remember priority encoder, you can skip this part, but in 2 minutes only we are going to study about priority encoder. So what is the priority encoder? If you remember this thing, I told you priority encoder is like a button. So if I am not pressing any button, then Y1 and Y0 will be my don't care. Any output can be there, it will be don't care. If I am pressing on denote button, so here I need to see, if I am pressing on denote button, so what is this? 0. And what is the binary equivalent of 0? That is 0, 0 only. If I am pressing on D1 button, I can press on D1 button as well, I can press on denote button as well. If I am pressing on both of the buttons, then what it will say? What is my priority? My priority is D1. So priority is defined by the user. Usually it is D3 is greater than D2, it is greater than D1 and it is greater than denote. So priority is defined by the user. So what is my priority? D1 is priority. So if I have clicked on D1, then do not care about denote. Your final output will be given as the decimal equivalent of 1. So what is the decimal equivalent? 1. If I am pressing on D2, then do not care about D1 and denote. Even if you press on that, if you have pressed on D2, then do not care about these. Your final output will be given as the decimal equivalent of 2. So that will be 1, 0. And if I am pressing on D3, then do not care about the rest. Your final output will be given as a decimal equivalent of 3. That would be 1, 1. So this is how the truth table looks like. Okay, right? So this is our priority encoder. Let's start studying about 1-bit flash type of ADC. So what is that? Here there is one comparator is used, two registers are used. So this will drive 0 ampere current. This I know. This will drive 0 ampere current. So directly I can apply potential divisor. So this will be Vref by 2 here. So if my VA is greater than Vref by 2, what will be the output? 1. And if my VA is less than Vref by 2, my output will be 0. So VA could be any value. Let's just say VA is 6 volt and my Vref is 8 volt. So what I will be having? 4 volt here. So 6 volt is greater than 4 volt. So my final output will be mapped as 1. And let's just say if it was 3 volt. So 3 volt is less than 4 volt. So final output will be mapped as 0. So any value less than 4 volt, any value, any analog value less than 4 volt will be mapped to 0. And any analog value greater than 4 volt will be mapped to 1. That's it. So this is your 1-bit flash type of ADC. So not that efficient, because for 3 volt also you are getting 0, for 2 volt also you will get 0, for 3.9 volt also you will get 0 only. Not that efficient. Then what we did? We came up, we increased the number of bits. So now we are going to study about 2-bit flash type of ADC. Okay, 2-bit flash type of ADC. So this is how we increase it. Now our output will be of 2 bit. Here output was of 1 bit. So you do not need to use any encoder or decoder or anything like that. Now output will be of 2 bit. So what I'm gonna do? I'm using these comparators. All these are comparators, and these are the registers. Okay. So Vref is connected to the Vref is connected to the registers, and these are connected to the negative terminals. So this is your Vref. Very simple concept of network analysis. Resistance R is there, R is there, R is there, and then another R is there. So how will be the drop looking like? This is your R, 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 R. What this drop will be? Vref by 4, right? This drop will be Vref by 2. How I am calculating it? R by 4R into Vref by 4, and this drop will be 3 Vref by 4, 3R by 4R. So this is your 3 Vref by 4. So this I can call as V3, this I can call as V2, and this I am calling as V1. So this is my V3, this is my V2, and this is my V1. Diagram looks more clear now. Okay, and this is your V. Now this will give me 3 bit of output, no? But I cannot design any 3 into that kind of decoder, because decoder is of 2 to the power n into n. So at least I will have to design 4 into 2 decoder, right? So I am design or I should use 4 into 2 decoder. So it will have 4 inputs, 1, 2, 3. So this I will have to keep by default 1. If it is given in the examination, then you can either take 0 or 1. It will be given in the examination whether it is 0 or 1. If it is not given, by default you will take it 1. Okay, by default D0 will be taken as 1 if it is not given. So here it is not given, so by default I am taking is 1. Now if my VA is less than V1, if my VA is less than V1, or you can say if my VA is less than Vref by 4, what will happen then? This value is less than, this value VA, this positive value, let's take example, my VA is, let's just say 6 volt and my Vref is VA is 2 volt. Okay, let's just say my VA is 2 volt and Vref is 16 volt. So what you are going to have here, V1 will be 4 volt, V1 will be 4 volt, and this is 2 volt. This will be 4 volt and this is 2 volt, right? So 4 and 2, which is greater? 4 volt is greater, so this will be 0. Now one thing, what this will be? This will be 8 volt. So if this is 0, then certainly they will also be 0, no? Because all VA is connected to the positive terminal. So all will be 2 volt, 2 volt, 2 volt only. And certainly your V3 is greater than V2 and greater than V1. No one can stop it. So if you compare V1 and VA and you are getting 0, then certainly V2 and VA will give you 0, V3 and VA will give you 0. Are you able to understand this point? That ahead you are going to get 0 only. If this is 0, if D1 is 0, then certainly you are going to get these as 0 only. So all these are 0 here. and by default this is 1. So 1 is priced. So what will be, sorry, 0 is priced. 0 is priced. So what will be the decimal equivalent of 0? 0, 0. So y1, y0 will be 0, 0. Now let's remove it off. Now I'm not going to take example. You should have good amount of aptitude that without even taking the example you can understand. Now all these are VA, VA, VA. Now in the next condition, your VA is greater than Vref by 4, but it is less than Vref by 2. So what about this? Your VA is greater than V1, but less than V2. So here VA is greater. So what will happen? This will become 1. VA is greater. So this will become 1. Here VA is less. VA is less than V2. So this will become 0 and this will also become 0. Right? Because if this is less, if V2 is greater, then certainly V3 will be greater. Right? So all these will be 0. This will be 1. So all these are 0. Here D naught is also 1, but it will give decision with respect to the priority, and priority I will define as D3 is greater than D2 is greater than D1 is greater than D naught. So what is the priority? D1 is the priority. So what is the decimal equivalent of 1? That is 1. In the next cycle, what will happen? This will become 1. Let's check. Now in the next cycle, your VA is greater than V2. Your VA is greater than V2, but less than V3. So if VA is greater than V2, then certainly it is greater than V1 as well. If VA is greater than V2, then certainly it is greater than V1 because V2 is less than V1. So here also it is greater, VA is greater, and here also it is greater. So what will happen? This will become 1. And here V3 is greater, so this will be 0. So 0, 1, 1. And in the next cycle, all will be 1 because your VA is greater than V3. VA is greater than V3, then this will be 1 as well. Okay, so let's remove them off. These are varying, but D naught is fixed, that is equal to 1. So what you are going to get? When D2 is priced, binary equivalent 1, 0. And when D3 is priced, no matter if they are priced or not, my priority is D3. So what is the binary equivalent of 3? 1, 1. So this is what you are going to get. So any value which is between 0 to Vref by 4 will be mapped to 0, 0. Any value which is between Vref by 4 to Vref by 2 will be mapped to 0, 1. Any value which is between Vref by 2 to 3 Vref by 4 will be mapped to 1, 0, and in that manner it will go. Let's take a blind example. Vref I am taking as 8 volt and VA I am taking as 6 volt. Okay. So what will happen? This value will be what? Just in a bit side I can keep it. So this will be Vref by 4. This will be 2 volt. This will be 4 volt and this will be 6 volt. I should not take at the boundary. I am taking Vref equals to 5 volt. Sorry, VA equals to 5 volt. Now this is 5 volt. Okay. So this is 5 volt. This is 4 volt. This is 5 volt. This is 2 volt. This is greater. 5 volt is greater than 2 volt. 1 volt. Sorry, 1 will be the output. 5 volt is greater than 4 volt. 1 will be the output. 5 volt is less than 6 volt. 0 will be the output. So what you are having? 0, 1, 1, 1. So what is clicked? D2 is clicked. So this is my priority. If D2 is clicked, what will be my output? Output will be 1, 0. Y1, Y0. So what is the decimal equivalent of 2? 1, 0. So this will be the output. Okay. So that's how you can write down any output. So your 5 volt is mapped to 1, 0. Is there any limit of VA? Is there any limit that this much VA you can apply? No. Any VA you can apply. 5 is mapped to 1, 0. 7 will be mapped to what? 7 will be mapped to 1, 1. Right? So in that manner, anything you can apply. So there is no limit. Say yes or no, right? So let's move ahead now. So this is just a simple, very simple analysis, very easy analysis. Let's move ahead in our, let's move it off. Let's remove it off as well. Remove this one off as well. So now everything are very standard. Okay. Let's solve some questions. Yeah, one more thing. What is that? Number of registers used. How many registers are used here? 4 registers are used. How many registers were used here? 2 registers were using. So number of registers used are 2 to the power n. If you design a 3-bit flash ADC, okay, if you design a 3-bit flash ADC, you are not going to see For n bit flash ADC, you are going to use 2 to the power n registers. How many comparators will be used? One less than that. So 2 to the power n minus 1. And how many decode? What will be the order of the decoder? That would be 2 to the power n into n. So here you are using 4:2. So one less. You can see the example of 3-bit ADC here. 3-bit flash type ADC. So 1, 2, 3, 4, 5, 6, 7, 8. 8 register you are using. So 2 to the power n. This is your 3-bit flash type ADC. How you are defining this 3-bit flash type ADC? Based on the output. 3-bit of output you are having. So it is 3-bit flash type ADC. 2-bit of output you are having 2-bit flash type ADC. And 1 bit of output you are having 1-bit flash type ADC. So this is how I am defining the ADC. Like based on the output only you define. 3-bit of output. In the previous analysis as well, SAR was giving me 3-bit of output. So I was saying 3-bit ADC. Counter type. If counter was giving me 4-bit of output, I was saying 4-bit ADC. So based on the number of bits at the output, I define the ADC. So here I am receiving 1, here I am receiving 2, and here I am receiving 3. In the next example, if I am receiving 3. So if I am receiving 3, so I am receiving, if I am receiving 3-bit of output, that means it is a 3-bit ADC. Okay. This question we are going to solve. But this you need to remember. Number of registers will be 2 to the power n. Comparator will be 1 less, and what will be the order of the decoder? 2 to the power n into n. You will be able to remember it. Very easy. Okay. Let's see the conversion time. What do you think? What is the conversion time? Just as you have applied VREF and just as you have applied VA, this will become active. Will it be 0 or 1? That I don't know. But this will become active. And if these are active, immediately it will give the output. Say yes or no. Just as you apply, immediately you are receiving the output. So ideally it should be 0. But there can be some delay of these comparators or priority encoders. There will be some delay of comparators, priority encoders, and some register delay can also be there. So practically it will be the delay of register plus delay of comparator plus the delay of decoder. Okay. This is not the ideal, this is the practical case that these delays will also come in action. Now in textbook what you will find? In textbook you will find that the conversion time of flash type ADC is, why it is known as flash type? Because in a flash very quickly it is giving me output. So in the textbook you will find it is equals to T clock. But there is no concept of T clock. We are not even using any sequential circuit. In sequential circuit we use the clock, right? In combination circuit we don't use the clock. In sequential circuit we use the clock. So if I am not even using any combination circuit, so if I am not even using any sequential circuit, so from where this clock is coming? So the thing is, if they are saying the conversion time is T clock, they are assuming that here I am using parallel in parallel out shift register. Do you remember parallel in parallel out? By an analogy we have understood. Parallelly people will come in, so it will take 1 clock cycle, and at the output you will be standing, so you can access all of them. So how much clock cycle you will take? Parallel in parallel out, how many clock cycles are required? Only 1 clock cycle is required. Parallel in parallel out, 1 clock cycle is required. So if at the output you are having this PPO register, parallel in parallel out, so at the output if you are having this register and this is your final output, then you can say that 1 more clock cycle I will require. So in textbook you will find that the conversion time of flash ADC is T clock. So this is what they mean, that output, at the output I am using my PPO register. If you are not using any PPO register, then ideally conversion time should be 0, or you can say conversion time will be equal to these register, comparator and decoder. But at the output if you are using your PPO register, then it will take 1 clock cycle to give the final output, because PPO will take parallel in, and at the output you will be able to access all the data. So to capture the data you are not taking any time, but to insert the data or to proceed with the data you are taking 1 clock cycle. Okay. To insert the data 1 clock cycle was required, so that will be T clock, but to get the output, to capture the data, no clock cycle was required. So T conversion time will be T clock. This could be written. What is the advantage? It is fastest, because conversion time is very less. What is the disadvantage? Bulky I am writing. bulky, and then there will be high power consumption. What do you mean by bulky? That I will explain. Bulky means there are a lot of registers. There are 2 to the power n register. There are 2 to the power n minus 1 comparators, and then there is a decoder as well. In decoder there will be a lot of AND gates, so decoder also there. 2 to the power n decoder is also there. So a lot of components are there. In the previous one, what we were using, comparator, one comparator only, and then there was one SAR type. You can say SAR register was there, or you can say there would be counter. So that will be made from 3 or 4 flops. Then there was a deck. So this was the circuitry. Here you are having a lot of, let's just say if I am making 6-bit flash ADC. So how many register I am going to use? 2 to the power 6. How many comparators I am going to use? 2 to the power 6 minus 1. And then there will be a huge decoder as well. So it will be bulky. Also, these register all will be of R. But practically these registers are not matched. One can be of R, another can be of 1.1 R, 1.01 R, another can be of 1.02 R. So matching these registers is also a very tough task. So if registers are not matched, then you can have the error in the output as well. So as the number of bits increases, the chances of having the error also increases. And if a lot of components you are using, it will be bulky and it will consume a lot of power, because all the elements will consume the power. So power consumption will also be more. So if you want to, let's just say I want to map my 4 in 6 bits, then I am not going to use it. I want to map my analog input VA in 6 bits, then I am not going to use my flash type ADC, because it will take a lot of circuitry. I can use SAR type or I can use any other thing, okay, but I am not going to use this flash type of ADC. So that is the disadvantage. So disadvantage I have already written that, only I wrote that it is bulky. So these things you need to remember, these 2 slides only you need to remember, which is this: number of register used, number of comparator used, decoder, advantage, disadvantage, and what is the conversion time. Very easy thing. Let's solve some questions. Okay, very straightforward topic it is. ADC and DAC is very straightforward. You just need to have a good knowledge of analog. So this I am getting from this particular PPT. This is the name of Professor Tan Nguyen. If I am pronouncing it wrong, I am really sorry. Okay, so he is a professor from University of Singapore. So from his PPT I am getting this particular question. Okay, so credit goes to him. All these slides are made by him only. So from his PPT I got this question. So always credit is necessary. So yeah, this is the problem. 3-bit DAC is given. Determine the binary sequence. You need to determine the output. Basically 3-bit DAC is given. You need to determine the binary sequence of this output. Determine the binary sequence of 3-bit ADC. Did I say DAC? No, it is ADC. I am again and again saying DAC. So 3-bit ADC for the analog input and the sampling pulses analog encoder enable. So these enable pulses are also given, shown there. Draw the resulting digital waveform. So here we are using an enable pulse as well. Okay. So this will be enabled only here. This will be enabled only here. This decoder will be enabled only at these particular time. So what will be our outputs? So very simple. This is our analog input. This is our analog input. But this is not being fed here. This is not being fed here. It will be first sampled and then will be coming here. I told you the first block will be sample and hold block. So how it will be sampled? Before this nothing was there, so 0. Now this value is sampled and it will be held till the next sample. So this we have already seen in the first lecture of ADC. Now this will be sampled, it will be held till the next sample. This will be sampled, held till the next sample. This will be sampled, held till the next sample. So now this waveform is fed to the input of ADC. Right? This waveform is fed. This waveform is fed. Now what we need to do? So here these are the enable input. So first when 0 was fed here, 0 was fed here, no problem. If 0 was fed here, then enable is not even active, so output will be 0 0 only, so no need to worry about that. Now applied input is somewhat greater than 3 and less than 4, so I can assume this is my 3.5. Can I assume it in that manner? What I am saying is that this is my somewhat around 3.5. Okay, somewhat around 3.5. Now this is my 8 volt which is given. So here what will be coming? These are 8 resistor. So 1 by 8, this will be 1 volt, this will be 2 volt, this will be 3 volt. So different color of pen I should use. Yellow will not work. I hope this works. 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt. This will be 7 volt. And what is applied at the input? VA. My VA is 3.5 volt. So all are having 3.5 volt. Okay. Now 3.5 volt is less than 7 volt. 3.5 is less than 7 volt. This will be 0. Which one will be 1? 3.5. This is 5 volt, na? So 3.5 is greater than 3 volt. 3.5 is greater than 3 volt. So this will be active. 3.5 is greater than 3 volt. Here 3.5 is there. So 3.5 is greater than 3 volt. So this will be active. This will also be active. This will also be active. Now 3.5 is less than 4 volt. So this will be 0. Basically your D3, this D3 is active. Your D3 is active. So what will be your output? Decimal equivalent of 3. D2 is also active, D1 is also active, and even D0 will also be considered active. D0 will also consider active. But what will be the output? Since it is a priority encoder, so output will be with respect to decimal equivalent, binary equivalent of 3. So what that would be? 0, 1, 1. So that will be the output. Okay, this is the answer we are writing. Now if the applied input is, this is somewhat greater than 5. If my applied input is 5.1 volt. If my applied input is 5.1 volt. So 5.1 volt will be fed here. Now these inputs are 5.1 volt. Here if 5.1 volt is coming, 5.1 volt is greater than 4 volt. So certainly this output will also be 1. Here if you see 5.1 is greater than 5 volt. So this output will also be 1. 5.1 is less than 6 volt. So this output will be 0. So what do you see? D5 will be active. Are you getting this point? At D5, this is your D5 and this is the comparator. One node of this comparator is connected to 5 volt and another node is connected to the input. One which is connected to the input, that is plus and this is minus. So this will be active 1. Next will not be active. So D5 will be active. So what will be the output? Output will be with respect to D5. So what is the decimal equivalent of 5? Sorry, binary equivalent of 5, 101. So what do you see here? For 3.5, 3 is mapped. For 5.1, 5 is mapped. Okay, so I'm gonna write it. Let's remove it off. So 3.5 is mapped to 3. 5.1 is mapped to 5. Next value is somewhat greater than 6. So how it will be mapped? To 6 only. Next value is somewhat greater than 6 but less than 7. So again it will be mapped to 6 only. What will be the next value? Next value is somewhat less than 5. So it is between 4 to 5. So it will be mapped to 4 only. What about the next one? Between 1 and 2. So it will be mapped to 1 only. Are you getting this point? Between 1 and 2. That means let us say the value is 1.5. So this will be active. This will be active. The value is 1.5. So if the value is 1.5, this will be active but this will not be active. So D1 is active. And what is the decimal equivalent of, what is the binary equivalent of D1? Binary equivalent of D1 will be 0, 0, 1. So here what do you see? Between 1 and 2 it is. So 0, 0, 1 you will receive. Between 0 and 1 it is. So what you will receive? 0, 0, 0. The next one is, at the boundary we cannot comment actually. So I will consider it greater than 0 only. So this is at boundary actually, but at boundary we cannot comment. So let's just say it is 1.01. So it will be mapped to 1 only. What about this? This is 2 point something. So it will be mapped to 2. The next one is Again it is at boundary, I will consider it high only. So if it is 5 volt, so it will be considered as 5 point something, it will be considered as 5 volt. Now this is 6 point something, so it will be mapped to 6, and next one is 7 point something, so it will be mapped to 7. So this is the way output will go. Okay, starting from here to here. I hope you must have understood. These kind of questions will come in your examination if they are asking the question from flash type ADC. Just you need to see that how output is being mapped. Once you realize how output is being mapped, so only for 1 or 2 input you need to analyze. After that you will be able to understand, right? I analyze for 3.5, I got to know that if 3.5 is applied here, let's move it off. Okay, let's all remove it off. Let's not disturb the question. So when I go to know that 3.5 is applied here, 3.5 is applied here. So this is my 4 volt. Here I am having 4 volt and here I am having 3.5. So this will go to 0, but here I am having 3 and here I am having 3.5. So my analog input is higher. 3.5 is higher than 3. So this value I will get 1. So D3 is clicked. So 3.5 is mapped to 011. 5.1 is mapped to 101. So in that same manner, I can see what all values will be mapped. Very easy question. Okay. So nothing tough is there. Just the thing is that this was the analog input and sample and hold we were doing. In that manner, we found the final output. Let's solve the next question. The circuit shown below works as 2 bit of ADC. 2 bit output is there. 2 bit ADC it is. Okay. And what you need to find? You need to find the expression of Y1. What you need to find? They did not even write it. So your V in can vary from 0 to 3 volt. Okay. What will be the expression of Y1? So try it on your own. V in can vary from 0 to 3 volt. So what you will do? First you will write down these inputs. What these inputs could be. So this is my 3 volt. So R divided by, what is the total resistance? 2R, 2R, R, 6R. So R divided by 6R into 3. So this will be 0.5 volt. This is right in the middle. 3R divided by 3R. This will be 1.5 volt. And what that will be? 5 by 6 into 3. So that will be 2.5 volt. Now what will be the range I will define? If V in is less than 0.5 volt, if V in is between 1.5 to if V in is between 0.5 to 1.5, if V in is between 1.5 to 2.5, and if V in is greater than 2.5. So these ranges I will define. Okay. Now if my V in is less than 0.5 volt, so here only 3 inputs are there. So this I will assume as 1 only. X naught I will assume as 1 only. Okay. So if V in is less than 0.5 volt, what will happen? If this value is less than 0.5 volt, so this will be 0, this will be 0, and this will be 0. So all these will be 0. If V in is greater than 1.5 volt, sorry, if V in is greater than 0.5 volt but less than 1.5 volt, less than 1.5 volt, less than 1.5 volt, so this will be 0, but this will be 1. So in that manner, this analysis we have already seen. What will be your Y1? So here decimal equivalent will be 0, 0. Here decimal equivalent will be 0, 1, and here decimal equivalent will be 1, 0, and here decimal equivalent will be 1, 1. So what is the expression of Y1? How you are going to write it? From here directly? That sir, my expression will be x3 bar into x2, x1, x0 plus x3 into x2, x1, s0. So I will take x3 this as common. So my final answer will be x2, x1, x0. Wrong. Why is that so? Why it is wrong? Why the expression of y1 is wrong? Because you did not think about the other combination. No. Other. What about the other combination? These are only the 4 combination. Rest all combination will be your don't care. Say yes or no. Are you getting this point? So you need to care about the don't cares one as well. But one thing is for sure. What is that? That x0 will be equals to 1 always. Because that is by default. This will be equals to 1 always. So now I am gonna make the K map, but I am not gonna include x0. Because this K map I am drawing considering that my x0 is always 1. Because this will always be 1. So I am drawing the K map, but I know one thing, that my x0 is always equals to 1. So that I will ignore and rest values I will take. So this is my x3, x2, x1. Do you remember the 5 variable K-map? The same concept we are using. There we consider one as 0 and another one as 1. So here I am ignoring the x0. I will only take these as these in consideration. So I will take these in consideration. Now tell me one thing. What will be the minterm of y1? What I am considering? Considering x0 is 1. Considering that x0 is 1. Now this is of 3 variable only. x0 is always 1. I am not gonna consider x0. This will be my final expression, that with respect to 0 0 0, this is my final combination. With respect to 0 0 0, I am getting 0. With respect to 0 1 1, I am getting 0. With respect to 0 1 1, I am getting 1. And with respect to 1 1 1, I am getting 1. Are you getting this point? x0 I have fixed it. So this minterm I will call it 0. This minterm I will call 1. This as 3 and this as 7. I am not gonna call this minterm as 15. Why I am doing so? Because x0 has been fixed. I am not even considering x0. In my final answer, what I am gonna write? y1 will be equals to x0 into whatever the expression I get. x0 into minterms, these minterms. Okay. So x0 is already 1. So my final expression will be these minterms only. Are you getting this point or not? This is just the basic thing. Again, we are coming back to combination circuit, right? x0 is fixed, so that I am already assuming as 1. So now I will make my K-map with these regard. So what I will do, what I am gonna do is that ये दिखेगा भाई, ठीक है? Actually I made the table a bit longer, so that I had to remove, but let it be. So what I am gonna do is that now I will make my K-map on these variables, and for 0 0 0 I am receiving output 0. For 0 0 1 I am receiving output 0. For 0 1 1 I am receiving output 1, and for 1 1 1 I am receiving output 1. So y1 is equals to what? What all are the minterms? This is 0, this is 1, this is 3 and 7. And what all are the don't cares? 0 1 2 3 4 5 6. Okay. So 0 1 2 3 4 5 6 7, right? 3 0 1, wait a second, 2 is don't care, no? So 0 1 2 3 and 4 5 6 7. This is 3 and 7, no? And this is 2 and 6. 0 1 2 3 4 5 6 7. So 0 1 are 0 0 only. So this is my K-map. So what I can see here, I can see this. So this will be 0 0 0 1 1 1 1 0 and 0 and 1. What is only constant here? x2 is only constant. So my y1 is equals to x2. Also I can see in the truth table as well that y1 is equals to x2 only. Okay. So this is how I am gonna solve it. Are you getting this point? So if I am gonna write down the expression of y1, in case of priority encoder as well, I told you this thing, that whenever you are going to write the expression, always make the K-map. Don't be smart. In case of priority encoder, if you remember it, I always told you that always make the K-map. So always I am gonna make the K-map. So y1 will be equals to x2. Okay. So that's it about our flash type ADC. Very easy concept it is. And did you observe one thing here? That was there any use of this analysis? Like I mean to say is that, is there any use of this analysis? No. You know one thing, that in the first go, x0 all bit will be 0. In the first go, all these will be 0. Then this will turn on, then this will turn on, and this will turn on. So there was no use of this analysis, but in the examination, you will do this analysis first, then you will get to know that these will be my input of decoder and these will be my final output. But there was actually no use of that, because I know that first this will be by default 1, then first x1 will turn on, then x2 will turn on, then x3 will turn on, and these will be my output. The only question was, it was based on priority encoder only. It was not based on your concept of flash ADC. This was only based on priority encoder. They asked the expression of MSB bit of your priority encoder. That's it. Okay, so that you have written. So y1 is equals to x2. That is your final answer. Okay, so yeah, that's it. In the next video, we are going to study about integrating type of ADC. So first we will study about single slope and then we will study about dual slope. Okay, so in the next video where we are going to cover integrating type of ADC. Okay, so that will be our last type of ADC. Hi everyone, so we have already seen three type of ADC. Now we are going to study about integrating type of ADCs. So in this we are going to study two parts, single slope and dual slope. So why it is called single slope, why the other one is called dual slope, that we will see, and what are the drawbacks of single slope that we had to move towards dual slope. Okay, so now we are going to see single slope ADC. So all the blocks you know, first one is the integrator, then it is a comparator, it is a AND gate, and this is a counter. Counter is fed with the clock which is coming from a gating circuit. Gating circuit means it is coming from a AND gate, right? Now when this counter will be fed with the clock, when this output is 1. Now when this output will be 1, when your VA is greater than Vx, right? So when your VA is greater than Vx, counter will up count. Do you agree to this point? When VA is greater than Vx, counter up counts. And when VA is less than or equals to Vx, counter holds, right? So yes or no? Okay. Now this is the integrator. I hope you know the analysis. Initially there is no charge on the capacitor. This 0 volt will be fed here because there is a negative feedback. 0 volt will be fed here. There is no charge on the capacitor. So initially Vx is 0. We will understand this by some particular values. Vref is 4 volt. I am assuming Vref to be 4 volt. So this will be minus 4 volt. RC value is 1 second. T clock is 1 second. You need to tell the digital output for VA equals to 5.4 volt. Okay. So initially first case is VA is equals to 5.4 volt. This is our first case. Okay. And Vref is minus 4 volt. So what will happen? 4 by R current will flow here. 0 minus 4. 4 by R current will flow here. It will charge the capacitor in this direction. So now Vx will go up. Vx is going up because this is 0 and this is positive. So Vx is going up. Current is flowing, that is 4 by R. So what will be your Vx? Capacitor will be getting charged linearly. So your Vx will be 1 by C integration I dot dt, which is 4 by R dt. From 0 to t it will charge. So it is charging with 4 by RC into t. So your Vx is going up. Will it keep on going up? No. The Vx will not keep on going up. Why is that so? Because the time it will keep on going up, but when the time, at the time when Vx is equals to VA, when Vx is equals to 5.4, when your 4 by R, 4 RC by T, RC value is 1 second, it is equals to 5.4. At that time what will happen? At that time counter will stop counting. The Vx is going up when it is trying to go above VA. At that time this output will go to 0 and counter will stop counting. So then you will get to know, just as it has stopped counting, you will get to know that yes, my VA has been reflected. Just as counter stop receiving the clock. In dual slope, in counter type ADC we did the same thing. In SAR type ADC also we did the same thing. Just as the counter stops counting, we always have a control unit here. Just as we get to know that clock is not being fed, at that time we see our final digital output. So when the clock will be stopped, when this value Vx tries to go above VA, so at this time the time is coming out to be 5.4 divided by 4. So 4 1 4, 12, 1.35 second. Okay. यार ये क्या हो गया, बार बार ये मूव हो रहा है. So at 1.35 second, let's just say this is your 1.35 second. This is only is your 1.35 second. So at 1.35 second, this has reached to what voltage? 5.4 volt. So what did you understand by this time? That means the clock was fed. Clock was fed. Clock was fed to the counter for 1.35 seconds. Say yes or no. This clock was fed to the counter for 1.35 seconds. Now what was your counter output? Q1, Q0. Initially it was 0, 0. Just as the first second came, not first second, this was your clock, right? This was your clock. T clock given is what? T clock given is 1 second. So just as it was fed, this was 0. Just as it was fed, it became 0, 1. This was your 0th second. At 0th second only it got the clock. So it became 0, 1. Now at 1 second, it would have come 1, 0. At 1 second only it would have come 1, 0. The next clock will be fed at the second, right? It would be fed at 2 seconds. This was your 1 second. It would be fed at 2 seconds. But just as it was applied from 0, 0 to it became 0, 1. At 1.35 second only, you got to know that now there is no further clock. So at this time only, somewhere here, you got to know that yes, I have reached my steady state. So this is my steady state output. So your 5.4 has been mapped to 1, 0, which is Q1, Q0. 5.4 has been mapped to 1, 0. Say yes or no. Did you understand this point? What did I do? I applied 5.4 here. As a user, I applied 5.4 here. I know that my Vref is 4 volt. Now it will start integrating. Vx will start going up. So the time when it reaches equals to 5.4, at that time my clock will be 0 and the counter will not receive the clock. The counter will not receive the further clock. Okay. And just I get to know that my clock is 0. I will tell that this is my final output. So 5.4 has been mapped to 1, 0. Same goes for 10.2 or whatever the voltage I have picked, that I will see, but I will have to add a page here. Same goes for 10.2 volt. So tell me what will be the steady state output for 10.2 volt. What do you think? VA is equals to 10.2 volt. So in this case as well, VA is fixed at 10.2 volt. VA is fixed at 10.2 volt. But now this value is going up. Vx is going up. Vx is going up. Okay. And this output is deciding whether clock will be fed or not. So I can write down the Vx equation first. Vx equation is 40 by Rc, right? 40 by Rc. So Vx is actually going up. The same slope is there. So Rc value is 1 second only. So 40 by 1 second is equals to, when it will give output 0, when it will go from 1 to 0. Initially Vx is 0 only, so it is giving 1 only and clock is being fed. When it will give 0? At the time when Vx is trying to go about 10.2. It is trying to go about 10.2. So T is becoming 10.2 divided by 4. 2.55 second, right? Yeah, 2.55 second. So at this time you will get to know that, let's just say at 2.55 second, at 2.55 second you get to know that my voltage has become 10.2 volt. Say yes or no. Okay. So basically clock has been fed for this much of time. Clock has been fed to the counter. Clock has been fed for this much of time. Clock has been fed to the counter or 2.55 second. So what would have happened? Rising is. This would have come at 1 second, this would have come at 0 second, 1 second and 2 second. So we would have started from 0 0, then we would have gone to 0 1, then we would have gone to 1 0. This is 0 0. At 0 0 only we must have got a clock, so we would have moved to 0 1. Here we must have got a clock, we would have moved to 1 0, and another clock we would have got, we would have moved to 1 1. So yes, this is our steady state output. That means 10.2 volt has been mapped to what? It has been mapped to 1 1. So I converted my 10.2 volt into digital output, that is 1 1. Are you getting this point or not? Okay. So this is the working of single slope ADC. But what is the drawback here? Here everything, this conversion from 10.2 volt to 1 1 volt is depending on the value of RC. Say yes or no? Let's just say by any mean, if my RC value changes, then what will happen? By any mean, if my RC value changes, then what will happen? RC value changes by, let's just say 50%. Then this time T will change. If the time T will change, that means corresponding digital output will change. Right? So problem is with RC. So we will see the example, but before that, let's write down this thing. Basically, what I'm gonna write down, I'm gonna just write down the summary. That is this. For both of the inputs, first one was 5.2, the next one was 10.4, right? Now 5.4 and 10.2, 5.4 and 10.2. So at some time T, which was 1.35 second, and this was 2.55 second. At this time T, we got the value equals to 5.4 volt, and here we got the value equals to 10.2 volt. Okay. So this slope, what we did, we just put Vref by RC into T is equals to VA. So from here we calculated T, which was VA into RC divided by Vref, and then we represented this T. Now this T is a function of VA, Vref would be a constant quantity. It is a function of RC, depending on RC, right? And this T, I would say T is a function of T clock as well, right? Basically, when I got T 2.55, then I got to know that 3 clock cycles are coming. When I got T equals to 2.55, I got to know that 3 clock cycle would have come. So in that manner, I am saying that it is a function of T clock as well. So what you are getting to know, that your final output is depending on RC. My final output is depending on RC. So that is an issue for me, because RC can change with respect to temperature. The register value will not stay constant in your particular design. In your particular IC, whatever the chip you design, register value will never stay constant. Okay. So if register value changes, let's just say if it changes by 50%. So what will happen? This slope will go down. This slope will go down. Changes by 50%, changes, or I should have written here increased by 50%, because in change you can say that sir it can decrease as well. Yeah, it can decrease as well, but we are taking an example of if it is increased. It can increase as well, no? If it is increased by 50%, then what will happen? The slope will go down. The slope will become Vref by 1.5 RC into T. Oh, let's see the analysis for VA equals to, we will see only for VA equals to 5.4 volt. What will happen? This would be the equation of Vx charging. Vx would be equals to Vref. Vref is 2 volt, right? Vref is 2 volt, no? याद ही नहीं रहता चल कुछ. Vref was 4 volt. I think I should start sleeping better. The basic thing I am not remembering. Vref 4 volt, so 40 by 1.5, right? Now when the comparator output would go to 0, when our comparator output is going to 0, this is your Vx and this was your Va. Va will always be at positive and Vx here negative. So when it is going to 0, initially Vx was 0. So when it will go to 0, 4 by 1.5 into T when it is equals to 5.4 volt. So what is the value of T you are getting? 5.4 into 1.5 divided by 4. So 5.4 into 1.5 divided by 4. It is getting 2.205. So again we will get the same answer only. 2. No. Yeah, okay, fine. So it is being 2.025. This is the time you are getting. So what do you think? What will happen? How many clock cycles would have come? 0, 1 second and 2 seconds. These much would have come, right? This is 0 second, 1 second and 2 seconds. So this would have also arrived. This 2 second one also would have arrived. So if that also has arrived, then what will be your final output? From 0, 0 to you would have gone to 0, 1 to there you would have gone to 1, 0, 1, 1, 0 and then 1, 1. So now your 5.4 is mapped to 5.4 is mapped to what? 1, 1. For 1.5 RC when the RC value got changed, and 5.4 initially was mapped to 1, 0, right? Initially it was mapped to 1, 0 when the case was simple RC. So one day you map 5.4 to 1, 0. Another day you go to your manager and you show him that, sir, if you apply 5.4, it will give me output 1, 0. Now your manager is applying 5.4 because of the temperature RC value got changed and you are getting 1, 1 there. So you may lose your job there, right? So you have to design something that is independent of RC. So the conversion time, what I would say is that T conversion, this is a conversion time only, no? This time T we found. This is a conversion time only. We started our circuit from 0. At 2.025 we will be able to tell that sir, this is now this is the time when we can see our output. Okay, so this is our conversion time only. So conversion time should not be a function of RC. Okay, or I should write in a better manner. This is our required design. Conversion time should not be a function of RC. This is our required design. Okay, so how we are going to design it? So for that we are going to use dual slope ADC. Okay, yeah, so now to make our conversion time independent of RC, we are going to start studying about dual slope ADC. So our conversion time should be independent of any other factor. So RC should not come there because that is depending on temperature. So for that we are going to start studying about dual slope ADC. We will study that, but before that we need to look at another concept, that is overflow bit in counter. So this is a simple counter, simple up counter it is. Clock is fed, there are n bit of output. So what it will do, it will up count. What do you mean by this overflow bit? So let's take an example of 2-bit up counter. So we are starting from 0, 0, initial condition is 0, 0. So just as the clock is fed, this is our clock, right? So at t equals to 0 second only the clock will be fed, right? So at t equals to 0 second only it will become 0, 1. Say yes or no? So from 0, 0 to it will count to 0, 1 to 1, 0 to 1, 1. So I am not writing what is my overflow bit here. I am telling this is my initial condition. Why it is my initial condition? Because just as the clock is fed, at t equals to 0 second only you are getting 0, 1. Right? At t equals to 0 second you are getting 0, 1. So here your overflow bit is 0. Here also overflow bit is 0. Here also overflow bit will be 0. It is counting from 0, 1, 1, 0, 1, 1 and again till 0, 0. After that it will again come back to 0, 1. Now my overflow bit will become 1. Overflow bit will become 1. It will be 1 only till 0, 0. Now again it is coming to 0, 1 because I am assuming my initial condition is 0, 1 because at t equals to 0 only it became 0, 1. At t equals to 0 only my output became 0, 1. So I am assuming this as initial condition. When no clock was applied it was 0, 0. Just as the clock is applied it has become 0, 1. Now at the 9th clock cycle, it will again become 0. Overflow bit will again become 0. So what overflow bit does is that when it is up counting for one cycle, it will be 0 only. Another clock cycle will start, it will be 1. Another clock cycle will start, it will be 0. Another clock cycle will start, it will be 1. Are you getting this point? We are counting from 0 1 to 1 0 to 1 1 to again 0 0. Then it was becoming overflow bit was 0 only. When we again started from 0 1, it became 1. So this is the concept of our overflow bit. Okay, so very simple concept that you need to know. Now we will move to our dual slope ADC. So this is the primary structure, or you can say block diagram of our dual slope ADC. Very simple, all the blocks you know. Just only one thing that has been added, that overflow bit is fed as the select line of a mux, and this input is coming from the output of the mux. So what it will do, when your overflow bit is 0, it will feed VA here, analog input here, and when it is becoming 1, it will feed minus VREF here. So let's understand the working by an example. What example I am taking? Initial example I forgot to write. VA is equals to, what we can take, 4.4 volt we can take. Okay, so VA is equals to 4.4 volt I will take here. So this is our first example, that if I put S equals here, initially I will take my overflow bit is 0 only. So this VA will be fed here, this VA will be fed here, which is equals to 4.4 volt. What will be the current flowing here? 4.4 by R. Now that current will be charging this capacitor in this direction, right? In this direction it will be charging the capacitor. So Vx node will be going down. Tell me one thing, if Vx is negative, then what will happen? There is this op amp, there is this comparator. V positive is connected at 0, and if V negative is negative, then what will happen? This output, what I will call? This output I can call anything, VK, Virat Kohli. This output will be 1, right? And if this output is 1, that means clock is fed here. And if clock is fed, that means counter is counting up. So if Vx is negative, then counter counts up. Counter counts up. And tell me one thing, just as Vs goes to 0 or positive, at that time what will happen? Just as Vx goes to 0, what will happen? This will go to 0, this will go to 0, that means clock is 0. Just as it goes to 0, counter holds. So our eyes will always be here. Our eyes will always be here. Just as it becomes 0, I will get to know that, sir, yes, this is my steady state output. That means my VA has been mapped here. So our target will be to know when this clock is going to 0. Initially what is happening? Overflow bit is 0, 4.4 is fed here, and this is charging the capacitor. If it is charging the capacitor, Vx is going down. Are you getting this point? Vx is going down. So this I get to know that my Vx is going down in the negative direction. Vx is going down in the negative direction. So this thing I have got to know. I am drawing the waveform of Vx. Vx is going down. Okay, so how it is going down? 4.4 by R current is being fed. So what will be the equation of Vx? Vx will be minus 4.4 by R C into T. 1 by C into I dot dt. Current is 4.4 by R. So 1 by minus 4.4 by RC into T. So this is how it is going down. So yes or no? RC value is given or not? RC value is not given, but VREF value should be given, which is not mentioned here. I will take VREF equals to 8 volt. Okay, VREF value will be given. VREF value is 8 volt. So now it is going down. Now tell me one thing, till what point Vx will keep on going down? Till what point Vx will keep on going down? Vx is depending on this 4.4 volt. Vx is depending on this 4.4 volt. Now until you do not change this voltage, it will keep on going down. Until you are not going to change this voltage, it will keep on going down. If it is keep on going down, that means clock will be keep on being fed, right? Clock will always be fed. If it is going down, clock will always be fed. Our target is to make the Vx go up. If it is going up, if it is going towards 0, that means this Vk will be 0, and if this is 0, then clock will be stopped. And if clock is stopped, then we can say that this is my final output, or my VA has been mapped. So for that, what should have happened? That this should change. Now when this will change? This will change when this bit becomes 1. Because if this becomes 1, then minus VREF will be fed here. When this will become 1, initial output is 0 0, it goes to 0 1 just as clock is applied at t equals to 0 second only. Just as clock is applied, it goes to 1 0, sorry 0 1, then it goes to 1 0, then it goes to 1 1, then it goes to 0 0, and then again it comes to 0 1. Here overflow bit will become 1. So for this time, this time, this time, and this time, it was 0. How much time it was? You started here, t clock is given or not? T clock should also be mentioned, that is 1 second. Okay, t clock I am taking as 1 second. Okay, so you started here, just as you applied, it became 0 1. After 1 second, this was the scene. After 2 seconds, this was the scene. After 3 seconds, this was the scene. And after 4 seconds, this was the scene. At 4th second, this will become 1 and minus VREF will be fed here. So at least for 4 seconds, are you getting this point? You started here, this was the scene at 0 second. At 1 second, this was the scene, it became 1 0. At 2 seconds, it became 1 1. At 3 seconds, it became 0 0. At 4 seconds, it became 0 1. So at 4th second, this became 1 and minus VREF is fed here. Now the scenes will change. How it will change, that we will analyze. But one thing I got to know, that till 4 seconds, it will keep on going down. Till 4 seconds, it will keep on going down. So until this time, it will keep on going down. This is your time t till 4 seconds. Okay, and this potential is minus 4.4 into 4 by RC. It will keep on going down, right? After that, what will happen? After that, minus VREF will be applied here. And what is your minus VREF? Minus VREF is 8 volt. VREF is 8 volt actually. So minus VREF will be minus 8 volt. It will be minus 8 volt, right? So let's say move it off. If it is minus 8 volt, that means it will drive the current 8 by R in this direction. If it is driving the current 8 by R in this direction, then what will happen? The capacitor will start charging in this direction. That means this negative voltage is going up now. Are you getting this point? This negative voltage is going up now. Because initially capacitor was getting charged in this direction. So voltage was going down. Now capacitor is getting charged in this direction. That means voltage will go up now. No? So from here it will go up. Are you getting this point? I hope you know the basic concept of integrator using op-amp. Simple integrator it is. So that we are doing. So now what is happening is that your Vx is going up. So Vx will go up. And how it will go up? How it will go up? The current is 8 by R. So what will be the capacitor charging equation? That would be 1 by C integration 8 by R into dt. Capacitor is already having some voltage. Capacitor is already having some voltage, that is 4.4 into 4 by RC. Capacitor was having the voltage in whatever the direction it was having, in opposite direction the current is flowing. Whatever in this direction capacitor was having this much of voltage, I am calling this as VCT. So in this direction capacitor was having this much of voltage. Now voltage is being fed in the opposite direction. So minus sign I am using. And what is your Vx? Vx is simply the negative of VCT. This I am calling as VCT. Okay, forget about this. This I am calling as VCT. So what is my Vx? Vx is minus VCT. So what will be the Vx equation? This much voltage is already fed. Okay, that is negative. Vx t equation. So this much voltage is already fed, that is negative. Now in addition we are making this much of voltage more. So it is starting from 4 seconds. It will go till time t. With the slope the current is 8 by R. 1 by C will also be there, that will come here into time t. Here I should write dt actually. So if I remove the integration time, what it will become? Why I am writing t here? It is into 4. So 4.4 into 4 by RC plus 8 by RC into t minus 4. Say yes or no? In that manner it is going. Now tell me one thing. Just as it touches 0, I don't know this time, but just as it touches 0, at that time what will happen? This Vx will go to 0, this will go to 0, and the counter will stop counting. Counter stops counting, or I would say clock becomes 0 when Vxt is equals to 0. When Vxt will be 0? When 4.4 into 4 by Rc is equals to 8 by Rc into T minus 4. So Rc 2.2, T is equals to 6.2 second. So at T equals to 6.2 second, this was your 4 second. This was your 4 second and this is your 6.2 second. So basically it took 2.2 second time more. It took 2.2 second time more to become 0. And just as it becomes 0, I will get to know that my clock has become 0. So now yeah, whatever that I am getting here, that will be my final output. So in the examination, I am not going to write down these equations. What I will get to know is that how I am going to solve in the examination. One thing I know that until it will completely count, until it completely counts, until my output completely counts, I am gonna go down only, because overflow bit will not become 1. Overflow bit was initially 0. To become it from 0 to 1, it has to completely count. From 0 1 to again it comes to 0 1, then it is going down to then this bit, overflow bit, is changing. So I need to go from 0 1 to again 0 1. That means at least I will take 4 clock cycle. If it was 8 bits, then how much clock cycle I would have taken? 0 0 1, then 0 1 0. Again it will keep on going down. Then again I will come back to 0 0 1. So how much clock cycles I would have taken? 2 to the power n into t clock. Say yes or no? 2 to the power n into t clock. That means 8 clock cycle I would have taken. This would take 1 second, and by that 8 seconds I would have taken. So what I am gonna think is that Va will be there for 2 to the power n into t clock time, right? So Va will be there for 2 to the power n into t clock time. So what will be my voltage? So Va by Rc into time t, that is 2 to the power n t clock. Now Vref will come in action. And that will be fed in the opposite direction. Vref will be charging the capacitor in the opposite direction. If it is charging the capacitor in the opposite direction, that means whatever the sign of this voltage, that will be opposite to that. And my target is to make it 0. My target is to make it 0. And if I make my Vx equals to 0, that means this, whatever the voltage has been fed, that should flow in the opposite direction as well. So that voltage would be Vref by R, Vref by Rc into T. From here I will find the value of T. And that value, I will find this value of T. And that value will be this 2.2. Are you getting this point or not? That value will be this 2.2. Till this amount I already know that this will be the time of 40 clock. So from here I will find the value of T, and that I will add in 2 to the power n t clock. So that will be my total conversion time. We will see it, but in the examination I am going to write down this equation. I hope you are understanding this equation. Va by Rc 2 to the power n t clock. So until this time it will be certainly charging in the negative direction. Now Vref will be coming in action, that will be charging in the positive direction. So Vref by Rc into T. So this equation I am going to write. And one thing I get to know here is that Rc and Rc are getting cancelled. So it is my time T is not depending on Rc. So this is why I wanted to design, and this is what I have designed. So at 6.2, what will be my digital output? Pause the video and write down on your own. Think with good amount of patience and tell me what will be your output at 6.2 second. So will I analyze right from the beginning? No, because I know one thing, that 0 1 is there at 4th second. At 4th second, just as 4th second started, I was getting 0 1. At 5th second, what I will have? 1 0. At 6th second, what I will have? 1 1. That's it. Are you getting this point? Basically, this was your 4th second, 5th second, 6th second. Next clock cycle will not even come. Next clock cycle will not even come. So that's it. This is your steady state here. 6.2. This is actually 6 second. but at 6.2 only you will have 1 voltage only. So basically your 4.4 volt has been mapped to 1. Are you getting this point or not? So this is how it is mapped. And my conversion time, if someone asks you what is the conversion time for this, so total conversion time is 6.2 second. Here my conversion time is 6.2 second. Why it is this? Why it is 6.2 second? Because 4 second it will certainly take 4 second it will take to go down to the particular value, and another 2.2 second it will take. So conversion time is 6.2 seconds. I hope you must have understood this example. I hope you must have understood the analysis. Okay. So let's remove this off, whatever that was there. Let it be there as it is. Yeah, all fine. So let's change this value. Let's make it 2.3 volt. Okay. So analyze it on your own. Vref is 8 volt again, and your T clock is what? 1 sec. So what do you think what will happen? We will only solve by the graph. Okay. Only we will solve by the graph. So this is the Vx graph we are drawing. First we know one thing, that it will be going down no matter whatever the voltage has been applied. Va will be there for 2 to the power n T clock. Va will be there for 2 to the power n T clock. So it will be going down for 2 to the power n T clock. And here 2 to the power n is 4. So it will be going down for T equals to 4 seconds. Okay. It will be going down for T equals to 4 seconds. So what will be this potential? V by RC, Va by RC into time T, that is 4 seconds. Now what will happen is that Vref will come in action and it will take it to 0. So initial voltage you are having is 2.3 by RC into 4. Now Vref is coming in action, that is 8 volt, and it will take some time T. I will call it at T1 time. It will take T1 time to make all the potential equals to 0. Okay, RC getting cancelled. So how much time it is taking? 2.3 by 2. So 1.15. 1.15 second it is taking. So what is your output? At 4th second, you know 1.15 second more it is taking. Are you getting this point? This is 1.15. Okay, 1.15 second more it is taking. Look, this is the initial potential it is having. It needs to nullify this much of potential. So this much of potential, whatever we are here, 2.3 by RC into 4 has been nullified by this 8T1 by RC. So how much time it is taking? 1.15 second more. So at 4th second you are already having 0.1. Okay, then, or you can say at 0th second, you can say in that manner, you can say basically before this you are having 0.1, just as it becomes, it will become 1.0. Basically what is the scene? Here it was taking 1.15 second and here it was taking 2.2 seconds. So again let me explain it right from the beginning. So total conversion time would be what? 2 second plus 1.15 second, that would be 5.15 second. So you can start right from the beginning as well. So if I start right from the beginning, at 0th second I was having 1.0. Directly it would become 1.0 just as the clock came. Then it would become not 1.0, sorry, 0.1. Just as the clock came, it became 0.1, then 1.0, and then 1.1, and then 0.0. At 4th second what happened? It became 0.1, and at 5th second what happened? It became 1.0. At 5th second it has become 1.0, right? and 5.15 will be somewhere here. Let us say if this is 5th second, if this is 5th second, 5.15 will be somewhere here. So next positive edge is not going to come. So this is my steady state, that is 1 0. Okay, so where it is mapped, 2.3 is mapped to 1 0, right? 2.3 volt is mapped to 1 0. So these are, they can ask conversion time, they can ask the digital output. So in that manner you will decide. So can you tell me what will be the shortcut for this digital output? So digital output will be the same that we have seen in counter type ADC, same output, ditto same. What we are going to write? Analog input divided by resolution. Resolution we are going to take as Vref by 2 to the power n. Okay, this is what we are going to take as the resolution. We are not going to take 2 to the power n minus 1. In some cases we can see 2 to the power n, in some cases we can see 2 to the power n minus 1. Here we are going to take 2 to the power n. In all the questions, in the examination what will happen is that this n value will be very large. They will not ask for 2 bits. This value will be very large. If this value is very large, then what will happen? 2 to the power n minus 1 will not matter much. Resolution, somewhere you can see Vref by 2 to the power n, somewhere you can see Vref by 2 to the power n minus 1. We will take Vref by 2 to the power n. Okay, in case of ADC generally we will take 2 to the power n, right? And here what we are assuming is that why I am taking 2 to the power n. Are you able to think it? Because what I am assuming is that just as clock is applied you are getting 0 1. So you are actually starting from 0 1, not from 0 0. Just as clock is applied from 0 0 we are directly getting 0 1. No. So this is the assumption. So that's why I have written Vref by 2 to the power n, not 2 to the power n minus 1. Okay. So what is the analog input? Here this is wrong actually. This should come least integer function, it is right. So analog input is 2.3 Vref 8 into 2 to the power n, that is 2. Again yeah, I am doing the same mistake. 2.3 divided by 2, that would be 1.15, right? And we have to go to 2, the next integer. So what is the decimal equivalent of 2? That is 10. You can see the same thing here as well. What we are going to do? Analog input is 4.4 volt divided by Vref 8 volt, right? 4.4 divided by 8 into 2 to the power n. What I did was analog input divided by resolution. What is the resolution? Vref by 2 to the power n. So 2.2. What I am gonna get? 2.2. And next value will be 311. Okay. This we are not writing here, just we got the formula here. We can solve by our method as well, or we can solve by this formula as well. Okay, but here we are learning the method. We will solve a lot of problem. There we can solve by the formula or the method as well. So by both we will see. Now analyze this. If my VA is 8.2 volt, what will happen? If my VA is 8.2 volt, then what will happen? So one thing I know, that first VA will be there. VA will be there for 4 T clock. VA will be there for 2 to the power n T clock, or you can say 4 T clock. So no one can stop this VA to be there for 2 to the power n T clock. In this case it is 4 T clock. So till 4 T clock, or you can say 4 second, this will be there. And how much voltage it will drive? VA by RC into time T, which is 4 seconds. Now what will happen? Now what will happen is that Vref will come in action and it will kill it. Will it be able to kill it? Let's check that out. So 8.2 by RC into 4 seconds. Now Vref will come, which is 8 T1 time it will take divided by RC. So what you are going to get? somewhat greater than 4 second, right? Somewhat greater than 4 second. So 8.2 divided by 8.2 divided by 8 into 4. So 4.1 second you will take. So now what VREF is saying, I need 4.1 second to kill this. Whatever the voltage you have developed here, I need 1.4 second to kill this. Will it be able to get 4.1 second? Look, you were at 1 0, right? At 4th second. At 5th second you will be at, यार ये बार बार 1 0 क्यों लिखता हूं मैं? At 4th second you were at 0 1, not 1 0, you were at 0 1. Then you became at 1 0. Then at 6th second you went to 1 1. At 7th second you went to 0 1 again, right? At 8th second, basically this will be 4 plus 4.1. So 8th second you are at 1 1. What you got to know that your overflow bit has already become 1. Basically, sorry, your overflow bit has already become 0. Initially it was 0, then you change the state, you have counted completely, now you are starting the new counting, so it has become 1 now. From 0 to 1 it has become, now again it has become 0, so again it will take VA. So it was going towards making it 0, but it was going towards making it 0. In 4 second of window it could go to here, in 4 second of window it could go to here. Till this point your overflow bit was 0, right? Now at this point only, till this point your overflow bit was 0, at this point it became 1, overflow bit changed. Now again overflow bit will change. Are you getting this point? Again overflow bit will change, then what will happen? Now again it will start charging. Again it will start charging. Again it will develop some voltage. Then again overflow bit will change. Again it will try to go down, but will not be able to go down. So in that manner, the voltage will keep on going up. So it will be never going towards 0. It will be never going towards 0. Are you getting this point? Because your this time, T1 time has only the window of 2 to the power n t clock. Do you agree to this point? In 2 to the power n t clock, you need to make it to 0. If you are not able to make it, again this guy will come up. Again this overflow bit will be changing. After every 2 to the power n t clock, overflow bit changes. I am writing this statement. After every 2 to the power n t clock, overflow bit changes. So whatever the voltage that has been developed here, that need to be killed in how much time? 2 to the power n t clock only. Are you getting this point? So I'm gonna write is what I'm gonna write. So I'm writing down the conclusion that my T1 should be less than, or worst case should be, it would be equal to 2 to the power n t clock. Because if my T1 is greater than 2 to the power n t clock, if it is taking more time to kill this voltage, then what will happen? The overflow bit will become again active. So here a small error I did. It should be 0 0. At 7th clock cycle I will get 0 0, right? And then I will get 0 1. So till this time there is no problem with the overflow bit. So here overflow bit was 1 only. So VREF was in action. VREF had 2 to the power n t clock to make the Vx potential go to 0. But if it was not able to make the Vx potential go to 0, after that what will happen? The overflow bit will become again 0 and again VA will become in action. Here VA is in action, here VREF is in action. Here VA was in action, VREF will come in action, but again it will not be able to kill the voltage because it will keep on going more and more. So again, basically the thing is, VA is developing more voltage in the negative direction. VA is developing more voltage in the negative direction and the VREF is not able to kill it. Why it is happening? So this is the first conclusion that we are having. What could be the other conclusion? The other conclusion could be your VA should be less than or equals to VREF. Say yes or no. Because if VA is more, then it is developing more voltage. Look, this slope is same, right? The speed of charging and discharging is same. The speed of charging and discharging is V by RC. Basically, the Vx voltage is V by RC into T. If it is VA, then VA by RC. If it is VREF, then VRF by RC. So speed of charging is same. The thing is, all depends on the potential. If VA is more, that means it will develop more voltage in the negative direction. If it is developing more voltage in the negative direction, then when VREF comes in action, it will not get sufficient time to kill this voltage. So never your Vx is going down to 0. And if your Vx is not going down to 0, what does that mean? If Vx is not going down to 0, then never the counter will stop having the clock. If counter is not stopping having the clock, then it will again keep on counting. And if counter is not getting 0 clock, then we cannot tell that this is our steady state output. So the condition that we have got now, that my VA should be less than VREF and T1 should be less than 2 to the power n T clock. Very important observation. Very, very important. Okay. Till now questions has not been asked, but certainly I am thinking that they will ask what should be the maximum applied voltage. They can ask in counter type ADC, they can ask in SAR type ADC, or they can ask in this dual slope ADC as well. So in all the conditions, what was the answer? That your VA should be less than VREF. In counter type ADC, what was the scene? In counter and in SAR type ADC, both scenes were same, that this was your VA and this was actually your VDAC, because it was coming from the DAC output. It was coming from the DAC output. So your VA should be less than the maximum value of VDAC. And what is the maximum value of VDAC? That is VREF only. So maximum value of VDAC is VREF only. So your VREF should always be, your VA should always be less than VREF. Any kind of ADC it is. So if they are asking what should be the applied maximum voltage, you will always say that, sir, my applied voltage should be less than my reference voltage. Are you getting this point? Is the thing crystal clear? Okay, so this is about your dual slope ADC. Now we are going to solve the problems only, which are very simple. So let's solve some problems, right? So dual slope ADC has a reference voltage of 100 millivolt. The first integration time is set for 100 millisecond. The conversion time of ADC for an input of 123.4 millivolt. So what will happen? First 123.4 millivolt is applied, and it is being integrated for 100 milliseconds, right? 123.4 millivolt is being integrated for 100 milliseconds. Now what will happen? Reference voltage will come in action. Here they did not give the, how many bits are there, nothing like that. They just told that it is being integrated for 100 milliseconds. Now what will happen? VREF will come in action. So now VREF will come in action. Now it will kill this voltage. It will kill this voltage in how much time? It will take T time to kill this voltage divided by RC. So this RC and this RC is getting cancelled. How much time it will take? 123.4 millisecond. So is this the final answer? No. The conversion time, what will be the conversion time? Total conversion time is initially 100 millisecond. I told you one thing, the conversion time is this time plus the time it takes to make it 0. Here also we saw the conversion time is 5.15 second. This time plus this time. So conversion time would be 100 millisecond plus 123.4 millisecond. So we are getting conversion time equals to 223.4 milliseconds. Okay, this is your conversion time. For 12-bit dual slope ADC, T clock is 1 second, VREF is 10 volt, input voltage is 2 volt, digital output you need to tell the decimal equivalent. How you are going to solve it? Look, let's just say I do not remember the formula, so how I would have solved it? 12-bit ADC is there, T clock is 1 microsecond and input voltage is 2 volt. So first VA will come in action, this is your VA. So first VA will come in action, right? So VA will be coming in action, so VA by R current will be flowing. So 2A by R current will be flowing. 1 by C integration, I do it, this is what I am applying. So 2 by R current is flowing, so 2 by RC into time T. So basically VA will develop this much of voltage, 2 by RC into time T. What will be time T? Time T will be, it will be there for 2 to the power n T clock. I told you one thing, it will be there for 2 to the power n T clock. Why it will be there for this much of time? Why it will be there for this much of time? Because till this time VREF will not become active. After this VREF will become active. After this VREF will become active, and it will take some time t to kill this particular voltage, or I would say it will take time t1. It will take time t1 to kill this particular voltage. Are you getting this point? Initially VA is in action. Initially VA is in action, and it will be there for 2 to the power n t clock. So it will develop VA into 2 to the power n t clock by RC voltage. Now VREF will come in action, and it will try to kill this much of voltage. So VREF into T1 by RC, it will take VREF into T1 by RC, right? It will take T1 time, so it will kill the voltage in this manner. So what will be the time? Time will be this, and this is getting cancelled. So the time will be 2 to the power 12 by 5 into t clock, which is 1 microsecond. So this much time it will take. So how much time it is? To the power 12 divided by 5. So this is 819.2 microsecond. So in this much of time, where you would have gotten, you have 819.2 microsecond. When I was saying that 819.2 microsecond, and this has already crossed. Basically, I am initially at 0000, 12 bits are there. So 11 bits will be 0 and then 1. So this is at 0th second. At 1 second, where I will be? At 1 second, I will be having a decimal equivalent of 2. So at 8/19th second, what will be my decimal equivalent? 820 only, no? I am starting from 0001. Why I am saying this is at 0 second? Because clock would have applied at 0 second only. So from 00 I would have gotten to 01 at 0th second only. So at 0th second my decimal equivalent is 1. At 1st second my decimal equivalent is 2. So at 8/19th second, what is my decimal equivalent? That is 820. So my decimal equivalent would have been 820, right? So output would have been 820. Or final, like what is the formula? Formula is digital output, that would be equals to analog input, which is 2 volt divided by what? Resolution I need to type, resolution. So what is the formula of resolution? VREF, which is 10 volt divided by 2 to the power n 12. So 10 into 2 to the power 12. Okay, again yeah, the same mistake. So by solving it, I will get this 819.2 only, and here I am gonna get 820. Okay, so this is my digital output, decimal equivalent it is. This is the decimal equivalent of my digital output. Are you getting this point? So this formula you can apply. How you are going to remember it? Dual slope D and counter type C and SAR type. Here we are getting ahead, and in SAR type we are getting back. So S stands for super. So if you are already at super, that means you can go back only. If you are having grade D or if you are having grade C, then you need to go ahead. So here we are going ahead. From 819.2 to we are going the next integer, and in super we will come back to the previous integer. So this is the formula. Like everyone will solve by this method, but by again and again taking the examples, we have developed this formula. What is that formula? Simply you need to write down the analog voltage divided by the what? Divided by your resolution. So from there you just need to remember two things: dual, counter, DC I will go ahead, and super I will go back. So I will calculate this value and then I will write down the next output. Okay. In flash type ADC there was no formula like that. In flash type ADC there is no counter, nothing like that, no clock. So there are no formula developed. In flash type ADC we will have to solve by the analysis. And in flash type ADC, if they are asking this question, Till now they have never asked digital output in flash type of ADC, and they are never gonna ask as well. And if they ask, that means they will ask for 3-bit or 2-bit only. They are not going to ask for 12-bit. If they ask for 12-bit, how much big circuitry it would be, right? They are not going to draw it. So they are, if they ask, they will ask only for 2-bit or 3-bit. So that you can solve simple by simple analysis. So there is no formula in flash type of ADC, but in this dual slope ADC, in this counter type ADC, in SAR type ADC, we have developed the formula. So this you need to remember, it is also very, very important. So conversion time and digital output, these are the two of the most important things which can be asked from ADC. Okay. So let's write down the summary. So this is our summary of our dual slope ADC. So conversion time is independent of RC, right, in dual slope ADC. Now how will you find the conversion time? So first VA will be in action for this much of time. So this much voltage it will develop. Then VREF will be action for T1 time. So that T1 time I will find VA into 2 to the power n into T clock by VREF. Basically I need to equate the voltage. This is what I did here. VA was 2 volt was in action for 2 to the power n into T clock time. Then VREF came in action for T1 time. So this T1 time I found, which in formula will come like this. So what will be my total conversion time? Here what was your total conversion time if I needed to find conversion time? So what was your total conversion time? That was 2 to the power n, that means 2 to the power 12 T clock. T clock is 1 second. 2 to the power n T clock plus 819.2. T clock should be 1 microsecond. That's why I was thinking. So 1 microsecond. So this much plus 819.2 microseconds. So this was your complete conversion time. 2 to the power 12 is not that much of large value. 2 to the power 12. 4096 plus 819.2. 4915. So total conversion time is 4915.2 microsecond. This is your total conversion time. Okay, 4915.2 microsecond. This is the total conversion time. So this is also they can ask. So but we can calculate in this manner. Now what will be your maximum conversion time? Can you tell me? If VA is equals to VREF, at that time you will get your maximum conversion time. Do you agree to this point? When VA is equals to VREF, when both are equal, that means whatever the voltage VA is developing, the same voltage VREF will kill, and whatever the time your VA took, the same time your VREF will take. And what is the maximum time VREF can take? What could be the maximum value of T1? That could be 2 to the power n T clock, right? And from here, let's write down this formula. T conversion would be 2 to the power n T clock plus what we are getting in place of T1. So that is 2 to the power n T clock into VA by VREF. So conversion time is coming out to be 2 to the power n T clock plus 1. 2 to the power n T clock will come in common, and 1 plus VA by VREF. This is your conversion time. Okay. From here this formula is also coming, but we are not going to remember this formula. This is just to write down. If they are asking the conversion time, we have this trick. Not trick, this is the method, sorry. First VA will come, it will develop for 2 to the power n T clock. After that VREF will come, it will be there for T1 time. That T1 time I need to find. And the maximum value of T1 time could be equal to 2 to the power n T clock. So my maximum conversion time would be this, 2 to the power n T clock plus 2 to the power n T clock. So 2 into 2 to the power n T clock, that would be 2 to the power n plus 1 into T clock. So this is your maximum conversion time. And one more thing that is there, that your VA should be less than VREF. And how will you calculate your digital output? Analog input divided by resolution. Let's write down the summary of all the ADCs we have studied. So this is the summary of all the ADCs we have studied. So we started with counter type ADC. So VA should be less than VDEC there. So VA should be less than VDEC maximum value. What that would be? R into 2 to the power n minus 1. Or I can write down that my VA should be less than VREF voltage. Right? VA should be less than VREF. VREF I can find by R into D maximum only, and D maximum would be 2 to the power n minus 1. Okay? Well and good. Digital output will be analog input divided by resolution. Conversion time, yeah, this is the new thing, right? This is something new coming. So that I forgot to tell when I was teaching counter type ADC. So this is a new thing. So conversion time, TC, maximum conversion time, I know that it would be 2 to the power n minus 1 into t clock. But for any analog value, let's just say, let's take the example which you took initially, counter type ADC only I am telling, okay? So let's just take the example of 0.2 volt. It was coming from VDEC. Initially counter position was 0, 0, 0. It was fed to our DEC and then it was delivering some output. Do you remember this thing? And here there was counter, and this counter was run by this clock, and this clock was managed by AND gate. Do you remember this thing? So initially 0, 0 came. Initially clock was being fed. So 0, 0 came, 0 was fed here. So this was your 0 cycle. Just as a clock cycle came, this became 0, 0, 1. If this became 0, 0, 1, then what happened? DEC output became 1. So this output became 1. So just as it became 1, what it got to know? That now I need to stop. Clock needs to be stopped. So how much cycle it took? 1 T clock. Do you remember? 1 T clock cycle it took. If resolution I am assuming to be 1. So how I could have calculated it? 0.2 divided by resolution I am assuming it to be 1 into T clock. So next value I need to go for T clock. If applied voltage was 13, then what would have happened? 13.1 you can take. What would have happened? Starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Till 13 also, if VDEC is 13 volt, till 13 volt also, the clock will be fed. Once it gets to 14, then clock will stop. Right? So how much clock cycle it will take? From 0 to 14 T clock it will take. So how you could have solved it? 13.1 divided by resolution. What was the resolution? 1. It was 13.1 or 13.2, whatever it was, into T clock. So how much time it would be? 14 T clock. I hope you are understanding it. You just need to revise counter type ADC. It would be very easy. I made the table as well. That for 0.1 it would be T clock, then 0.4 it would be 0.2 T clock, T clock only. So there was this table. I can show the table as well. मिल जा भाई मिल जा. Yeah, you can see this table. For 0.1 volt we were taking T clock only. For 0.9 volt we were taking T clock. Here you can see for 0.9 volt we were taking 2 T clock. So how I would have solved it? 0.9 divided by resolution here was 0.5 into T clock. So what I am gonna get? Somewhat greater than 1 point something, and next integer I need to take. So 2 T clock. Yes, conversion time was 2 T clock. So if they are asking conversion time for a particular voltage, if they are not asking for maximum conversion time, they are asking the conversion time for a particular voltage, then this is what you are going to apply. How this formula came, that also is clear. In the examination, you will not be able to think that much. If you are able to think, that is good. Otherwise, you can remember the formula, because only one formula I am asking you to remember. Right? Also, I have told you the trick. Analog input divided by resolution that you need to do. Just the trick is, for counter type, you need to take the next value. For dual type, you need to take the next value. For SAR type, you need to take the previous value. Say yes or no. Okay. So only this thing you can keep in mind, and a lot of problems you will be solving very quickly. So that's why I only ask you to remember the formula if it helps solving the problem easily. Now I am not asking you to remember this formula, because you are not going to eventually remember it. We can solve the problem easily by this method. I know VA will come, VREF will come. That's it. So I will never ask you to remember this formula. But this formula will be useful. These kind of formula will be useful in the examination. You will be able to solve it quickly. Okay. So that's why I developed this formula. You are not going to find in any textbook, in any notes as well. Okay. You are not going to find this formula, that how much conversion time will be there for a particular analog input. Everyone will write for highest value. Okay. Maximum conversion time everyone will write. Minimum everyone will write. But for a particular value, for a given resolution, how much time it will take. So there you are not going to think that much in the examination. Here when we are studying you can think, but in the examination it will take a lot of time. So for that we have developed the formula. Okay. And that is also very easy, not tough at all. So maximum conversion time we know, minimum conversion time we know, average conversion time we know. But and for tracking type ADC, what was the what was our advantage? So average conversion time was less than 2 to the power n minus 1 t kilog. We are also not remembering the formula of average conversion time. What we will do, we will take the maximum conversion time and minimum conversion time and just take the average of both. 2 to the power n minus 1 t kilog plus t kilog divided by 2. So 2 to the power n minus 1 t kilog we will be getting. So average conversion time will be the average of minimum and maximum. Okay. So this is your counter type ADC. For SAR type ADC, same things were there. VA should be less than that. Digital output, just you need to take the greatest integer function. We are not going to remember greatest or least. We are going to remember that SAR super. That means we can go down now. So least so the previous integer we need to take. And conversion time is n t kilog. Here there is no concept of maximum minimum. Both are equal. Maximum conversion time and फिर यार उल्टा लिखा जा रहा है. Maximum conversion time and minimum conversion time both are equal here. So for any analog input, if they are asking that what will be your conversion time for 4.2 volt, what will be your conversion time for 6.2 volt, all will have the same conversion time, because in SAR type ADC we were making the tree, and at the final of the tree we were calculating our output. We were making the tree, and at final that was our final output, right? 1 step, 2 step, 3 step, 4 step, and then finally we will taking the output. So there is no minimum or maximum. Conversion time is same. Okay. So maximum TC and minimum TC both are same only here. So don't do this mistake. Maximum TC and minimum TC will come in counter type ADC, not here. Okay. Flash type ADC. Flash type ADC conversion time was 0. Ideal conversion time was 0, or it could be equals to delay of the component, or maximum it could be equals to t kilog if you are using the parallel in parallel out register. Digital output will be analysis based. Number of register used. This is what they are going to ask. How many registers were used? For n bit, 2 to the power n. How many comparators were there? 1 less, 2 to the power n minus 1. And what was the order of decoder? 2 to the power n into n. Okay, so this is what these three are important for flash type ADC. And for dual slope ADC, just now we saw VA should be less than VREF. Conversion time, that would be, this is your, conversion time. This formula we have developed, 2 to the power n t kilog 1 plus VA by VREF. Here only we developed, or we are not going to remember the formula, we are going to solve by this analysis. Okay, so better I would write here, what is that? Here only I will write one thing, that I am not going to remember the formula. What I am going to remember is that VA will come therefore 2 to the power n t kilog, and it will be killed by VREF in T1 time. So T1 time will be therefore, T1 time I will be getting as VA into 2 to the power n t kilog. So my total conversion time will be what? Conversion time will be what? It will be 2 to the power n t kilog and divided by VREF रह गया यार. Here VREF. So conversion time would be, TC would be 2 to the power n t kilog plus T1. Okay, and from there we are getting this formula. So this is what I am gonna remember. And maximum conversion time, this VA VREF would be equal, maximum conversion time would be 2 to the power n plus 1 into t kilog, or you can remember 2 to the power n t kilog plus 2 to the power n t kilog, and this will be your digital output. Okay, so all kind of ADC we have studied: dual slope type of ADC, flash type ADC, SAR type ADC, and counter type ADC. This is the conclusion. From here only, whatever the question is framed, all the questions will be framed from here only. That's my short guarantee. One question will be there from sample and whole circuit, that we are going to see. From sampling, they can ask the rate of sampling as well. So that we are going to see. I told you one thing, in ADC before there is a sample and hold circuit. So from there, what kind of questions they can ask, that we are going to see. Afterwards, everything will come from here, and everything is crystal clear, right? ADC becomes very complex for a lot of students. Let me tell you this thing, it becomes very complex that they will think that what kind of formula are there, how we will calculate the digital output. Nothing, just for everything we have developed the formula. We also have the concept clear. So if good question is coming with the block diagram, then we will be able to solve. If the question is coming in statement, then we will just write down the values and we will solve it. In the next lecture, we are going to see some specifications of ADC. Okay, like a resolution is there, that we have already studied. Also a lot of things are there, offset error, gain error. So these we are going to see in the next lecture, and we will solve some problems as well. So see the next lecture, there we will solve some problems, and then we will see the assignment. Okay then, thank you very much. Hi everyone. So till now we have studied all kind of ADCs, all four kind of ADC we have seen. Now we are going to see the specifications of ADC. So some of the specification we have already studied, like conversion time we have studied, resolution we have studied, and what else we have studied? Conversion time we have studied, resolution, quantization error also we have studied. So just I am going to revise it, or you can say just once more I am gonna explain it. Okay, after that we will see the assignment. So these are the important terms which you should be knowing to solve the theoretical question of ADC. If some question is coming on circuital way, then we will be able to solve it. But theoretical question of ADC will be solved by this much of information that I am going to give now. Okay. So this is your ADC. Analog input is applied VA, which is coming from a sample and hold circuit. And after that, you are having your n bit of digital word as an output. Now there is this new term that I introduced here, dynamic range. What do you mean by that? So it is nothing but Vref voltage only. It is reference voltage only. Okay. Dynamic range is nothing but a reference voltage only. But what do you actually mean by dynamic range? That what should be the range of VA that can be applied to this ADC. In counter type ADC, in dual slope type ADC, and in SAR type of ADC, what did we write? Your VA should be less than or equals to Vref, right? Or it should be greater than 0, certainly. So from 0 to Vref you can apply. So this is your dynamic range. This is your dynamic range, which is Vref minus 0. So dynamic range is coming out to be Vref. If I say that my applied input, applied VA can be from Vx to Vy. VA can be from Vx to Vy. Then what will be my dynamic range? That would be Vy minus Vx. Okay. So this is what you mean by dynamic range. So to a particular ADC, there has to be a range of VA which can be applied. So that is known as dynamic range. So now what will be the new formula of resolution? Formula of resolution we used to write Vref by 2 to the power n minus 1 or Vref by 2 to the power n. So what I can write now? Dynamic range divided by 2 to the power n minus 1. It can be nearly equals to dynamic range divided by 2 to the power n only. Okay. This dynamic range will be large and 2 to the power n will also be a large value. So that will not matter. This minus 1 will not matter much. So both formulas we can use. Your answer is not going to change based on that. Okay. So from this slide, you must have understood what is the meaning of dynamic range and what is the new formula of resolution we are getting. Other name of resolution is step size. Right. And if they are talking about resolution, that means certainly they are talking about, they are not talking about flash type of ADC. In flash type of ADC, there is no meaning of resolution. So certainly they are not talking about flash type of ADC. Apart from that, all ADCs are having a DAC. And if they are having a DAC, that means that will have the resolution. So if I am talking about the resolution of ADC, that means I am talking about the resolution of DAC that has been connected in the ADC. Right. Now let's see a curve between VA and this digital word output. Applied analog input and the digital word of output. So let's see the curve. Applied analog input and digital word output. So this is the curve. Now this was your ideal curve, right? This was your ideal curve, or you can say expected curve. What do you mean by that? What do I mean by that is that if I change my VA by a small amount from 0 to, if I am going to 0.001, then also I should expect a change in the digital output. Are you getting my point? This is my digital word output. If I am changing my VA only by a small amount, then I should expect a change in my digital word. Right? So with the change, it should be linear. Basically, if you are changing VA, digital word should also change. But this is what does not happen. Right? Let's take an example of 3-bit counter type ADC. So what will happen there? For 0 to 1 volt, only one clock cycle will come. Only one clock cycle will come. That means you will have output equals to 001. What do I mean by that? If your applied input is 0.9, then also your output will be 001. If your applied input is 0.7, then also your output is 001. If your applied input is 0.4, then also your output is 001. So it all depends on the resolution. If your resolution is higher, higher means, I mean, if my resolution is 0.5 volt, higher means I am having better resolution. Then what will happen? From 0 to 0.5, it will give me 001. And then 0.5 to 1, it will give me 010. You remember this? I am taking the example of counter type ADC. So at 0.4, I would be getting 001, but at 0.7, I would have been getting 010. So better the resolution. Resolution better means resolution, this value should be less. If 0.5 is my resolution, then I will have better range. Or I should say that with respect to the change in VA, I will see the change in digital output better. At 0.4 I am getting 001, at 0.7 I am getting 010, but in this case at 0.9 as well I am getting the same, 0.7 as well and 0.4 as well, right? So this is not our ideal curve. Getting the ideal curve will be very difficult. So this is how we get the curve. So from 0 to 1 volt I am getting 000 as output for 0 to 1 volt. This is just a random curve. It is not, I am not saying that this curve I am getting from counter type of ADC or from any other kind of ADC. Just a random curve that from 0 to 1 I have designed a ADC such that for 0 to 1 my output is 000. If my applied input is 1 to 2, my output is 001. For 2 to 3 it is 010, 3 to 4 it is 011, 4 to 5 it is 100, 5 to 6 in that manner. This is the output I am having. So this is your actual curve. ये कर्व की स्पेलिंग भाई बड़ी. This is your actual curve. Now tell me one thing, what does this space represent? What does this space represent? This represent your resolution. What do you mean by resolution? What do you mean by resolution? That when I will detect the first change in my output, I was applying 0 volt, I was getting 000. I was applying 0.4 volt, I was getting 000. I was applying 0.99 volt, I was getting 000. But just as I applied 0.1 volt, I was getting 100. Not 0.1, sorry. Just as I applied 1 volt, I was getting 001. Just as I applied 1 volt, I was getting 001. So what is my resolution here? 1. Same goes here. If I was applying 1.001, I was getting 001 only. 1.5 also I was getting 001 only. If I was applying 1.99999, then also I was getting 001. But just as I applied it 2.001, at that time I got 010. So just as 2.1 I got 010. So this is what do you mean by resolution, right? Your ADC is able to detect the change of 1 volt. Your ADC is able to detect the change of 1 volt and it will reflect that change in your output. So for 0 to 1 volt it was giving the same output, but after 1 volt it will give a different output. So this is what is represented by resolution. So this is your resolution. Say yes or no. So this space, or you can say this space is parallel to this space. So this space is your resolution. This space is your resolution. In DAC, what was your resolution? This was your resolution, right? In DAC, this was your resolution. But in ADC, this is your resolution. And do you remember one thing? That your resolution is always equals to 1 LSP. Do you remember this thing? If there is change of 1 LSB, at 000, I am having output equals to 0. If I make a change of 1 LSB, if I go from 000 to 001, then my output will be what? Equals to the resolution. You can say 1. In place of 1, I could have written R. In place of 2, I could have written 2R. In place of 3, I could have written 3R, 4R, 5R, 6R, 7R, 8R. Do you agree to this point? In place of 1, I could have written, because this space is R only. Another space is R. When your digital output is changing, that is represented by your resolution. I am just giving the deep meaning. We are not talking about a particular counter now. I am talking about ADC on a block level. Right? So this is your R, this is your R, this is your another R. So if my digital output is changing by 1 LSB, that means I must have worked for R distance. Right? So wherever in complete data converter chapter, wherever you see 1 LSB, that means they are talking about resolution. If it is written 4 LSB, what do you mean by that? 4 into resolution. And what do you mean by resolution? Dynamic range divided by 2 to the power n minus 1. 1 LSB will represent resolution. Okay, so this is what you need to remember. You don't need to remember, actually you have understood that if I change by 1 LSB, if my digital output is changing by 1 LSB, that means I must have worked for 1 resolution, right? What do you mean by quantization error? What is my quantization error here? In counter type ADC, what was the quantization error? Plus minus R. In SAR type of ADC, it was plus minus R only. Here also it is plus minus R only. Why is that so? At 0.9999 volt, you are having 000. Here you are having 000 output. At 0.999 volt, you are having 00 output. And at 0 volt as well, if applied input is 0 volt, then also you are having 000 output. It should be near to 001, right? At 0.9999 volt, as per the ideal curve, at 0.9999 volt, you are expecting the output to be 001, near to 001, but you are getting it as 000. So what is your quantization error here? That is equals to 1 LSB. At 0.9999 volt, my expected output was 001. And I am getting it near to what? I am getting it near to what? 000. This is my actual output. So it is equals to 1 LSB, no? This was the decimal equivalent 1, this is having a decimal equivalent of 0. So there is a change of 1 LSB. So what is your quantization error? That is equals to 1 LSB. And 1 LSB is equals to resolution. So it is always shown in plus minus. So quantization error is plus minus 1 LSB. Very simple formula, like actually no one will tell you the actual depth from where it came. And you don't even need to remember. You just need to remember, for solving the question, you just need to remember that LSB is equals to resolution. And if they are talking about quantization error, that means it should be equal to 1 LSB. And LSB is resolution only. So this thing, till now everything is clear, right? Now what if I shift this curve to this side? If I shift this curve to left side, just in that manner if I have shifted. So what will be my quantization error now? Basically this curve has been shifted in this side. So this point is minus R by 2 and this point is R by 2. Are you getting this point? This is shifted. This complete length is R, right? This complete length is R. So this would be your minus R by 2 and this would be your plus R by 2. So what will your quantization error become now? Plus minus R by 2. The curve is shifted. Here at 0.9, here at 0.9999 volt, now you are having in between 001, sorry, in between 000 and 001, whatever the bit you are having here. Are you getting this point? At 0.999, you are expecting your output to be, in the previous case, you were expecting your output to be 001. But now at 0.999, you are not expecting your output to be 001. You are expecting somewhere in between. So that means your quantization error has reduced by R by 2, no? Are you getting this point? Here the quantization error was 1 LSB. Now it has become half LSB just because I have shifted the curve. So in the examination, if they are asking the quantization error, always you will write plus minus half LSB, or you can say plus minus R by 2, always. Okay, do not write this. This will be used. In the examination, this will be used. And resolution is equals to step size, so you can write down plus minus half delta, where delta represent step size. Okay, so this formula is used. All the questions, all the gate PYQs has been solved by this formula only, because in the examination they are not going to give you the curve. They are not going to give anything. They will just write down the question in theory. So there, what will be the quantization error you will be using? Plus minus R by 2, or you can say plus minus half LSB, or you can say plus minus half step size. Just because I shifted the curve, my quantization error has reduced to plus minus half. Basically, here also it is reduced to minus R by 2, here also it is reduced to R by 2. Okay, so plus minus R by 2. Actually, the range of error is again R only. The range of error is R only. From minus R by 2, the error can be till plus R by 2. So what is the range of error? Range is again R only. Here, what was the range of error? It was also R only. Range of error did not change, but these values are changed, minus R by 2 and plus R by 2. So if in the examination they ask you the quantization error, so just remember this thing, quantization error is equals to plus minus R by 2. And what is your R? R is equals to dynamic range divided by 2 to the power n. So just by remembering these two formula, you will be able to solve all the questions of ADC, all the theoretical question of ADC. Otherwise, you already know how to solve the circuital question. If they have given a particular ADC, if they have mentioned the name of that particular ADC, then solving it will be a cakewalk for us. But if they represent that a block diagram, that this is a particular ADC, it has a dynamic range of this, it has a resolution of this, then find the quantization error. So what you are going to do, plus minus R by 2. Okay. So a lot of questions has been asked in this manner only, that they represent the DAC on a, sorry, not DAC, they will represent the ADC on a block level. They can represent the DAC on a block level as well. So this is how we are going to solve. So that's why I am writing down this formula so that you remember it. So till now these two formula we have to remember. This is the resolution and this is the quantization error. Now this you are going to study in communication system, quantization noise power. So that is equals to delta square by 12. So this can be asked to EC student only. Electrical students will not be asked. On this, no question will be coming for electrical student. This will be coming for EC and instrumentation only. Okay. Quantization error, that would be delta square by 12, and signal to noise ratio will be 6n plus 1.76 dB, where n is the number of bits. So derivation of this we will see in communication system in a very detailed manner. We will draw the PDF. We will see minus, PDF means probability density function. Okay, not your book PDF. Probability density function. So from minus delta by 2 plus delta by 2, and the magnitude will be 1 by delta, and then we will find the power. Okay, and we will find the average value as well. So average value will be 0 and power will come out to be delta square by 12. So quantization noise power is delta square by 12 and signal to noise ratio will be 6n plus 1.76 dB. So if they are asking a question on ADC and directly if they are asking these values, the quantization noise power will be what, or no, signal to noise ratio will be what, then you can directly write down these expression and you can get your final answer. Okay, so ECIN will be asked, electrical students will not be asked here. Okay then. So let's move to the next thing, that is offset error. What is offset error? Even when there is no applied input, even if I apply VA equals to 0, still you are receiving some digital word. It could be anything, 001 or 010, anything. At 0 volt, I would be expecting that I would be getting 000. But still, if I am getting anything, that is my offset error. Okay. So that's it about the specifications. There are more specification of ADC, INL, DNL, okay, gain error. So these kind of specifications are also there. Conversion time we have already seen. So a lot of specifications are there. If you want to see a data sheet of ADC, then you can just type a random ADC Texas Instruments. So on first page only you will see the specification. So a lot of specification will be written there. Gain error, offset error, you can see those error, you can see those specifications. But whatever that are important for our examination, for our understanding, that we have covered. So from there we just got two formulas, quantization error and resolution. Just these two formulas from this particular slide, from last 20 minutes, you just need to remember only these two formulas. Okay. Now we will see some important point. It has nothing to do with ADC or anything, just it will be helpful in solving the problems. So that we are going to see. So what is an ideal comparator? You know this thing. What is an ideal comparator? This is the V positive potential, which is 3 volt, and V negative potential is VDAC. If I am asking you to draw V0 versus VDAC, how will the curve look like? V0 versus VDAC. So if VDAC is greater than 3 volt, if VDAC is greater than 3 volt, that means V negative is more, so output will be 0. Right? And if VDAC is less than 3 volt, then output will be high. So 1 and 0. Actually, it is plus 5 and plus VSAT and minus VSAT, but in digital we will represent 1 0. So 1 and 0. For VDAC greater than 3 volt, for VDAC greater than 3 volt, output will be 0. For VDAC less than 3 volt, output will be 1. Right? Now, if in the question it is mentioned that it is a comparator, it is having a positive threshold of 1 volt. It is having a positive threshold. What do you mean by that? So, what was expected that if this was ideal, if this was not having any threshold voltage, then what was expected? It was expected that when VDAC is greater than 3 volt, it will go to 0. But if it is having a positive threshold, then what will happen is that the output will go to 0, but at VDAC equals to 4 volt, at negative potential of 4 volt. So VDAC versus V naught. So basically the thing is, when the difference between V positive and V negative is equals to -1 volt, at that time output will change. Output will toggle. That means it is going from 1 to 0 at what point? At 4 volt. That means when the difference is -1 volt. So can you say one thing, that VA is effectively acting as a 4 volt source? What did I say? If I am saying that my positive, if my comparator is having positive threshold, that means at VDAC you need to apply 4 volt to change my output. So at 4 volt you will see the transition if it is having positive threshold. Initially you were seeing the transition at 3 volt because this was 3 volt and you just need to apply it 3 volt, then you will see the transition. But now if it is having a positive threshold of 1 volt, so at 4 volt you will see the transition. So what I can say, that my VA is effectively working as VA, or better I should write V positive. V positive is effectively working as VA plus VT, which is equals to 3 plus 1 volt. So in any of the question of ADC or DAC, if the comparator, it will be used in ADC only, because in DAC we will use amplifier as a, we will use op-amp as an amplifier, but in ADC we are going to use op-amp as a comparator. So these kind of questions can come in ADC only. So in ADC, if they are saying that your op-amp is having, or your comparator is having a threshold voltage of 1 volt, so what will you understand by that? That effectively my VT will go, my VA will go above by VT voltage. So effectively VA is working as VA plus VT, and in this case effectively VA will effectively V positive is equals to VA is effectively working as, for negative threshold voltage, it will work as VA minus VT. That is 3 minus 1 is equals to 2 volt. So it was supposed that it will go to 0 at 3 volt, but since there is negative threshold, so if there is negative threshold, that means it will go to 0 at 2 volt only. So from this slide, what you need to remember, that positive threshold, that means I will increase my analog input, and negative threshold, that means I will decrease my analog input. That's it. So this is what you need to remember. Don't think much about it. Positive threshold, increase the analog input. Negative threshold, decrease the analog input. This is your VDAC, which is equals to 2 volt. This is not T, this is your VDAC. Okay. So positive VT, VA will go to VA dash plus VT, and negative VT, VA will go to VA dash minus VT. Okay, so this is what do you mean by threshold voltage. Threshold voltage means applied VDAC should change. The transition value will change now. For threshold voltage positive, the transition value will increase. For threshold voltage negative, the transition value will decrease. Okay, so this is what you need to remember. Well and good. These will help in the problems. Now in some question, if they are asking, find the value of ramp voltage in dual slope ADC. So in dual slope ADC, we know that first VA will come in action and it will be going up till 2 to the power nt clock. Right? So this particular voltage is known as ramp voltage. Okay. VA will come in action and it will be going up. So the maximum value you get in ramp type of ADC, that is known as ramp voltage. Okay. So this is just one term that I wanted to introduce. What do you mean by ramp voltage in dual slope ADC? So maximum voltage you get there. So that is known as ramp voltage. Now you will see a term that is known as stuck at 0 volt or stuck at 1 volt. So here I am saying in this circuit, bit Y is stuck at 0 volt. So no matter whatever you apply at Y, it will always be at 0. It will always be at 0. So what will be your output always? X. This is your OR gate. So X plus 0 will be X only. And here, no matter whatever the input you apply, always your output will be 0. because it is stuck at 0. If this is stuck at 1, so no matter whatever you apply, x plus 1 will always be 1. No matter whatever you apply at x, it will always be 1. If it is stuck at 1, so output will always be equal to x. So y is stuck at 1, that means it will be always fixed at 1. Y is stuck at 0, that means it will be always fixed at 0. So till now, let's revise it. Whatever we have studied till now, this is what we have studied, that quantization error would be plus minus half LSB. 1 LSB means equals to resolution. This is your resolution, dynamic range divided by 2 to the power n, that is equals to 1 LSB. Okay. And then we saw these things, comparator with positive threshold and negative threshold. So if positive threshold is there, that means effectively you need to increase the VA. And if negative threshold is there, that means you need to increase the VA value. Okay. Positive threshold increase the VA value, negative threshold decrease the VA value. Right. Ramp voltage means whatever the maximum voltage you can achieve, and stuck at 0 volt, stuck at 1 volt, that means it is stuck at that particular voltage. Well and good. Let's start solving the assignment. So this is the first question. The temperature range of minus 40 degrees Celsius to 55 degrees Celsius is to be measured with the resolution of 0.1 degree Celsius. What should be the minimum number of ADC bits? What do you think? What is this? Minus 40 to 55 degrees Celsius. Basically, you need to measure 55 degree to 40 degrees Celsius. That means this much of temperature you need to measure from 55 to minus 40. So what is the range you need to cover? 95 degree. So this is your dynamic range. This is the range you need to cover. And resolution is 0.1 degree Celsius. That means from 0 to 0.1 degree Celsius should be given to 1 bit. 0.1 degree Celsius to 0.2 degree Celsius should be given to 1 bit. 0.2 degree Celsius to 0.3 degree Celsius should be given to 1 bit. 0.3 degree to 0.4 should be given to 1 bit. So this is how you need to give. Okay. So from 95 to, and resolution is 0.1 degree. Then how many bits you require? Basically, how many combination you require? From 0 to 0.1 degree Celsius was asking one combination. From 0.1 degree Celsius to 0.2 degree Celsius, it was also asking another combination. 0.2 to 0.3, it was asking another combination. So how many combinations you require now? This is simply what I have calculated. This is equals to 2 to the power n. 2 to the power n minus 1 actually. Using 3 bits, I can make 3 combination. Using 3 bits, I can make 8 combination. Using 3 bits, I can make 8 combination. So how many bits I require to make 950 combination? Using 3 bits, I can make 2 to the power 3 combination. Using n bits, I can make 2 to the power n combination. So 2 to the power n should be equals to 950. Or you can directly solve by the formula. Resolution is equals to dynamic range divided by 2 to the power n. Here it should be 2 to the power n, or you can put 2 to the power n minus 1 as well, doesn't matter much. So 2 to the power n would be dynamic range. What is the dynamic range? 95 divided by 0.1 degree Celsius. But here I gave you the concept that from 0 to 0.1 degree Celsius should be represented by one combination. 0.1 degree to 0.2 degree should be represented by one combination. 0.2 to 0.3 should be represented by one combination. So in that manner we are going. So what should be the n minimum? 10. Why 10? Because using 9 you will be able to make only 512 combination, but using 10 you can make 124 combination, right? Or you can, what you can do always is that you can just take the log. Okay, you can take the log. What that would be? 950, and always take the higher value. Always take the higher value. Why higher value? Because from the lower value you cannot generate those combinations. From the higher value you can certainly generate those combinations. So always take the higher value. So you can say it is like a least integer function. So, but the concept is crystal clear. Then this question was a very simple, very simple cakewalk it was, right? 95 divided by 0.1, 950. So 950 can be generated by 10. So without even using a pen, I will be solving this question in the examination. Let's go to the next one. For the digital output of a 10-bit ADC, when applied input is 10.3 volt is 11111. What is the quantization error? What do you think? What is given here? What is your 10.23 volt? What do you think? What is that? When your applied input is 10.3 volt, then your output is 11111. What does that mean? That you have reached till the maximum. You started from 000 and you have reached till the maximum. So this is your dynamic range. Are you getting this point or not? Look, resolution, I don't know. Okay, what is my resolution? Resolution is equals to Vref divided by 2 to the power n minus 1, or forget about it. What I know is that V naught is equals to R into D, right? 10.23 volt I will get R into, what is the decimal equivalent of this? 2 to the power n minus 1 only. 1, 1, 1, 1. What is the decimal equivalent? 15. Or you can say 2 to the power 4 minus 1. So here 2 to the power 10 minus 1. So what is the resolution here? One by 100, or you can say 0.01. Now you will say that, sir, this formula we have studied in ADC. Sorry, we have studied this in DAC. Why you are applying in ADC? In ADC also there is a DAC, no? So that DAC also works as a resolution, right? So the DAC is giving you 10.3 volt, 10.2, 10.23 volt of output, 10.23 volt of output that DAC is giving you for having the resolution equals to R, and the bits it will be taking 10. Or you can directly see this is the dynamic range only, because till the max you have reached 1, 1, 1, 1, 1, 1. After that you don't have any other combination. So this is the dynamic range. So dynamic range divided by 2 to the power n, that 2 to the power 10 you can do. So that will be your resolution, no? So from here what you are getting, 1 by 100, 1 by 100 will be 10 millivolt. So what is my quantity? 1 by 100, 10.23, 1, 2, 1 by 100, right? If I multiply by 100, yeah, 1 by 100. So 10 millivolt. So what will be my quantization error? Quantization error, I told you one thing, always write down plus minus R by 2, right? So plus minus 0.5 millivolt. So if it is not 0.5 millivolt, sorry, plus minus 5 millivolt. So if it is coming in your numerical answer type, so you are not going to write 10. Okay, quantization error will be plus minus R by 2. So always you need to consider that the curve must have been shifted by R by 2. Okay, so quantization error would have been plus minus R by 2. So there is no error in the calculation, hopefully. 1 by 10, 1 by 100 it would be. So 10 will go upward. So 10 millivolt. So error will be 5. In a 4-bit weighted register ADC, sorry, DAC. This question is based on DAC, not on ADC. 4-bit weighted register DAC. The register value corresponding to LSB is 32 kilo ohm. What will be the register value corresponding to MSB? So what is the scene? To MSB you will have R, the next 2R, then 4R, then 8R. You don't need to mug up this formula 2 to the power n minus 1, because you will be getting confused in the examination, 2 to the power n minus 1 or n minus 1. So what you will think, okay sir, I am remembering weighted register type DAC. So R, 2R, 4R. So for 3 bits it was 4R. The LSB bit was having, for 3 bit it was having 4R. So for 4 bit it would be 8R, or you can generate the formula now, 2 to the power n minus 1. So 8R is equivalent to, so this was associated with MSB, because with MSB you are having least resistance, and with LSB you are having the maximum resistance. So 8R was equivalent to 32 kilo ohm. So R would be 4 kilo ohm. Very easy. The minimum number of bits that should be used while constructing a DAC to keep the quantization error below 0.4% of full scale value. So what is my quantization error? 0.4% of your full scale value. What they are saying? Minimum number of bits. In case of quantization error while constructing a DAC, 0.4. Okay. In case of DAC, what was our quantization error? In case of DAC, it would be Vref by, or V scale by 2 to the power n minus 1 only, right? There I did not tell you that plus minus R by 2 you need to do. It would be to Vref by 2 to the power, sorry, 2 to the power n minus 1. So it should be less than 0.4% of a full scale value. So 2 to the power n minus 1 should be greater than 250. 2 to the power n should be greater than 251. So what would be your n? What would be the minimum value of n? So 2 to the power 8 is 128, 256, right? 256. So n minimum will be 8. Did you understand this point? Did you understand this question? Quantization error in case of DAC. In case of DAC, you will take quantization error equals to plus minus r only. Plus minus r. What is your r? V full scale divided by 2 to the power n minus 1. And that should be less than 0.4% of its full scale value. So how many bits are required? 8. Well and good. Let's go to the next one. The figure below shows a circuit for implementing 8-bit D2A converter using two identical 4-bit D2A while with equal reference voltage. So all are having the same Vref, both are having the same Vref, and both are having the same number of bits as well. So both are having the same resolution as well. Assume that B0 represent LSB and B7. This is your B7 actually. This is your B7. So this is your B7 to B4 and this is B3 to B0. This you can solve on your own. This is not tough. And B7 represent the MSB. The op-amp is ideal to obtain the correct analog values corresponding to 8-bit DAC. At the output, then what should be the value of register R? So you need to find the value of register R. So tell me one thing, for 8-bit of DAC, 8-bit of DAC, अरे यार उल्टा बना दिया. 8 bits are there, you just assume there are 8 bits. So correct value you need to tell. So just tell me one thing, I am finding the complete resolution of 8-bit of DAC. I am finding the resolution of 8-bit of DAC. This complete circuit represent 8-bit of DAC. This is what they are saying. This complete circuit represent 8-bit of DAC. So I will find its resolution. How I can find the resolution of it? First I will put 0, 0, 0. Then I will see if there is any offset error or not. So first I will put all bits equals to 0. If I put all bits equals to 0, then what is the decimal equivalent here? 0 only. So what will be your V out? V out will be R into decimal equivalent. This will be 0. This will also be 0. Right? So 0, 0, no current here, V0 will be 0. So if I put all bits equals to 0, from B7, B6 to B1, B0, if I put all of them equals to 0, then what V out I am having? 0 volt. If I put one of them equals to 1, only first one I am putting as 1, this I am putting as 1. Okay, so did they give any resolution? No. So we can find the resolution, or we can assume any resolution, because it will not depend on resolution for sure. So let's assume the resolution. Assume both will be having the same resolution. What will be the resolution? Resolution will be Vref by 2 to the power 4 minus 1, and that we are assuming equals to what? Resolution we are assuming equals to 1. So if my decimal equivalent, here my decimal equivalent is 1. If I have put B7 to B1, all bits are 0. So all these bits are 0, 0 I am putting, and this I am putting as 0, 0, 0, 1. So what I will get here? 1 volt. And what I will get here? 0 volt. So what I put output I will get? This is 0, 0 minus 0, this will drive 0 ampere current. This is 1 volt here, so this will drive 1 by 8 ampere current. That 1 by 8 will be flowing from here. So 1 by 8 into 8. So V0 value I will get is minus 1 volt. So from here I am getting V0 value equals to minus 1 volt. Right? So for 8-bit of DAC as well, what is the resolution? If nothing was applied, your V0 was 0. 1 LSB is equals to 1 volt. So for 8-bit of DAC, this 8-bit DAC, how much resolution it is having? Resolution of 8-bit of DAC. You assumed this resolution equals to 1, and this is also 1 volt only, right? So what do you think when your applied input is B7, B6, B5, B4, okay? You put all these three equals to 0 and this as 1, and you put B3, B2, B1 and B0. This has 0, 0, 0, 0. What you are applying? in the input of 8 bit of DAC, you are applying 0, 0, 0, 1, 0, 0, 0. What output you will be expecting? Another 0. What output you will be expecting? With the resolution of 1 volt. So what will be the output? R into D. 1 into decimal equivalent of this. What that would be? 1, 2, 4, 8, 16. So output you will be expecting is 16 volt. Are you getting this point? I get to know that at 0001, if I assume resolution equals to 1, both are having the same resolution. If I assume resolution equals to 1, that means here I have applied decimal equivalent to 1. So this will be 1 volt. So at the output I am getting minus 1 volt. So for 8 bit of DAC as well, my resolution is 1 volt only. So if my resolution is 1 volt, that means what will be my output of my 8 bit of DAC? That would be R into D. And if I assume my input is 16, that means my input is 001, 4 times 0. That means decimal equivalent is 16. So what output I will be expecting? 16 volt only. So now I would be expecting 16 volt output for which input? For this applied input. Which applied input? For this applied input. Now what this DAC will think? That across me 00 has been applied. So I should give 0 volt as the output. Now what this DAC will think? That across me 0001 has been applied. So I should give 1 volt as output. Right? 0 minus 0, this will be 0 minus 0, this will drive 0 ampere current, this will drive 1 by R current. So 1 by R will be flowing from here. So V0 will be 8 by R. So from here what did you get to know? That now my output is 8 by R or minus 8 by R, and I am expecting my output to be minus 16. So my R should be what? 0.5 kilo ohm. That's it. This is the answer. Did you understand the approach? They are trying to make this complete circuit as your 8 bit of DAC. 8 bit input are there. So not this complete circuit, actually this much of complete circuit, they are trying to make it 8 bit of DAC. So it should work perfectly. For that you need to tell me the value of R. This is what they wanted. So if I put all bit equals to 0, so I am getting V0 equals to 0. If I put these bits 0, these bits 0, and this bit only LSB bit if I active. Only LSB bit if I activate, my output will be equals to what? Will be equals to resolution. So I am assuming these are having the resolution of 1 volt. So my output is equals to 1 volt. What does that mean? That my 8 bit ADC is also having a resolution of 1 volt. So if I apply my input with the decimal equivalent to 16 volt, then my output should be also equals to 16 volt. My output should also be equals to 16 volt. Now how this DAC will behave? This will get 001 here. That means it will give 1 volt of output. It will give 0 volt of output. So my output is coming out to be minus 8 by R. So value of R I should put 0.5 kilo ohm. Okay, very easy question. This should have been solved by you. Okay, this was not that tough. Okay, it should have been solved by you. Let's see the next question. This is also very easy. So a 4-bit D2A converter is connected to a free running 3-bit up counter as shown in the following figure. Which of the following waveform will be observed at V0? Now some of the people may think that, sir, what kind of question is that? Sir, if this is 0, there is a negative feedback present, so this will also be 0, sir. And what kind of circuit is that now? Like nothing we can comment. Sir, if this is 0, no resistance is there, how will I find the output? So the thing is, what they are assuming is that this is a D2A converter. So this will be made from some op-amp or some any other IC. So it will have finite output resistance, right? So that output resistance they are assuming here. It could be anything. It could be R. So what will be your output? What will be your V0? V0 will be minus 1 by R into output of DAC. V DAC. So here if I am having output of DAC as V DAC, so this is what they are assuming. Okay, so this DAC is having a finite output resistance. So what if this is your V DAC and it is having a finite output resistance of R, so what will be your V0? Minus 1 by R into V DAC. Okay, so you just need to draw the graph now. So what will happen? It is a free running counter basically. Initially all bits are 0, 0, 0. All bits are 0, 0, 0. So all are fed with 0, 0, 0. This is my Q2, Q1 and Q0. Then with respect to D3, D2, D1 and D0 I am writing. So D2 will always be 0. Now initially if it is 0, 0, 0. So here decimal equivalent is 0. So what will be your V DAC? VDAC will be, VDAC is equals to what? R into D. Decimal equivalent is 0 only, so output will be 0. In the next cycle, this will become 1. So D2 is always 0. Q2 is D3 is equals to Q2, D1 is equals to Q1, and D0 is equals to Q0. So this will become 1 now. So VDAC will be R. In the next cycle, what will happen? Q2 has become 1. So this will become 1, this will be 0, this will be always 0 only. And this will be 2R. Then in the next cycle, what will happen? 0, 1, 1. So these kind of questions, for solving these kind of questions, you just always need to see what is happening in the circuit. That's it. Nothing else. What it would be? Decimal equivalent is 3R. In the next cycle, what will happen? 1, 0, 0. 1, 0, 0. So now Q2 is 1. So D3 will be 1. D2 is at 0 only, and this will be 0, 0. So what is the decimal equivalent? 8R. Right? Are you understanding this point? So from 0, R, 2R, 3R, and directly 8R. So there is a sudden jump. Now 1, 0, 1 will come. 1, 0, 1 will come. So this is 1 only. D2 is fixed at 0, 0, 1. So 9R. 1, 1, 0 will come. D2 is fixed at 0 only. 10R. Then 1, 1, 1 will come. D2 is fixed at 0 only. 11R. After that, again 0, 0, 0 will come. So all will be 0, 0 only. So again 0R. So what is happening? 0, R, 2R, 3R, then sudden jump 8R, 9R, 10R, 11R, then again 0. What is that option? Option B. There is nothing like that. You are directly coming from 11R to 0. 0, R, 2R, 3R, 8R, 9R, 10R, 11R, and again 0. Then again in this cycle it will keep on going. So this is the output. So you just need to solve what is, you just need to see what is happening in the circuit. Counter will be counting up, then it is fed to the DAC. What DAC will do? R into D. DAC will do R into D. So what is the decimal equivalent? You just need to see, and this is how the graph will go. Let's see the next one. Digital ramp ADC means counter type ADC. I hope you remember it. Counter type ADC. ADC with 40 millivolt resolution. Comparator is having a threshold of 1 millivolt. So what will be your effective VA now? Resolution is given. Find the digital output for VA equals to 6 volt. I can write 6000 millivolt plus positive threshold it is. Comparator with 1 millivolt threshold voltage. So it is a positive threshold. So VA will become 6001 millivolt. What they are asking to find? Digital output. So for that we have the formula, right? For digital output we have the formula. What is that? Analog input divided by resolution, which is 40. 6001 millivolt divided by 40 millivolt. And I need to go with the counter. Counter means C. So I need to increase my grades. If I am getting C grade, that means I need to increase it. So how will I increase it? One more I will get. So 6001 divided by 40. Answer we can directly know, but just to calculate the thing also I am feeling tired, that's why. So what I am getting? 150.25. So what will be the answer? 151. This is in the decimal. You can get the binary equivalent. So for digital output I have given this formula. What is that? You just write down the VA. Here effective VA has increased to 1 millivolt. So effective VA has become 6001 millivolt divided by what? Divided by your resolution. So resolution is 40 millivolts. So that would be 151 will be your final output, because we need to go to the higher value. For C and D, for counter type ADC and for dual slope ADC, we always go to the higher value, right? The higher value. Now this is the question. Step size is 0.2. For this DAC, resolution is 0.2. Okay. Now these are 8 input bit. BCD inputs are there. BCD inputs are there. BCD code for most significant digit. That means tell me how many digits will be there in decimal. If 8 bits are there in BCD, that means in decimal there will be 2 digits. It could be 23. So 23, 2 will be represented by this value and 3 will be represented by this value. This is the LSB, this is the MSB, this is the LSB, this is the MSB. So BCD code for most significant bit, this is the BCD code for most significant bit. That means this is the BCD code for 2 and this is the BCD code for 3, right? So this is what it is written. Now what they are asking, full scale value. So step size we know. First, resolution you know, which is equals to 0.2 volt. What is your resolution? What is your resolution? Forget about it. What do I know? V naught is equals to R into D. V naught is equals to R into D. So maximum value of V naught. Maximum value of V naught is not given, that we need to find. That is full scale only. So maximum value of V naught I need to find, R into maximum value of decimal equivalent. What can be the maximum value of decimal equivalent? This I have already told, 99, right? With the 8 bits you can represent only 99. For 100 you require 12 bits. So this I have already told. With 3 bits you can represent 999 in case of BCD inputs. And in case of general, what would be the scene? 2 to the power n minus 1. So in case of 8 bits you can represent till 255. But in case of BCD you can represent till 99 only. So what will be the maximum value of decimal equivalent? That would be 99. So full scale will be coming out to be 99 into 0.2. So that would be 19.8, right? 99.2, 198 divided by 10. Yeah, 19.8 volt. Secondly, what they are asking, percentage resolution. Percentage resolution, what did I tell you? 1 divided by maximum decimal equivalent into 100. It would be near about 1.01, right? Or 1.001, 100 by 99, 1.01. I am really tired now, I guess. That's why my efficiency has gone down now. But I hope you are understanding all the questions. Now the second thing is D1, C1, B1, A1 and D naught, C naught, B naught, A naught is equals to 0, 1, 0, 1, 0, 1. What they are asking? They are asking the V naught value. V naught will be equals to what? R into decimal equivalent. R is given 0.2. 0.2. What is the decimal equivalent of this? 12489 and this is 5. So 59. 0.2 into 59. 11.8 volt. This is your V naught. Right? This is your 5, this is your 9. 59 into 0.2. 59 into 0.2. So that would be 11.8 volt. What they are asking? Weight of LSB of most significant bit, most significant digit in volts. What they are asking? Weight of LSB. Weight of LSB of most significant digit. That means they are asking the weight of this. What do you mean by that? When only this bit is active, then what will be your output? This is what they are asking. Weight of this bit. They are asking the weight of A1. So if I am asking weight of C1, that means when only C1 is active, then what will be your V naught output? So what they are asking is that D1, C1, B1, A1, D naught, C naught, B naught, A naught, all should be 0, only this should be active. So what will be the decimal equivalent of this? This will represent your 1, this will represent your 0. So what will be your V naught? V naught will be R into D. So weight will be 2 volt. So weight of which bit? Weight of the LSB of most significant digit. So the weight of A1 they are asking. So that means only A1 should be active. Weight of A1. Only A1 active. If only A1 is active, then what will be your output? What will be your analog output? This is what they are asking. Let's see next one. A 6-bit ramp type of ADC is there. Vref is 10.2 volt. T clock is 1 microsecond. VA is 3.4 volt. Threshold voltage comparator is this. You need to find the conversion time. Okay. Ramp type ADC, again counter type ADC. What will be the conversion time? I told you one thing. What was that? You just need to find VA effective divided by what? VA divided by resolution into T clock. What is your VA effective now? VA is 3.4 volt plus 0.005. 5 millivolt it is. 5 millivolt means 5 by 1000. So 0.005 divided by resolution into T clock. T clock is 1 microsecond. So resolution we can find. What is the resolution? Vref by 2 to the power n. 2 to the power n minus 1. Right? This we can calculate. अभी कैलकुलेशन करने की हिम्मत नहीं है मेरे में, तो मैं कैलकुलेटर से ही करूँगा. ठीक है, आप लोग डायरेक्ट कर पाओ तो कर लो, मैं तो कैलकुलेटर से करने वाला हूँ. मिल जा भाई कैलकुलेटर. This we are getting somewhat around 0.162 and reciprocal of this into 3.405, so 21.03. so just next value we need to take, so 22 microsecond. So conversion time would be what? 22 microseconds. So you remember it. In the summary, we wrote these expressions that for conversion time, what we need to do? VA by resolution into T clock. So VA, effective VA, what is our effective VA? 3.4 plus VA will be what? 3.4 plus 0.005, 5 by 1000. So 3.405 divided by the resolution. These kind of calculation you should do with the calculator only. In the resolution, we should not calculate it separately, because this is very near to 21. If it was 21, it would have been 21 microsecond, right? So better we should do the calculation with calculator only. So resolution is here 10.2 divided by 2 to the power 6 minus 1, that would be 63. So 10.2 divided by 63, then you take the reciprocal of that, multiply with 3.4 plus 0.005, and then you get this answer. Let's see the next one. So DAC output of a SAR type ADC has been shown. This is the DAC output. Note the complete output, DAC output. To the comparator, what do you feed? You feed VA, you feed VDAC. So this is the DAC output which has been shown. You need to find the resolution, clock frequency and digital output. So initial output what would have been? 0, 0, 0. Digital output we are talking about. What we are talking about? Digital output. So where we start from? 0, 0, 0. In SAR type ADC. Then what happens? Then what we write? Here we write decimal equivalent. Not decimal equivalent. Here we write VDAC value. So here VDAC is 0. VDAC would be R into D. Resolution I don't know. But I know one thing, the decimal equivalent of this is 0 only. So 0 into R would be 0. Now what will happen? It will be compared with VA. VA also I don't know. I don't know anything. It will be compared with VA. But certainly the thing is VA will be larger than that. So output I will get 1. If output I get 1, this will be 1, 0, 0. So this is the first clock cycle that everyone knows. Or it is a 6-bit ADC. So this will be the scene. So this will be your output. So now this will be your decimal output. This will be your DAC output. And what is that DAC output? That DAC output is equivalent to 1.28 volt. This is equivalent to 1.28 volt. So from here what did you get to know? That my R into decimal equivalent is what? Decimal equivalent of this 1000. What is the decimal equivalent of this? 1, 2, 4, 8, 16, 32. R into 32 is equals to 1.28 volt. Did you understand this point? In any kind of SAR type ADC, what is the first step? You will go from 000 to 1000. So I am going from 000 to 1000. So at that time, this will be from SAR. From SAR, what will happen? This will be fed to the DAC, and DAC will give the output. So that DAC output has been shown here. That is 1.28 volt. So these bits has been fed. 100 has been fed. So it will be multiplied with the resolution. You will find the decimal equivalent of this. Multiply with the resolution. You will get 1.28 volt. So R into decimal equivalent of this 32, and you will get the VDAC which is 1.28. So what will be the resolution? 1.28 divided by 32, 0.04. This will be the resolution. Are you getting this point? I hope it is clear to you. What is the clock frequency? This you should get after one clock cycle. This output you should get 1.28 you should get after one clock cycle. That means it is equals to 1 nanosecond. So what will be the clock frequency? 1 gigahertz. Answer of second. And what would be your digital output? Digital output. Where I can find? Here I can find digital output. So it is SAR type ADC. So first thing I know is that it would be analog input divided by resolution. Analog input divided by resolution. And I will go to the previous integer. I will go to the previous integer. So where it will settle down? What do you think? First clock cycle, second clock cycle, here you cannot tell the final output. Third clock cycle, you cannot tell the final output. Fourth, fifth, sixth, and seventh. At seventh clock cycle, you will tell the final output. In sixth clock cycle, you take in action all the bits. In sixth clock cycle, you will take in action all the bits. And in seventh, you will see whether 0 will come or 1 will come, and you will tell your final output. So this is my final output. This is my final output. And it is in between 1.52 volt and 1.56 volt. This final output, how this is my final output, did you get to know? I will start from first T clock, then second T clock, then third T clock, then fourth T clock, first T clock, second T clock, third T clock, fourth T clock, fifth T clock, sixth T clock. Here I should stop, but I told you we will take another cycle. We will take another cycle, we will see again the input is coming 0 or 1. So if 0 is coming, we will go back to 1 LSB, and if 1 is coming, we will stay there. If 0 comes, we go back, and if 1 comes, we stay there. So this is your final output, which is coming in between 1.56 to 1.52. So I can assume it is nearly equals to 1.54 divided by resolution. What is the resolution? 0.04. So 1.54 divided by 0.04, 38.5, and it would be equals to 38. Right? This is your output, and you can get the binary equivalent. Shall I get the binary equivalent? Only 6 bits are there, so you can write down the binary equivalent. 1, 2, 4, 8, 16, 32. Yeah, so what I need? 38. So 48 would be 38. Yeah, so output will be 1, 0, 0, 1, 1, 0. So this is the answer. This is your digital output. Did you understand how did I approach this question? It was a very straightforward question, very easy question. Just I know that in first clock cycle I will go to 10000. That means this is my equivalent 1.28 volt. So this is equals to 1.28 volt. So R into D, R into decimal equivalent of this, that is 32. So the resolution is 0.04 volt. Now from here to here, how much time I took? 1 nanosecond. That means this would be my clock frequency. And what is my digital output? Digital output I will find. I need to take the analog value. This would be my final output. This would be my final output. Right? Here everything will stop. So it is equivalent to near about 1.54 volt. This is my VDAC. So my VA should be near to VDAC only. Right? It would be near to VDAC only. So it is equals to 1.54 volt. So it is nearly equals to 1.54 volt. Resolution I already know. And in case of SAR type ADC, SAR, S stands for super. If I am super, I will go down only because I am already at higher side. If I am super, that means I am already at higher side, so I can go down only. So from 38.5 to I will go to 38. So this will be my output. Well and good. Very simple question it was. Let's see this question. 4-bit SAR type ADC is there. Output voltage range is 0 to 15 volt. I guess this is last. After that we will solve this good question. So this will be the last question that we will solve in the next video. For this video, this is the last question that we are going to solve. So 4-bit SAR type ADC is there. Input voltage range is 0 to 15. Output bit B1 has stuck at 0 volt. So SAR type ADC, SAR type. अरे यार तू सीधा रह जा भाई. ये क्यों नहीं सीधा रहता है? SAR type ADC. SAR type ADC is there, 4-bit SAR type ADC is there, input voltage range is 0 to 15. So can I find my resolution first? Resolution, voltage range 15 divided by 2 to the power n minus 1. So resolution will be 1 volt. Output bit B1 is stuck at 0. B1 is stuck at 0. So you will start from 0, 0, 0 only, no? This is your B1 which is stuck at 0. This is not going to change. It will be always 0. This is what they are saying. Which pair of input voltage produce the same output? Okay. So here we will write down the digital output and here we write down the VDAC. Resolution is 1 only. So no need to worry about that. My VDAC will simply be equals to R into D and R is 1. So my VDAC will be equals to the decimal equivalent of this. So let's find out for 2 volt. Okay. Let's find out for 2 volt. So how will my SAR type ADC will behave? So 4 clock cycle I need to take. So first clock cycle will come. Certainly at first clock cycle I don't even need to write down the VDAC value. I know at first clock cycle it will be 0. 2 is greater than 0. Output will be 1. If output is 1, it will make this bit as 1. Now 8 into 1. Decimal equivalent is 8. 8 into 1. VDAC will be 8. 8 is basically this is the scene. This is the comparator. Always if you get confused, you just make a comparator. I know one thing, that this is my VA and this is my VDAC, and output of this comparator will decide the SAR output, because this will be fed to the SAR. If SAR is getting clock, it will keep on going, right? Sorry, in SAR there is no concept of clock actually. SAR will respond with respect to 1 and 0. So in SAR, if 1 is fed, it will make this bit which is in action, this bit equals to 1, rest all as it is. Now what will happen? Another clock cycle will come. Now your input will be 0, because here VDAC is higher than VA. VA is 2 volt, so VDAC is higher than VA. So what will happen? Input will be 0. So now if input is 0, what it will do? This bit has already been treated. Now this is the next bit in action. So what it will say? That 100, you are not capable. Making this bit 1 was my mistake. So you should be 0 and next bit should be 1. So now I will try with the next bit. So here again decimal equivalent is 4. So again what it will say? That making you 1 was my mistake. You are wrong. I should not make this as 1. So I will make next bit as 1. I will make this bit as 1. So this is what your SAR will say. Because applied input will again be 0. Why applied input is again 0? Because if 4 is again greater than 2, so applied input will again be 0. It will say that you will go to 0. I will again make the next bit as 1. Will it be 1? No. It will not be 1, because it is stuck at 0. Stuck at 0. So this will be decimal equivalent will be 0 only. Now 2 and 0, who is larger? 2 is larger. So what will be the output? SAR will receive 1 output. So if SAR is receiving 1 output, so this bit has been treated, this bit has been treated, this bit also has been treated. Now this bit will be treated. If SAR has received 1 output, that means what it will do? It will make this bit as 1. 1 clock cycle, 2 clock cycle, 3 clock cycle, 4 clock cycles. We have done all the clock cycle. In the last, we need to see what we will receive at SAR. So what we are going to receive at SAR? This is decimal equivalent is 1. Applied input is 2. 2 and VDAC is 1. So what you are going to receive? Output as 1. So this will stay at 0, 0, 1 only. Here everything has been treated. Just one more cycle we take. We see the VDAC, that is 1. 2 is greater than 1. So VC will be 1. So if VC is 1, that means you will stay here only. If VC was 0, I will go back to 1 bit. Right? What we will receive for 4 volt? So let's check for 4 volt. Do it on your own. You will start from 0, 0, 0. Decimal equivalent is 0 only. First clock cycle will come. What will happen? Just as the first clock cycle will come, this will become 100. This is what? 8 volt. If this is 8 volt, then what will happen? Another clock cycle will come, which is 2t clock. Here I should have written 2t clock, 3t clock and 4t clock. Another clock cycle will come. Here 4 is less than 8. So you will receive 0 at the input of SAR. So what SAR will say? That making you 1 was my mistake. Now I will try with this. Now what is the decimal equivalent? 1, 2, 4. Decimal equivalent is 4. Here did I write decimal equivalent is? No. Decimal equivalent is 4 only. Now in comparator, no, usually we ignore the condition that both should be equal. Usually we ignore it, that here 4 volt is applied and VDAC is also 4. But if both are equal, your output will be 0 only. Okay, because V0 is given by A into V positive minus V negative. So if both are same, if both are same, output will be 0. So always remember, in SAR type of ADC, by chance if you are getting both input equals to same, both input same, then you will take output equals to 0. Okay, in SAR type of ADC. So another clock cycle will come. What it will say? Again I am having output equals to 0. So making this bit 1 was mistake. So I will make next bit as 1. But it is stuck at 0. Stuck at 0. Now what is the decimal equivalent? 00. Decimal equivalent is 00. So what your SAR will receive? Decimal equivalent is 0. So VTech is 0. This is 4. So SAR will receive 1. So what SAR will do? That in next clock cycle I will make the next bit as 1. Now what is the decimal equivalent? All the cycles have been completed, all the bits has been treated. Now in the last cycle what will happen? It will check what is the decimal equivalent. Decimal equivalent is 1. So 4 and 1 is being compared. So which is higher? 4 is higher. So if 4 is higher, it will remain there as it is. All bits has been treated, it will remain there as it is. That's it. So for 2 volt what you are getting? 0001. For 4 volt what you are getting? 0001. Both of them you are getting the same output. Let's check for 1 volt as well. Let's check for 1 volt. What we will start from? 0000. 0 is certainly greater, 1 is certainly greater than 0. So T clock will come. It will make 100. 8 volt, not satisfied. 0 output. At second T clock what will happen? This will go to 0, this will become 1. What is the decimal equivalent? 4. Again not satisfied. Again 0. What it will do? Next cycle will come, it will take it to 1, but it is stuck at 0. So it will be at 0 only. Now 0 is compared. 0 is compared with 1. So 1 is higher. So what will happen? Next cycle will come. This is your equivalent 0. 0 and 1. What is higher? 1 is higher. If 1 is higher, next cycle will come. What will be the output? 1. So what it will do? It will take the next bit as 1. But now what is happening? What is the decimal equivalent? 1 only. All the clock cycle have been completed. Now we need to check the final output. Now we will go towards final output. So this has become 1 and 1 is being compared with 1. 1 volt is compared with VDAC which is equals to 1 volt. Here decimal equivalent is 1 volt. So 1 is compared with 1 volt. So what will happen? Both are equal. So output will be 0. So what SAR is receiving? SAR is receiving 0 input. So SAR is receiving 0 input. So what it will say? Go back by 1 LSB. So go back to 000. So this is the final output. So 1 is mapped to 0000. Right? Let's check for other ones, or you can check on your own. I will check because I am the educator. So for one more I am gonna do. Let's do it for 4 and 6 is not possible. 1 and 2 is also not possible, that we have already seen. 6 volt. Let's check for 6 volt. Let's check for 6 volt. So how 6 volt will be starting from 000. T clock will come. It will become 100. Decimal equivalent is 8. Not satisfied. 0 will come on the next cycle. It will make the next one equals to 0. What is the decimal equivalent? 4. Yes, happy, satisfied. In the next cycle what it will say? That till now this was okay. I will try to make another bit as 1 as well. Now what is the decimal equivalent here? 6. 1, 2, 4. Decimal equivalent is 6. So not satisfied. So what it will say? That making you wait a second. Here only what did I do? What did I do? I took this as 1. But this will not happen. This will be 00 only. So again what is the decimal equivalent? Again it is 4 only. So next clock cycle will come. What will happen? In the next clock cycle, this bit has been treated, this bit has been treated, this bit also has been treated. So in the last clock cycle, this bit will be treated. So decimal equivalent is 4 and VA is 6. So what it will receive? 1 output. SAR is receiving 1 input. SAR is receiving 1 input. So what it will do? Whatever the bit in action, it will make it 1. So bit into action, it has made it 1. So now last clock cycle I need to check. 1, 2, 4, 5. 5 is less than 6. So SAR will receive 1. So if SAR is receiving 1, so I will be happy with 0, 1, 0, 1. Right? If SAR is receiving 1, so I will stay there. So 6 volt is mapped to what? 0, 1, 0, 1. Let's do for the rest one as well. What is left? 8 volt. 8 volt you will do on your own. I will do for 9 volt. Let's start with 9 volt. So first what is going to happen? T clock will come, not 8 volt. Yeah, it will receive 1 as output because 9 volt is greater than 8 volt. It will receive 1 output. What it will say? This was a good thing, but now 12. So what it will say? That taking you 1 was wrong. I will make you 0 and I will try to take this as 1, but that will not happen because it is stuck at 0. So 1 0 0. What is the decimal equivalent? Again 8. So what SAR will receive? Again 1. So third clock cycle, this will be the fourth clock cycle. So this is the bit into action now. So this will be 1 now. This is 1. So what we are receiving? 9. So at the 9, if we receive 9, then what will happen? 9 and 9 both are equal, so SAR will receive 0. So it will say that go back by 1 bit. So 9 is mapped to 1 0 0 0. This is what 9 is mapped to. Let's check for 8 volt as well, because why I should drop anything. So let's check for 8 volt. So if I check for 8 volt, I will start from 0 0 0. T clock will come. I will go to 1 0 0. 8 volt both are equal. For equal I told you one thing. Your output will go to 0. So SAR will receive 0. So what SAR will say? Taking you 1 was my mistake. I will make you 0 and next bit as 1. So what is the decimal equivalent? 4. Now he is happy. What he will say? That I will take the next bit as 1 as well. I will keep this as it is, next bit as 1 as well. But what will happen? This is stuck at 0. So it will be at 0 only. So what is the decimal equivalent? 4. Again it will receive 1. So again it is happy. What it will say? This is the bit into consideration. So I will take this bit as 1. Now last cycle we need to check what is the decimal equivalent. Decimal equivalent is 5. So what it will receive? 1. So if 1 is received, it will stay there only. That's it. So 8 volt is mapped to 0 1 0 1. So what you are getting? 2 volt and 4 volt are same. 6 volt and 8 volt are also same. Okay, let me check back again if there is any error from my side. 8 volt was my mistake. 0 1 0. Then this is not a mistake. Then 0 1 1 0. 1 1 0 will not happen. 4 it says I am happy. If he is happy, then I will take the next bit as 1. If next bit as 1, 5 and 8 are compared, so it would be 1 only. Yeah. So 6 volt is and 8 volt are also possible. So if I make another option, that is E, 8 volt and 6 volt. So yes, both are matchable. You check for 7 volt as well. If for 7 volt and 9 volt are also matched, then we can say that there is a gap of 2 volt. 2 volt and 4 volt are matched, 6 and 8 are matched. What if 1 and 3 are matched? You can check for 3 volt as well, or check for 7 volt. If they are matched, then we can come to the conclusion that with the gap of 2 they are matching. But forget about that. We have seen the concept. What do you mean by stuck at 0? That means this bit will always be stuck at 0. This is not going to change. This will be stuck at 0. So that will change our output. So this is the way output are changing. 2 volt and 4 volt are same. 6 volt and 8 volt are same. Now we are going to solve this question, which is based on sampling. The first block will be sample and hold. So this is what we are going to see in the next video. So in the next video, I will make the video and I will be uploading that video on YouTube. Okay, so from YouTube only I will integrate it to our next part. Okay, so let's meet you in the next video. Thank you very much. Hi everyone. So in this video we are going to solve this particular question which was asked in GATE 2016 examination. It is based on data converters, and from data converters it is based on ADC, analog to digital converter. So we will solve this question. We will understand the meaning of each block. We will also understand what is the meaning of thermometric code. We will also understand what do you mean by thermometric to binary conversion. We will understand the meaning of each line. But before that I will give you one important concept which you might not be knowing. So what your ADC does? What is the job of ADC? It will take an analog input. It will take an analog input and will give digital word as the output. Let's just say I apply 2.1 volt and I am receiving 010. For 3.1 volt I can receive different code which could be 011. So with respect to analog input, it will give me a digital word of output. This is what your A to D converter does. But tell me one thing, let's just say if this is my V in. If this is my V in. V in with respect to time. If this is my V in, then this V in will be fed to the input of ADC. Is that so? What is fed at the input of ADC? Analog input. So Vin will be fed at the input of ADC. No, Vin is not fed at the input of ADC. Why is that so? Look, this ADC will have some finite conversion time. For dual slope ADC, it would be different. For counter type ADC, for SAR type ADC, for flash type ADC, all ADC will have different conversion time. So it will take some time to convert the analog input to digital word. If I am applying 2.1 volt at t equals to 0, then I am not gonna receive 0010 at t equals to 0 only. It will take some time. It will take some conversion time. Now let's just say if I apply this input here, then what will happen? At t equals to t1, assume that this is my 5 volt. So I am applying 5 volt here at t equals to t1. So now what this ADC will do? This ADC will start converting 5 volt to the digital word. It will start converting 5 volt to the digital word. So this is the job of ADC, but it will take some conversion time. Let's just say the conversion time is 2 seconds. So it will take the time of 2 seconds to convert this 5 volt to digital output. So from 5 volt to getting digital output, it will take 2 seconds of time. But what will be happening at the input? At the input, the very next second, my input will be changing to 5.2 volt. At 0.1 second only, my input has changed to 5.1 volt. Now, if my input has changed to 5.1 volt, what will happen? At the input, you are seeing 5.1 volt, and now your ADC is processing 5 volt only, because 5 volt was applied at t equals to t1. Now, at t1 plus 0.1 second, input has changed, but currently it is processing 5 volt only. It will give the digital output after 2 seconds. So let's just say the digital output for 5 volt is 101. So it will give 101 after 2 seconds. But at the input, after 2 seconds, this might be the input or this might be the input. So after 2 seconds, at the input you are having 4 volt, but output you are getting corresponding to 101, and in between this much value would have come. 5, 5.2, 5.3, 5.4, 5.6, 5.7 or 5.1, 5.2, 5.3 again, and in these much values would have come. So input is continuously changing, but it is still processing this 5 volt for 2 seconds. So what did you understand by that? That input of ADC should remain constant for a particular time, so that it gets some time to process that particular input. That means this 5 volt should remain constant for at least 2 seconds, because conversion time is 2 seconds. So at least for 2 seconds it should remain constant. After that input can change. So for this process, before ADC, we always use sample and hold circuit. Always sample and hold circuit will be used before ADC. Now what is the meaning of sample and hold circuit? So here never Vin will be applied. Here VA will be applied, which will be coming from the output of sample and hold circuit. So what this sample and hold circuit will do? Okay, so let's check that out. So I will again redraw my Vin. This is my Vin. Okay, I am starting from t equals to 0. Let's just say this voltage is 3 volt. Now my conversion time I am assuming it 2 seconds. So now this 3 volt should stay constant for 2 seconds at least. This we have understood, that if it is changing continuously, then what will happen? This ADC will not be able to process these much of data. So it needs conversion time of 2 seconds. So at least 3 volt should be constant for 2 seconds. So what I am gonna do? I am gonna sample this signal with a time window of 2 seconds. What do you mean by sample? Sample is like clicking picture. I am here. Okay, I click the picture at t equals to 0. So the next picture I will click at t equals to 2 seconds. Let's just say here, this is my t equals to 2 seconds. So the next picture I will click at t equals to 2 seconds. And the next picture I will click at t equals to 4 seconds. This is my t equals to 4 seconds. So this is what sample means. Next picture I will click at 6 seconds. What do you mean by sample and hold? That means I have clicked this picture. I have clicked this picture at t equals to 0 seconds. So if my sampling time is 2 seconds, that means this picture will remain there till 2 seconds. So at t equals to 0, I got 3 volt. So that will be remaining till the next sample. Now next sample I am calculating at 2 seconds. So let's just say this sample was 5 volt. So this 5 volt will remain there till the next sample. Next sample I am getting at 4 volt. So let's just say this sample was 4.8 volt. So this will remain there till then next sample you get at 6 second. So let's just say it is 2.8 volt. So till the next sample you will have 4.8 volt only, and then now you are calculating another sample. Now you will have 2.8 volt. So what did you understand? If I am sampling and holding it, that means for 0 to 2 second, I am having 3 volt only. For 2 second to 4 second, I am having 5 volt only. For 4 second to 6 second, I am having 4.8 volt only. And in that manner I am going. Now what is this? This is known as VA. And this is fed here. That your input should, the analog input should remain constant for a particular time. So what did you get to know? That your sampling time should be at least greater than, or in the worst case equals to TC. Very important observation, very important, you will say very important formula, I should not say, very important observation only I will say. So very important observation which you need to remember, that your sampling time should be greater than or equals to the conversion time. Because if it is lesser, that means let's just say if I am calculating the sample here at t equals to 1 second, then what will happen? The input will change at t equals to 1 second, but it needs the conversion time of 2 seconds. So it will be processing 3 volt at t equals to 0 till t equals to 2 seconds, it will be processing 3 volt, but input has already changed. So that should not happen. When it is processing 3 volt, the input should remain constant at 3 volt, right? So always the first block of ADC is sample and hold circuit, which is not usually shown, but you should know that this particular input is coming from the sample and hold circuit. Okay, so this is the concept which I wanted to deliver. This we have already studied in our course only, but since I will be uploading this video on YouTube, so that's why I am explaining it again here. So now let's come to the question. So what this question is saying, that there is an input voltage, it has a input resistance as well, that is 75 ohm. Okay, and this node, these nodes are connected together. So in a comparator, negative node is connected together and positive node are connected with some reference voltage. Okay, now the op-amp is having an input capacitance of 8 picofarad. What do you mean by that? Look, op-amp are made from some MOSFETs or BJT. Some MOSFETs or BJT, it would be made from some MOSFETs or BJT. This is how your op-amp would be made. And MOSFET and BJT will have some input capacitance. Like all the components, be it MOSFET or BJT, they will have some input capacitance. So that will effectively become the input capacitance of op-amp. So all these op-amps are having any ICU design on a chip, all will have some input capacitance. So these op-amps are having some input capacitance. So how these input capacitance will be connected? So this is your op-amp. This is connected to a fixed potential, that is Vref. So input capacitance would be connected here, right? So this node is common to all, right? This node is common to all. So from this node to ground, 8 picofarad capacitance is connected. So let's just say I am making this node. From this node to ground, 8 picofarad is there. From this node to ground, 8 picofarad is there. In that manner, a lot of 8 picofarad capacitance are there. How many 8 picofarad capacitance are there? How many comparators are there? How many comparators are there? There are total 255 comparators. So how many total capacitance will be there? 8 picofarad in parallel to 8 picofarad in parallel to 8 picofarad. This node is common. From this node to ground, you are having 8 picofarad and all are in parallel. So 255 into 8 picofarad. So this much capacitance is there. Say yes or no. Now this node is connected to 75 ohm and then V in. Basically the scene is, this is your V in 75 ohm and then this node is common to all. So all the capacitance are coming in parallel. V in 75 ohm and from this node to ground you are having 8 picofarad and 255 are in parallel. So 255 into 8 picofarad. So this would be your capacitance value. This I am calling as R. Now what will happen? Let us say V in some voltage. So that will take some time to rise here, no? That will take some time to reach here. So what they are saying, The input must settle to an accuracy of half LSB even for a full scale input change for proper conversion. Now I saw at YouTube in some videos they were saying that here it should be output. No, it should be input only. They are talking about this input. It should not be output. What they are saying, this particular input of the comparator. One input of the comparator is VREV, other input of the comparator is this node. This node I am calling as X. So this node I am calling as X. All these nodes are X. So this input of the comparator should settle to an accuracy of half LSB, even for a full scale input change. So if my input is V full scale, then what should be my output? What they are saying? So X should settle, ideally X should settle to V full scale. But accuracy of half LSB means it can take the error of half LSB. It can take the error of half LSB. Ideally it should settle to full scale only, because this full scale will be charging this capacitor. But you know one thing, that to charge this capacitor completely it will take infinite time. So at least it should settle to half LSB accuracy. That means it can take half LSB of error. Just as, let's just say my half LSB value is, wait a second, half LSB of full scale, half LSB of full scale, half LSB even for a full scale. So you can write plus minus half LSB as well. So basically this much of error it can take. Now just as we reach this value, just as at node X we reach this value, this comparator will be in condition to give the output. Are you getting this point? At the comparator input is changing. If at the comparator input is changing, so there is the chance that the output will change. But now what the question is saying, that if the input is changing, if the input has reached to this value, at that time comparator will be giving the output, and those outputs will be taken by this digital circuit and we will receive corresponding digital output. Are you getting this point? Until we reach this point, until this node X reach this point, we are not in position to give the final output. So when we will come into the position to give the final output, when our X becomes this much. So what do you think, what is this? Like it will take some time. How much time it will take? What will be the equation of xt? Equation of xt will be Vfs e to the power minus t by rc. And I am saying that at t equals to t1, my X will be this much. At t equals to t1, my X will be this much. So what do you think, what is t1? I am saying that at t equals to t1, my X will be this much of value. So then what do you think, what is your t1? T1 is the conversion time. Ideally flash type ADC has a zero conversion time. If everything is ideal, zero conversion time, just as you apply the input, comparator will give the output that will be fed to a decoder and we will receive the digital output. But here the scene is, input capacitance are coming. That means the input Vref is stable, but input at the other node, at negative node, that is not stable. So we have to stabilize that particular input. If this resistance was not there, then what would have happened? Even though there is some capacitance, then still this input would have been stable. Directly input will be exposed. So all the output you will be getting at t equals to 0 only. If all the comparator delay, if this thermometric code conversion delay, if all delays are 0, so just as you apply the input, you will receive the digital output. But here there is some resistance, so this input is being stable after some time. And what they are saying, just as the input becomes stable at this, your comparator will be in action. Your comparator will be able to give the output. And if it is giving the output, at that time you will see the digital output. If comparator is giving the output, that is fed to this digital circuit and you will receive the corresponding digital output. Look, comparator is always in condition to give the output. But when you are going to check, this line states that when your X has reached to this much of value, at that time I will check my digital output. This is what this line is saying. So conversion time is t equals to t1. Are you able to understand this point? Are you able to grasp this particular line? This is the most important line. Vin is there, 75 ohm is there, this much of capacitance is there. This capacitance will take some time to charge. That means this X node is going up. So with respect to X node, you are getting the comparator output, but comparator output you are going to check only when your X is this much. This is what this question is saying. So at what time you are getting this X, that I am calling as T1. And what is your T1? T1 is your conversion time. And what is the relation we got for conversion time? The relation we got that your conversion time should be less than or equals to sampling frequency. There you go. From there we need to find the sampling frequency. That's it. This was the question. So from the first lecture onwards, when you are studying ADC, I told you one thing, that in the end I will tell you the meaning of sampling, why sampling is required, and how to solve the questions based on sampling. So yeah, this is the last video of our ADC, and here I am telling. In the first video only I told that there will be sample and hold circuit which will be used, and once we have the stable VA, we will get the digital word output. So here also the same thing is happening. What we are taking as a stable VA, that is this value. If we are having this value, at that time we can give the comparator output, and based on the comparator output, this digital logic will give us a digital output. Are you able to grasp this point? So all these things we are going to write down now. Okay. So if you are not able to understand, slowly you will understand. Okay, again we are going to write it down. So let it be here. Let this much of thing be here. Now I am going to draw it. That this is my V in. I am having a resistance of 75 ohm. This I am calling as R. Okay. And this is my node X. This node X is actually fed to all the comparators, where positive node is connected to Vref and negative node is connected to this X potential. Okay, and based on that we will receive the output, and then there is this digital circuit. There is this digital circuit which is giving us corresponding digital output. So this is our complete structure which is given. So this node X, this capacitance is 255 into 8 picofarad. This is the capacitance. So now this node X will charge. So how this node X will charge? In this manner. V full scale 1 minus e to the power minus t by RC. And at what time it will, what we need to find? Ideally it should be V full scale, but we can have the error of plus minus half LSP. And the time when we reach it, that time is T1. And here T1 is your, T1 will become your conversion time. Why T1 is becoming conversion time? If this particular block, this thermometric code binary conversion would be having some delay. Let's just say this is having some delay of 2 seconds. So what will be your conversion time? T1 plus 2 seconds, right? Here we are assuming this comparator is not having any delay, this is not having any delay, further circuit is not having any delay. This is what we are assuming. If this code converter was having some delay, or this comparator was having some delay, then that delay would have been added. But here T1 will become conversion time, because delay of other components are 0. So what do you mean by half LSB? What is the LSB? LSB is the resolution. I told you this thing. LSB is the resolution. Now tell me one thing. Can it ever go above VFS? No, it can never go above VFS. No, it can never go above VFS. It has to go below VFS only. So positive sign is needless, right? So we will take the negative sign. And what is your LSB? V full scale divided by 2 to the power n minus 1. How many bits are there? If there are 255 comparator, then how many bits should have been there? You could have analyzed by looking at the output bit, but they are not making the output bit. They have only shown 2 bits. It is certainly not 2-bit flash type ADC. It is 8-bit flash type ADC. How you can say so? Because there are 255 comparators. So what is the number of comparators? 2 to the power 8 minus 1. So number of bits are 8. So it is a 8-bit ADC. V full scale 1 minus e to the power minus T1 by RC. So n is equals to 8 here, n is equals to 8 here. So I will put the value of n equals to 8 and we will find the value. So shall I show you the calculation, or you can do it on your own? I think you should be able to do it on your own. VFS will get cancelled. Let's write down one more step. Otherwise people will be getting confused. 1 minus 2 into 2 to the power 8. What that would be? 256 into 2. That would be 255. 255 into 2 would be what? 255 into 2 would be 510. 510. V full scale is getting cancelled. 1 minus e to the power minus T1 by RC. I hope now you can solve on your own, right? So now I will solve the value and find the value of T1. Mark that R value is 75 ohm and C value is this much. Okay, so I will solve it by pausing the video and write down the answer. So after solving it, I am getting T1 equals to 0.953 microsecond. That means your sample and hold circuit should give the window of at least 0.953 microsecond so that it becomes stable here and then give the corresponding outputs. So you need a window of at least 0.953 microseconds. Did you understand this point or not? So I need a window of 0.953 microseconds. So what is the conclusion? That my sampling time should be greater than 0.953 microseconds. This is the sampling time. This should be greater than or in the worst case equals to. So you can just take the reciprocal. I just need to find the sampling frequency, right? What they are asking. Sampling rate or sampling frequency? Sampling rate. So just take the reciprocal of this. So what I am getting? 1.04 megahertz, or I can say mega samples per second. Right? Basically, here what was my sampling time? 2 seconds. So what will be my sampling frequency? Half. That means I am taking half sample per second. Half sample per second. What do you mean by that? In 2 seconds I am taking one sample. Half sample per second. What do you mean by that? In 2 seconds I am taking one sample. So in 2 seconds I am taking one sample. So sample per second also could be unit, or you can say hertz as well. Okay, you can say hertz as well. So you can say 1.04 megahertz. So your fs should be less than 1.04 mega samples per second. And what is the option? 1 mega sample per second. Okay, so fs would be 1 mega sample per second. Okay, if I had been the question paper setter, I would have put one of the option as 1.6 mega sample per second as well. Okay, then what people would think that 1.04 is near to, okay, not 1.04, 1.06 I would have put. So they would think that it is near to this, so this should be the answer. No, your fs should be less than that, and there is only one option. There is only one option. If it was the scene that there is option available 0.5 mega sample per second, then that could be also correct. Okay, here they are asking closest, but what they would say that which all are the maximum possible sampling rate. So anything less than 1.04 will work. So 1 mega sample, 0.5 mega sample per second. So I hope you must have understood the concept here, that what is the core concept, that first there is a sample and whole circuit. So you should give at least conversion time to that, so that it can convert it, then you should apply the next sample. So basically, let's just say if this was my input, if this was my input, and first sample I am collecting at T1, then at least I should give a window of 0.953 seconds, microsecond, to collect the next sample. Then again this window to collect the next sample. Then that sample would have come here, and it would take 0.953 second time. Basically at t equals to T1, let's just say at t equals to T1 you are having V in voltage. So that would take 0.953 second time to reach there, and you will receive a digital output. And in the meantime, V in will also receive another sample. So again 0.953 microsecond it will take and will give the final output. And in the meantime, V in will receive another voltage. So that process will go on. Sample and whole circuit will give voltage to V in, and V in will give voltage to the negative terminal of op amp, negative terminal of comparator. So that process will go on 0.953 seconds, 0.953 microsecond, and you are receiving the output. So that's the thing. So that's it about this question. But there is one more interesting thing which is not usually taught, but we will see this block. Usually what do we use here? When you study the standard flash type ADC, what do you use? Priority encoder. Priority encoder. 2 to the power n, priority encoder. Now what is this thermometric code converter? Thermometer you can say, or thermometric code to binary conversion. What do you mean by this thermometric code? So once you go into the industry, once you start working in the DAC team or ADC team, there you will be using this thing. What is thermometric code? So let me explain you. It is not relevant to your gate examination, but yeah, if they have given this particular block, then who knows, they can ask this question as well. Okay, they can ask this kind of question as well if they have given the block. So what is the meaning of thermometric code? So that we will understand by an example. Okay, so you know what is a binary code? You need to find me the equivalent resistance R equivalent with respect to these binary codes. That means if B0, B1 and B2, all are 0 0, that means all are open circuited. So what will be the equivalent resistance? Infinity. All are open resistance, all are open circuited, so equivalent resistance is infinity. And this is your this is your conductance, this is your resistance. Okay, resistance, conductance, so that is 0 0 0 1, that means this is on, sorry, equivalent resistance will be R. Okay, this G we will write, no need to worry. Now only B1 is on, this is decimal equivalent 1, this is decimal equivalent 2, so only B1 is on. We are going line by line. Now decimal equivalent 3, so if both are on, what you will get? R parallel with R by 2, R parallel with R by 2 is equivalent to R by 3, so R by 3. 1 0 0, next you will get R by 4. 1 0 1, next you are going to get R by 5. Basically R by 4 will come in parallel to R, R by 4 come in parallel to R, what you are going to get? R by 5. Here you are going to get R by 6, and if all come in parallel you are going to get R by 7. So here your resistance is not linearly increasing, but you can see your conductance is linearly increasing. If conductance here is G, then what it would be? 2G. Here it would be 3G. R by 2 is the resistance, then what will be the conductance? 3G, 4G, 5G, 6G and 7G. So what do you see? It is linear. Linearly it is increasing, no? With respect to bit, it is linearly increasing with step size of G. Right? It is linearly increasing 0 to G, G to G, but it is not linearly increasing. R by 2, R by 3. This is not linear relation. This is the linear relation. Now, if I need to implement the same circuit using thermometric code, what I will do? I will connect same kind of resistance in parallel. Okay, 7 same kind of resistance in parallel. And how I will start? Once I will not connect any of the switches. I am just telling you the meaning of thermometric code, that is important because the question has come. So R equivalent will be infinity and this will be 0. If T1 only is on, so what will be the R equivalent? R, and G will be, I am calling as G. Now the next what we are going to do, if this is on, we will keep this as on only. If one has become on, we will keep this as on only. So what we are going to do now? Next I will turn this one on. So R by 2, 2G. Now if these two are on, we will keep these two as on only. Next I will turn this on. So R parallel with R parallel with R, 3G. So if your design does not allow to you to make R by 2 and R by 4, if you are not able to make R by 2 and R by 4, you are only having the resistance R, then you are going to use thermometric code, not binary code. Let's just say in my design I need linear resistance. I need not linear resistance, sorry, I need linear transconductance. I need 0, G, 2G, 3G, 4G, 5G, 6G, 7G. This is what I need in my design. Somewhere I need this. And I only have the resistance R. If I only connect resistance R here and go with the binary code, what will happen? First only this R will turn on, so R you will get. Then next this R will turn on, again R you are getting. Then both will turn on, then R by 2 you will get. Very random it will be. Very random. So in that case what you need to do? You need to use thermometric code. Okay, this is just a depth I am telling, which is not required as per the question, but this block was given. So people will have the doubt of what is the meaning of that block, so that I am telling. So yeah, what we were doing. So here 4 will turn on, so R by 4, then all 5 will turn on, R by 5, 6 will turn on, R by 6, and then R by 7. So 4G, 5G, 6G and 7G. So both are serving the same purpose, you know. So what I can do? I can relate this thermometric code to binary code. This is how I am going to relate. So 0 0 0 was equivalent to 0 0 0 only, because you were getting both same. G equivalent was 0 only. And 0 0 0 1 is equivalent to 0 0 0 1. This was equivalent to 0 1 0. This was equivalent to 0 1 1. This was equivalent to 1 0 0. This was equivalent to 1 0 1. This was equivalent to 1 1 0. This was equivalent to 1 1 1. This truth table doesn't look like priority encoder or not. Yes, it is like priority encoder only. If you are clicking on T1 button, do not think about, if I have clicked on T1 and do not click on these buttons, then output will be given with respect to this decimal equivalent, which is 0 1 0 0 1. If I am clicking on T3 button, do not think about these two. Output will be given with respect to T3 only. So 1 0 0. And what is the good advantage here? In case of priority encoder, this 000 will give you don't care here. Say yes or no. Do you remember it? In case of priority encoder, if you are not clicking on any of the button, then at the output you will get don't care, not 000. And don't care can take value 1 as well. And if they take value 1, then that would be our issue. Basically, this is my final output of the ADC. This is my final output of ADC. So let's just say at the in all the comparators is giving me 000, all the comparators which are connected. I am not taking the example of 255 here. There are 255 connected. So if all the comparators are giving me 000, and if I use priority encoder, then 000 will give me output as don't care. And what if my don't care take 110 value? So what user will think? That here 110 you are getting, that means must have been 6 must have been applied. So that would give you wrong output. But if you use thermometric to binary conversion, there you see that you are getting correct output. That for 000 you are getting 000 only. So you can use this block as well, thermometric to binary. Are you getting this point? So that's why they use this block, and this is the meaning of thermometric code. With an example we understood where we are going to use thermometric code and how they are equivalent. Okay, if you need to study deep about this ADC, this kind of ADC, there is thermometric ADC as well, there is binary ADC as well. So if you need to study deeply about that, you can go to the lectures of Shanti Pawan sir. Okay, Shanti Pawan sir has a course on data converters that you can watch. But as a GATE aspirant, even for UG guys and even for PG guys, I do not recommend that. That course is very tough. Okay, I have tried studying that course. I haven't completed that, but somewhat I have studied that. Okay, that data converters course that is related to analog VLSI. Once you go into the industry, there will be, if you be analog engineer, there will be a team of DAC and there will be a team of ADC as well. Certainly there will be these two teams. And for these two teams, that course is like a must. Everyone should study that course. But that is the thing of later on. Just now I am telling it just for your information. So if you want to study, you can go there. It would be in the last. Okay, in the last lectures you will see this thermometric DAC and binary DAC that you can see. I am talking about DAC, not ADC. Thermometric DAC and binary DAC. There you will be using this configuration. So from using his reference only, I am telling you the expression. What do you mean by thermometric code and what do you mean by binary code? Okay, so I hope you must have understood each block of this question. What is the meaning of accuracy of half LSB? What is the first block? Why they are asking the sampling frequency? What is the meaning of sampling frequency? Why this block is used? How it is giving us digital output? And what is the use of these capacitance? How they are coming in parallel? All kind of things. Every single thing related to this question has been clear to you, right? So with this we end our A to D converters. Now to my YouTube subscribers, if they want me to bring whole data converters on YouTube, I have taught it for 7 to 8 hours and I can guarantee you this would be the best ever D2A converter you would ever study, at least till UG level or at least till GATE level. So if you want me to bring, I am asking you to share this video. If this get good response, then I would be happy and we will be bringing the next marathon on A to D converters or D2A converters, basically the complete data converters I can bring. So the demand is you need to share. Okay, if we get good subscriber, if I get good motivation, if I get the good response, then I can think of bringing the complete marathon. Okay, thank you very much. Now we are going to start CMOS VLSI. We can start, or logic family we will start, or we can start PLDs. So that I will see what I need to start and we will cover it very quickly. Now 2 to 3 lectures are remaining. That's it.